very easily see today conference session chair, Dr. Noor. He is in front of me, and in today's session, I have already sent a detailed program to Noor. And now I think it is my formal duty to introduce all of you with Dr. Noor, because he is going to chair today's session. So regarding Dr. Noor, I can say Dr. Noor is my old friend, you can say, although he's very enthusiastic new guy working in solid state ionics. And we have a good friendship, let us say, because when I was in too much young age, you can say, still I am not too much old, but when I was young, that time Noor is just doing PhD with a well-known professor, Professor A.K. Arop. So Professor A.K. Arop is just like my guru from Malaysia. He taught me many things related to solid state ionics. And with this own ICSEM, we have already with too many renowned speakers related to one major area of material science, you can say solid state ionics. So regarding Dr. Noor, now Dr. Noor is a senior lecturer in University Putra, Malaysia. Physics division, you can say Center for Foundation Studies for Agriculture Sciences, and is very young, bright student. Still, I can say he's only 32 years old, and now he is going to chair this session. The basic background behind that, he is a renowned researcher, I can say. That's why we have decided to make him, and his, if you can see his brief CV, I think Google Scholar, everything, he has already citation in his scopus more than 500. He has Google Scholar citation, you can say Google Scholar citation is 10 until 22 July 2000. So he already sent me, you can say, recent CV. Before joining this, you can say, this university, Dr. Noor is closely related with University of Malaya, where we have visited so many times. And he got PhD in 2017 from University of Malaya, Malaysia, with a well-renowned group. I have already informed you, Professor A.K. Arop is his own supervisor. With his blessing, I think we are in position to handle this conference and ICSEM 2021 successfully. So with this brief description of Noor, now I think I am going to say the panel in Dr. Noor hand. Noor, please.
Okay, thank you very much, Professor Pramod Singh. It's a great pleasure for me to chair this session and participate in this ICSEM conference. All right. So actually, this is my third participation, and I remember, yeah, I missed one conference. I think in 2017, I think, right?
No, 19.
19, I be there. I was there in 2019. Yeah. And I remember that during my first time visit to your place in Sharda in 2014, I think we brought a bus. I think we can say that one bus from Malaysia, right, to the Sharda University, and then we are really happy with the visit to Taj Mahal and some other place in India. So I think this conference is well organized by Prof. Pramod and team, and I think that this conference should be attended in the next year. I think next year, Prof, or next 2 years.
I cannot disclose these things. These things we are going to disclose in validatory section. Okay.
Okay,
so
bro.
let us start. Just a brief about all those. I think how many invited and plenary in this session.
Okay.
And we are going to start.
All right. I think today we have about 7 plenary invited presenter. So I think first presenter is come from Mexico, and where the time in Mexico is almost 11:30 p.m. I hope that we are going to invite Professor Caballero Bionas. I hope he's still awake at this time and still energetic to present in this conference. So, Prof, I think you can share your screen. And his title is about on synthesis and characterization of magnetic graphite oxide, phase composition, fine structure, and magnetic properties. So, without any further ado, I pass this session to you, Prof. Please.
Okay, now you can see my screen and you can hear me.
Philip.
Yes, Prof.
Philip,
Please.
Philip, everything is okay. You can just carry on.
Thank you very much, Dr. Singh. Thank you very much, Dr. Noor, for the presentation. I am very glad to be here again. This is my second time in the ICSEM conference. I've been in the first one in 2018.
Yeah.
So I am going to talk to you about let me put, okay. This is okay. I will minimize the video. Sure. So okay, I will talk about the synthesis and characterization of magnetic graphene oxide, where we will talk about the phase composition, fine structure, and magnetic properties of these materials. This is a collaboration we have between several institutions both in Mexico and in the United States, and in India. We have a collaboration with Pondicherry University, as well as Stanford University in the United States, and four institutions in Mexico: Instituto Politécnico Nacional, it's my institution, Universidad Marista, Sinvestav Mérida, and Instituto Potosino de Investigación Científica. This work is supported by our National Council of Sciences. Okay, so this this work will have an abstract, the introduction, that we are talking about the experimental details, the results discussion, and the remarks, and I will do a small presentation of my center, my research group, and acknowledgements. So in this talk, we are going to deal with a synthesis of magnetic graphene oxide, where the graphene oxide was prepared by a modification of the Humber's method, and afterwards it was decorated using ferric and ferrous solutions. Also, we made some modifications of the process to treat, to reduce or not to reduce the materials with hydrazine. And then we made several studies trying to elucidate the phase composition of the materials depending on the preparation conditions. And so we see several phases that influence both the magnetic properties and on other properties. So the interest of magnetic graphene oxide is still high. There are something like 5,000 publications in the later years, and it has several potential applications. For example, there are several reports on water purification, on electromagnetic field insulation, on catalysis of the oxygen reduction reaction. There are also reports of cancer treatment by magnetic hyperthermia, and different biosensors, and some potential applications on information storage, and maybe magnetic refrigeration. So this is a small scheme on how we prepare the material. We depart from graphene oxide that is later decorated with iron oxide nanoparticles, and then we observed the rolling of this sheet. We will talk later about this. So this is the material we are going to work with. Regarding the applications, we have some experiences about. We are able to introduce the magnetic graphene oxide into a microorganism, a unicellular organism that is a paramecium, that it survives by ingesting. It ingests the magnetic graphene oxide, and it survives. And the material influences its swimming behavior. We believe that this is the potential of having drug delivery capabilities. Also, we try the material to take some dyes and some heavy metals from water, and as it is a magnetic material, we can remove the adsorbent from the solution very easily. We try the material also as a catalyst for the oxygen reduction reaction in microbial fuel cells, and we observed a very nice performance compared with the usual catalyst made of platinum and carbon black. And we have the interest in using these materials after functionalizing and loading with cancer killing drugs, and make some medical tests, in vitro tests, and then in vivo tests to see if the materials can be activated. First, if they can be swallowed by the cells. The name is hard. And then if they can be activated by irradiation, and then if the cancer cells die or they explode. So there's a delicate balance on that, because the ablation of the cells is not desirable. It's not desirable, the ablation of the cells, but the death by apoptosis. And then future works can be done by taking some cancer lines and doing cultures, and then inoculating and in vivo tests and that. So this is a long-term, a very long-term project. We are also looking for collaborations in this regard. So this is some of the applications of interest of these materials. So about the introduction of the structures of iron oxides. Iron and oxygen have a very rich chemistry. They can form a lot of oxides and hydroxides, and so we will describe a bit the first ones. That is the magnetite. That is a mixed valence iron oxide composed of iron 3 and iron 2 oxides with a cubic structure with inverse spinal structure, where you can see how they organize the different atoms. And there is a very similar and very close related structure that is the magemite, that is also called gamma hematite, that has two allotropes, that is the tetragonal one, and also the cubic one with the same structure as magnetite. That it has the difference that it has the iron vacancies where it should be the iron 2 in magnetite. There is a vacancy in the magemite. So they are very, very isostructural, and so the elucidation of the structure of these materials by X-ray diffraction is very tricky. And also there is the final oxide, the most oxidized form of iron oxide is hematite, that is a trigonal crystal system. And there are three oxohydroxides that are the lepidocrosite, goethite, and acagenite. For example, I want to stress that these three are very, very porous. The structure is very open, so they're very suitable for absorption, for example. So these are the structures that we are going to deal with. Regarding the magnetic properties of iron oxides, many people have prepared iron oxide nanoparticles. These are the proposed structures. But as you can see, in the case of the magnetic configurations of magnetite and magemite, both are magnetic, have magnetic response, but the mechanism is different. In the case of magnetite, you have this spin ordering. You can interchange spins in the octahedral size, while it's not possible in the case of magemite. So both are magnetic properties, but not exactly the same mechanisms. Regarding all the series of materials, magnetite and magemite are considered ferrimagnetic materials with a very intense and positive susceptibility. And this is different regarding hematite and goethite, that are antiferromagnetic with the spin coupling is antiparallel, and they have a moderate and positive susceptibility, magnetic susceptibility. How do we prepare the material? Well, first we prepare our own graphene oxide by a modification of the Homber's method. basically we mix the graphite, sodium nitrate, and sulfuric acid in a nice bath, adding potassium permanganate and make a stirring on several times. And then we increase the temperature after adding water to begin the hydration of all the functional groups. And finally, we have the graphene oxide after the purification that has several oxygen functional groups, such as carboxyl, hydroxyl, carbonyl, and epoxy groups. And then for preparing our magnetic graphene oxide, we mix an amount of the graphene oxide and water, and then we add a mixture at pH 11, or you can control the pH, and adding the mixture of ferric and ferrous chlorides, and then we can choose if we make a reduction process or not. And finally, we get these flakes after, before grinding. We have these thick flakes that are very, very magnetic. As you can see here, they is very easily removed from the solution. And after grinding and drying, you have a very, very nice magnetic response. So for this study, we prepared 4 samples. We varied first the concentration of the solution of the ferric and ferrous chlorides. We used the stoichiometric relation of 1 mole of ferrous ion and 2 moles of ferric ions to have the stoichiometry of magnetite. And then we do an hydrazine reduction, and the other sample is without reduction. And also we reduce the quantity of iron to the half using the same proportion, but we have the total concentration of iron and the same. We did the reduction or not. The purpose of these experiments was to try to control the amount of nanoparticles within the graphene oxide sheet, and also study and try to control the magnetic properties, and also, if possible, control the absorption properties if the material is going to be used for water treatment. So we did several characterizations such as electron microscopy, EDS, zeta potential, Raman spectroscopy, infrared spectroscopy, X-ray diffraction, X-ray absorption spectroscopy, and vibrating sample magnetometry. For the X-ray absorption near edge spectroscopy, we performed this in the BM4.1 line at the synchrotron in Stanford, California. So this is the line we were using. This is the sample holder, and this is the chamber where the samples are positioned. When this is the fluorescence detector, where you detect the fluorescence emitted by the samples, and this is all the line work, and this is how the spectra are acquired during the experiment. So we are going to talk about the results and discussion. As I showed before, the flakes we obtained, the powder in the solution that can be easily separated, and if the powder is filtered, you can obtain magnetic paper that is quite nice to see. Okay, this is our graphene oxide. It is quite nice. It's quite flat, and we have a few layer graphene. We see that we have some 10 layers, something like that are very, very nice exfoliated. And we try to see the microstructure by scanning electron microscopy. We try the first 2 samples that are the one with the double of the concentration of iron, and this is the reduced one, and this is the non-reduced one. So we in the reduced sample, we observed the formation of these tubes all around the sample, together with particles all around, and the evidence of the graphene sheet. And in the case of the non-reduced sample, we did not observe those tubes, and we observe also nanoparticles and on the top of the sheet. We tried some of the samples in transmission microscopy. It was very hard to study because as the materials are magnetic, the magnetic lenses remove the material from the grids, from the 10 grids. So it was very, very tricky. So we were able to measure only 2 samples, in fact. And we obtained these very nice images and this kind of rows that is made of this tube that is made of carbon. We studied it, and this is nanoparticles on the top and around the tube, and also inside the tube we observed the iron nanoparticles. So when we see other magnifications, we see this kind of crumbles or forest of tubules together with some sheet and together with some nanoparticles. And when observed in close detail, this tube, you can see inside you can see the nanoparticles inside also, and these are nanoparticles outside and some sheet. So this is a very interesting effect. We haven't seen it in the literature, and it's not explained. So we propose this rolling mechanism where you have the oxygen groups on the top of the graphene sheet, and also in the edges you have usually the carboxyl groups. And when the material is decorated, these groups roll onto itself, and they make this kind of structure. No, it's observed here in the TEM image. But when we observed the sample with this sample is diluted because it has less total iron contents, and this is not reduced. So we observed only nanoparticles and evenly distributed on the sheet. As you can see, these are very crystalline, but the sheet are a bit disrupted. It's a bit broken, as in the other cases is rolled. In this case, it's a bit broken. But as we mentioned, this was very difficult to measure because the powders flip over the grid, and the grid was even broken during the measurement. So the technician said it has to stop to measure because the TEM column will be contaminated by the magnetic powder. Well, we did other things. We tried to see the effect of the hydrazine reduction. What happens if the hydrazine is used? So the iron content is basically the same. Hydrazine does not influence, but it is after the GOM1 is the reduced one. So you see an important reduction on the oxygen content together with an increase in the carbon contents. And then, as we see the infrared spectra, we observe this. This is the region of the carboxyl group. This big one is the carboxyl group, and this one is the phenol group. So after the iron incorporation, this group disappears completely, so indicating that the iron nucleates on the borders of the sheet where the carboxyl groups are, and also well, here this mount is due to the carbon to carbon bonding. So the sheet is reduced by the incorporation of iron. And also you can see here these groups, these infrared peaks belong to the iron, to the surface iron bonded with hydroxyls. This is made in quite alkaline media, and also evidence of this iron oxygen carbon moieties. And the presence depends also on how the materials are prepared. So the most intense is the reduced samples, but the unreduced samples are very small, the materials. And this finally is the iron oxygen band related with the oxides themselves. So at this point, it's still tricky to elucidate which kind of iron oxide or hydroxide we have. So we tried Raman. Raman is very sensitive to local order, as we know. So we tried to differentiate the iron oxides by using Raman, and so we find several bands that are related with all the possible structures here. Well, we saw these main bands, this in color, and so we also observed the disappearance of the graphite band. So it indicates that the graphite structure is disrupted by the iron incorporation. So we can say we have a kind of disordered graphene here instead of a very ordered sheet. And we saw bands related with hematite, with goethite, with magnetite, but also we have problems with thermal and laser transformation of magnetite and goethite to hematite, because the Raman is made in air. So after you illuminate with the laser, the materials immediately decompose or oxidize to hematite. So it was also complicated to do a clear elucidation with Raman. As I mentioned, we saw bands related to hematite here, to goethite, magnetite, and magemite. But the main problem was that they're unstable towards the laser irradiation. But X-ray diffraction, that could be the most obvious technique to try to elucidate the phases. First, unfortunately, our X-ray tube it's a copper one, so it has a very intense fluorescence from iron with the copper radiation. So and also it was hard to identify, to separate mostly the magemite and the magnetite phases that have very similar peaks, as we mentioned at the beginning. But we were able to see some hematite. This peak belongs to hematite, so it was possible at least to see that we have hematite in some of the cases. And well, in the case of the most diluted sample, we observe a very amorphous signal. So the idea was to do some rivet analysis and to do X-ray absorption spectroscopy to really clarify the phases we have without affecting the sample by radiation, and to try to confirm the phase identities. So the first thing we did was rivet analysis using the GSAS program. It was complicated to do. We have some residues here. This is a bit high residue, mostly in the most amorphous sample. We tried with these structures, the magnetite, the hematite, and the goethite. We were not being able to incorporate magemite to the analysis. It didn't fit to the diffractograms, and so using the rivet analysis, we were able to define a composition, a phase composition on magnetite, hematite, and goethite. And as you can see, the sample with the higher iron contents and with reduction has a higher amount of magnetite and also has an important amount of goethite. In the case of the small GOM1 and GOM4 are comparable because they are reduced, but this GOM4 has half of the amount of iron, and it has a very high increase in the goethite composition. Probably because with less iron is highly possible to create hydroxides on the nanoparticle surface. And also in the case of GOM2 and GOM5, GOM2 has the higher amount of magnetite, and GOM5 has a higher amount of goethite. So it says that the reduced amount of total iron will lead to an increased amount of hydroxides because the nanoparticle surface is covered by hydroxides. But we tried also, as you see, there were a lot of residues in the rivet analysis, so we tried X-ray absorption spectroscopy. First of all, we measure the standards of the goethite, hematite, magnetite, and magemite. As you can see, they are different enough to try to do a linear combination of these standards for all our experimental materials. So as you can see, this is our experimental spectra. They have different features. They have here in the region of the absorption edge, it is related with the effective oxidation state. So as you can see, there is a slight movement of the absorption edge. So we can safely say that we have an effective oxidation state that is different with the samples. And so after having this experimental spectra, we fit the using the standards. We did a linear combination of the standards, trying to do the best fit of our spectra. As you can see here and here, this is the best one. And we were able here to incorporate magnetite, au contraire to the Rydberg analysis. We found magnetite here in the first sample, and also the higher phase, as in Rydberg, was magemite, both for the higher iron contents, that GOM1, GOM2, and GOM5, and also we confirmed that the sample with the that reduced sample with a lower amount of iron was rich in goethite. As you remember, magnetite and magemite were the most magnetic responsive oxides, and hematite and goethite have the lowest response to the magnetic field. So we will expect that GOM4 will have the smaller or the more reduced response to the magnetization. So here we also try to do the fine structure by X-ray absorption, extended ray absorption fine structure, and we only able to resolve the first two neighbors that were in all the cases that were oxygen and iron, and was the worst fit because as you remember, GOM5 was the most the less crystalline material, so it was the most disordered structure. So the fit was very bad, in fact. But at least we were able to say that is the iron, and the first neighbor to iron is oxygen. Okay, related to the magnetic properties, we made the measurements by rating sample magnetometry. We begin at 5 Kelvin. The equipment was an helium refrigerator. So we performed the measurements from 5 Kelvin to 350 Kelvin. In this, you have the hysteresis curve. The hysteresis curve show the materials are super paramagnetic. Now they have a very small coercitivity field. So you can say that the materials are super paramagnetic. And it's important to see here the magnetization, the saturation magnetization. It's quite high in these two materials. But in the case of GOM3, it has it's GOM4. I'm sorry. It has the lower magnetization capability as we predicted from the composition. It has the higher amount of non-magnetic phases, so the magnetization, in fact, is the smaller one. Here we make the quantification after the hysteresis curve. We have the saturation magnetization in this case. We compare here with commercial magnetite nanoparticles to compare the magnetic response. And in the case of magnetic nanoparticles, we have a higher saturation magnetization of 75 that reduces fast with the temperature, as it is expected. It's a common behavior. But in the case of the GOM1 and GOM2 that have the higher amount of magemite, the saturation magnetization is quite stable. It's very stable with the temperature. This is an interesting result. As we predicted also, the lowest response is GOM4 that has the higher amount of hematite and goethite. And also this is also an interesting result. The remnant magnetization is at room temperature is higher than the magnetite nanoparticles, and this is interesting because it is an evidence of magnetic coupling that is usually reported for multiferroic materials, but has not been reported as far as we know for magnetic graphene oxides. And finally, we observed also the coercitive field. It decreases as expected with the temperature as the anisotropy of the material increases. But we observed an increase here on the coercive field going towards room temperature that is different with the magnetite nanoparticles that decreases as usually expected in these materials. And this together with the remnant magnetization, it's an evidence that it can be some magnetic coupling between the nanoparticles that are separated by the graphene sheet. So this is a noticeable result. As we will not be able to determine the sizes, the particle sizes by microscopy because the problems I mentioned before, we tried the zeta potential. First we made a suspension of the materials in water. They are quite very, very good suspended in water. And as expected, the graphene oxide zeta potential is negative. And in the case of all our magnetic materials, it is positive because surface charged. But the one I wanted to show here is the hydrodynamic sizes that is related directly with the particle size of the material. The graphene oxide is quite large because the sheet is, as you saw in the 10 micrographs, our graphene oxide sheet are some 4 by 4 microns wide, so is very large, like 4,000 nanometers. And in the case of our magnetic graphene, the hydrodynamic size is more or less the same. It's the same order of magnitude. So the effects we observed in the magnetic properties are not related with the size, because sometimes or the magnetic effects are usually related with size. I mean, smaller size or bigger size changes the magnetic behavior, but this is not the case. The sizes are more or less the same. So this is an intrinsic effect of the materials. Afterwards, we try to test the absorption material of the sample with the higher amount of goethite. We said, okay, if the material is rich in goethite, it should have a very nice absorption property to some dye, for example. No? And indeed, it has graphene oxide has a very good absorption, and also the GOM5 that is richer in goethite. The absorption capacity is around 30 milligrams per gram of methylene blue, with a dose of 50 milligrams of the material by 100 milliliters. So it is you can say that the response is very different in the case of when you have the higher amount of magnetite or magnemite, the absorption is not so good. So this is a very nice result regarding the applications. This is the absorption kinetics, just to show you have a very, very nice absorption in the materials. When you increase the dose, 50 milligrams of the material reduce 5 ppm of methylene blue. And to conclude, we can say, okay, the magnetic graphene oxides were prepared with different iron contents and with different phase compositions by the hydrothermal method. And we studied the molecular structure, phase composition, and the magnetic behavior. We resolved the phases. The best resolution was made by XAMES. And we saw that we have mixtures of magnetite, magnemite, hematite, and goethite. The samples are super paramagnetic, and the behavior indicates that the goethite confirmed that an increased amount of goethite has the smaller magnetic response. The samples showed an increased magnetic remnancy, as well as an increase in the coercive field at room temperature. It suggested that is some kind of magnetoelectric coupling. It has to be more studied in detail. And we made some small application showing that the goethite is better to make remove a dye in water using as an absorption agent. This is our group. This is my research group in my center. We are at the Instituto Politécnico Nacional, that is the second public university in Mexico. We are the group of HESMAT, Materials and Technologies for Energy, Health and Environment, at CICAT Altamira, that is our center. This is my group. This is my colleague research. She's a researcher from a neighboring university. These two professors from another university, and these are my PhD students, Fernando, Jana Zilan, and Marcela. master students Sergio, former master Rafael, BAC students Sergio and Mike. And this is the synchrotron team. This is the people we work to the synchrotron to make these measurements. Myself, Dr. Espinosa, Dr. Salvador, Dr. Mustre, and Dr. Alejandro. Okay, Alexander. This is our center is we are in the state of Tamaulipas, is in the Gulf of Mexico shore in northeast Mexico. We are here in the middle of this city made of three municipalities, Altamira, Tampico, and Madero. We are here in the middle of lagoons and by the sea. We have a very nice beach here. We have 2 ports, a lot of industry here. This is our center. It's a small center. We are 13 researchers, some 40 students. So it's a very, very small center, but we are in a very nice location. And we hope you visit us someday. We can organize a parallel session of ICSEM in Tamaulipas when the times allow it. We have very nice beaches and very nice places to visit here. This is a souvenir of our first ICSEM in 2018. We were visiting the very nice Sharda University. We were with my family. They brought us to the magnificent Taj Mahal. So we were happy to be there, and we would like to be there another time. So thank you very much for your attention. I cannot pronounce it in Hindi, but thank you again.
All right, thank you very much, Professor. That is very interesting presentation about the graphene oxide. About the graphene, okay. There's 2 questions. First, from Professor Pramod. As a new beginner, what are the precautions one should take if he or she wish to enter in this area?
The precautions you must take. I don't know. You mean precautions like health precautions or material good practices?
I think Philip, that question is from my own side. So
Yes.
yeah, since we have already a renowned personality in this area, as a new beginner, whatever we feel that whenever a newbie going to enter and just want to develop his own laboratory in this area, that time what type of equipment or materials one should take precaution from that? That only my own question.
Okay, as entering the okay. Well, I don't. What can I say? I mean, we begin this line some 8 years ago. First,
Yes.
before I was working on semiconductors. So first, this is you have to know that working with graphene is a very dirty. It's powder and it's very black. So you in some moment of you have a lot of powder everywhere. So it is complicated work. We have to take some care because it is itchy. I mean, many people, this is a controversy between the toxicity of graphene, but graphene oxide is maybe it's not toxic, but it's very irritating to the skin and also for the respiration. So you have to take care. You have to change the philosophy on the lab because now you work with powders, and now you have to confine the areas, not to allow the ventilation. So this is one thing, no, and also you have to see that you will use a lot of water. That's one of the current problem on the graphene research, that you need a lot of water to make the purification. The synthesis, no, the synthesis is easy, I will say, but to make the purification you will need some water. So you have to enter in this water recovery and so on, no? And afterwards, the characterization is also different. When you work with films, you have your sample and you go on and do AFM, STM, whatever you want. But in this case, you have powders. In many cases, you have to make compact powders, and you have to take care of, for example, on laser susceptibility. When you do Raman, for example, Raman, it will affect sometimes your samples. In our case, it alter the iron oxides. So you have a lot of change in the philosophy, no?
Yeah, thank you.
Right. Okay, so there's another question from Dr. Sunil. Can we synthesize graphene oxide with magnetic ferrite by chemical methods, which is Hammers plus sol gel for photocatalytic activity? And can you explain the synthesis of high purity graphene oxide?
Okay, about the synthesis of graphene oxide, sure. I will. Let me show you the slide here. Okay, this is our synthesis. The synthesis is not complicated, but so you have to take some care.
Sorry, Prof, we can't see the slide.
You cannot see. Okay, sorry.
Okay.
You can or you cannot?
All right, now we can see.
You can see now. Okay, sure. Okay, first you have, this is a trick, an experimental trick we found. First, you have to mix graphite with sodium nitrate in the powder. You have to make a mixture, a very good mixture of the graphite and the powder. Usually, you use synthetic graphite from Aldrich. You use synthetic graphite because it has less metal impurities or non-metal impurities. That is the best thing, and it has to be very fine powdered, because otherwise you will have problems with the oxidizing thing. We found a very interesting thing here. We tried to use graphite from a very coarse source. It was big. The grain size is was bigger. So we have a very surface oxidation, but then all the surface became reduced, and a carbon dioxide evolved from the graphite, and it reduced it again. So you have to use very fine divided graphite. Then you have your mixture of sodium nitrate and graphite, and then you pour the sulfuric acid inside the ice bath. So the temperature can be about 5 degrees. You can use some salt to reduce even more. And this is important because when you add the sodium permanganate, if you add it fast or a high temperature, the graphite sheets will break apart, will unzip, as you tear all the sheet. So you have to add very slowly the sodium permanganate powder and keep it in cold during 2 hours, mixing thoroughly. And then you begin to increase the temperature and you add water. The water will hydrate all the groups. When you do the addition of sulfuric acid and sodium permanganate, you will form how it's said in English, sulfonate groups in the borders of the sheet, and in the top and in the bottom of the sheet you will form these manganate groups. The manganate will be like this on the top and on the bottom of the sheet. And then when you add the water will hydrate these groups, and it will form epoxy and hydroxyl. And in the case of the sulfonate groups, you will form carboxyl groups. Yes. So by controlling this, the temperature and the times, you will be able to change the proportion of the groups you obtain at the end. Yes. So then you will finish the reaction by using peroxide, and then you will purify by several washing in chlorhydric acid diluted to remove permanganate and sulfate, and then with water, and that's it. You have it. It's very important to dry at very moderate temperature, because if you dry above 70 degrees, you will decompose the oxide. So I will dry at 50 degrees.
Okay, Thank you very much, Prof. And one more last question. Are these
Yes.
materials show a good magnetological properties?
We haven't studied the magnetorological behavior. We only studied the magnetic properties using the powders in the vibrating sample magnetometry. We haven't studied magnetorology.
All right. Okay. Thank you very much, Prof. Okay, we go to the next presenter. Right.
Thank you very much.
Thank you very much, Prof. So we go to the next presenter, Dr. Sujit Kumar Chaurasya from India. He will present a topic about development of task-specific ionic liquid-based solid-state electrolyte for technological application. So without any further ado, I would like to invite Dr. Sujit to present. Yes, we can hear, but we cannot see your slide.
Okay.
Can you share your slide, Doctor?
Okay, Dr. Noor.
Okay.
I'll also thank the organizers of ICSEM-21 for giving me opportunity to present my work here. Myself is Dr. Sujit Kumar Chaurasya. I am Assistant Professor at Center for Nanoscience and Technology, Veer Bahadur Singh Purvanchal University, Jaunpur, UP, India. As you know, the title of my task is the development of ionic task-specific ionic liquid-based solid electrolytes for their technological application. So the broad scientific question addressed here, as we know that the ionic liquids are good electrolytes. They have high value of the ionic conductivity, widest liquidus range. That means it can be used at minus 200 degrees centigrade to more than 350 degrees centigrade, and wider electrochemical window, but they cannot use such devices due to their liquidous nature. So it is important to incorporate these ionic liquid into some solid matrices, some inorganic and organic polymer matrices. Then if these ionic liquid are incorporated into polymer matrices, then what changes occur and what are their technological relevance of this study? To seek the answer of the above question, we will study the following things. My talk is divided into the following section. First one is the introduction and brief idea about the energy storage devices and electrolytes, advantage of solid electrolyte over liquid electrolytes, and then we move to the polymer soft electrolytes, limitations, and then next one we move to what happen when we can combine the organic polymer and inorganic filler particle or matrices by the in situ technique and their method of preparation and some lab results, and last one, conclusion. As you know that nowadays all the aspects of the human life is associated with energy, and this energy can be obtained from the fossil fuels. And we also aware that in nature there is a limited storage of the fossil fuel. Though, therefore, our scientific community is moving towards the development of the alternate energy resources like batteries, fuel cells, supercapacitor. So in 2019, the Nobel Prize in the chemistry has been awarded to John B. Goodenough, Whittingham, and Akira Yoshino for their research in the improvement of the battery technology. Here we will discuss the thin film lithium ion battery. It has attracted much interest because of their utilization in many electronic equipment and due to its intimate nature of power supply. So we have to develop the new functional materials for the energy storage devices to meet the industrial and technological relevance. These are some examples of the flexible electronic devices that can use the polymer-based lithium-ion battery. So the given diagram shows the energy density of our specific power density of the various electrochemical devices. This is also known as tangent plot. Here we can see that we know that the energy density of and power density are the much crucial factor for determining the efficiency of any electrochemical devices. Here we can see that the supercapacitor have the higher power density and more than the rechargeable lithium battery, but they have less energy density. So we can tailor the know the efficiency of a devices by tailoring its combination. We also know that a solid state battery has is a electric devices which can convert the electrochemical energy chemical energy by the electrochemical reaction to the electrical energy. A battery consists of at least two cells. A cell consists of a anode, cathode, and in between there is some medium which can be used to transport of the ion between these electrodes, which could be in solid and liquid forms. There are on the basis of this there are two types of the battery: primary battery and secondary battery. Primary batteries are the non-rechargeable, while the secondary battery are rechargeable. Our focus is basically based on the secondary battery. This is the schematic representation of the working principle of the battery. Here we can see that in the charging process, the positive ions such as lithium or sodium ion can move from the cathode to anode, and in the discharging process it can be vice versa. And we can also see that the electrolytic potential, chemical potential of the this is the mu one is the chemical potential of the cathode, and this is the anode is mu b. We can see that the for the successful performance of the device we have electrochemical potential between them. Earlier we have used the liquid electrolyte for preparation of the solid for the battery. Here we can use the organic carbonate solvents such as ethylene carbonate, propylene carbonate. They are volatile, also they are flammable. Their liquidous range is very limited. They can be flammable. So here you can see that there is a overheating or overcharging of the lithium battery may suffer thermal runaway and cell rupture, and extreme cases it leads to the combustion. In March 2007, Lenovo recalled approximately 2 lakh battery at the risk of explosion, and approximately 10 millions of the batteries can be called back from the various companies used in Dell, Sony, Apple, Lenovo laptops. So these problems can be solved by developing the electrolytes which are based on ionic liquid. We can see that the electrolyte is the main component of the battery. It allows the movements of the ions between the electrodes, and these electrolytes should be in liquid or solid form. Solid electrolytes have various advantages, such as on the basis of the microstructural property, these solid electrolytes can be divided into the 4 parts. This is the single or polycrystalline solid electrolyte, amorphous or glassy electrolytes, and composite electrolytes, and polymer-based soft electrolytes. These electrolytes have various advantages over liquid electrolytes, such as safety issue. These are very not bulky in nature, and miniaturization of the devices. It's a wide temperature range of the operation. Here we can use the polymers based solid electrolytes. These polymer electrolytes can be obtained by immobilization of the cation, lithium salt or sodium salt into the soft polymer matrix. These solid polymer electrolytes should have the following properties. They have high cationic transference number. high ambient temperature ionic conductivity, and poor electrical conductivity. Here I also mentioned that we are concerned with the motion of the ions in solid state here. Also, they have high mechanical stability and good chemical stability. So different approaches have been used to increase the conductivity of the polymer electrolytes by which by addition of the low molecular weight solvents, which are known as the plasticizers. Plasticizers are entrapped within the polymer matrix and increasing the segmental motion of the polymer chain, and through the hopping mechanism as well as the segmental motion, cations of the dopant salts can move throughout the matrix and constitute the ionic conductivity. So the polymers electrolytes should have the following property. It have low value of the glass transition temperature, miscible with the polymer salt mixture, low volatile, and good chemical and thermal stability. Nowadays, ionic liquids can be uh, used as a plasticizer as well as supplier of the mobile charge carriers, and obtaining the same goal as the plasticizer. So here with the ionic liquids are room temperature molten salt. It consists of the dissociated cation and anion at room temperature. So it has very high value of the ionic conductivity, approximately 1 to 10 millisiemens per centimeter at room temperature. It has some properties of the ionic liquid. This is the high ionic conductivity, high thermal conductivity, heat capacity. These are the highly polar. They have low melting point, high thermal stability. Means if we use the electrolyte based on the ionic liquid, then they can be used in the wider temperature range. Means it can be, our device can be efficient work within the temperature range minus 200 degrees centigrade to more than 350 degrees centigrade. And they have low vapor pressure. They can be used as a reaction media for the different chemical reaction, and high flame resistance and flame retardancy. And these can also known as the desirable solvents. If we can change the structure of the cation and anion, then we can obtain the ionic liquids of the required property. And the expected role of the ionic liquid in polymer electrolytes, the immobilization of the ionic liquid in the soft polymer matrices, changing is melting in glass transition temperature. It also modify the ionic transport behavior. It also changes, reduces its degrees of crystallinity, provided more flexible polymer backbone, and modify the complexation behavior. Means it can modify the ion-ion interaction and ion polymer interaction and structure property relation between them. It also changes the kinetics of the crystallization of the polymers. So if we added the very large amount of ionic liquid, then it compromises its mechanical stability. It enhances the conductivity, but our polymeric membranes have low mechanical stability. So different approaches have been used to modify the property of the polymer electrolyte along with high thermal and mechanical stability. So one such approach is the making of the organic mixing of the organic polymer and inorganic fillers, suppose silica, titanium dioxide particle at a molecular level to make a organic inorganic hybrid electrolytes ionogels. The hybrid ionogels have combined the organic in molecular scale new materials with unusual features, and they show superior property compared to their pure counterpart. Organic moiety containing the functional group that allow the attachment of the inorganic network to the organic part. Why we use the organic hybrid electrolyte? The organic parts provide the have following advantage: high thermal stability, mechanical strength, porosity, non-flammability, and Organic part have flexibility is a fabrication, moldability, chemical stability. So our goal is to create material with a specific combination of property by combining different molecular building blocks in various ratios by controlling their mutual arrangements. The hybrid material can be classified into three different parts on the basis of their microstructure, that is nature of the interaction. This is the class 1 and class 2 hybrid and composition of different combination of the different components, that is organic inorganic. Uh, Electrolyte, it can be obtained by in situ dispersion of the inorganic filler particle into the organic polymer backbone by the sol gel technique, and simply by forming a composite by mixing of the organic polymer and nanofiller particle to form a nanocomposite. And another is the different processing method, that is sol gel hybrid materials method, intercalation material, etc. In class 1 hybrid material, no covalent bond between organic and inorganic phases. In class 2 hybrid material, there is a covalent bond between organic and inorganic phases. Third one is the making composite by mixing, etc. In situ formation. This one is the here is the some skeleton structure by the obtained by the dispersion of the silica particles. This is the pores and inorganic monocatalysis, and then we can use the here we use the water and precursors to for metal oxide particles. And the issues here, the organic inorganic hybrid electrolytes so shows homogeneous distribution of the both. This is the silica part, suppose inorganic filler particle, which enhances the interfacial compatibility between electrode and electrolyte, and stable distribution, no microphase separation occurs. Interaction between the two components by the cross-linker and enhances the structure property relationship. Inclusion of the functionality, tailoring the molecular structure. We can also synthesize the materials from the microstructure to nanostructure. These are the some simple building blocks for their synthesis route. This is the building blocks. This is the solution building method. In this method, we can dissolve the polymers, organic polymer, in some solvents like acetone, ethanol, methanol, etc. And then we have to another part is the sol gel method, in which we can prepare by the sol gel method the inorganic part and mix them, and then after over a time we can get a flexible membrane. And another part is the melt blending method, in which we organic polymer and inorganic filler particle are melted in a, they can be homogeneously mixed and then pressed in the thin film form to act as a separator membrane or electroactive membrane for the method. And there is the in situ method, which consists of a sol gel route. Sol gel route. The sol gel route generally consists of involves the 5 steps. First one is the formation of the sol, a colloidal suspension of the suppose precursor solution in water, etc., and gelation of the salt to form a network. And aging of the gel means polycondensation reaction continues until the gel transform into the solid mass, and drying of the gel at elevated temperature, and densification at high temperature. And this method can be optimized by depends upon the following factor, that is the ratio of the water and silicon. Suppose silicon or titanium precursor, nature of the solvent used, and their pH condition. pH is acidic or basic. Then we can obtain the particles from micrometer to nanometer range by changing these three conditions. So this is the some some steps involved in the synthesis of the silicon particle. Yeah, some, this is the hydrolysis and water condensation. This is the tetraethyl orthosilicate. Then we have water hydrolysis. In the hydrolysis, it is solvent technique is two types, that is the hydrolytic and non-hydrolytic. In hydrolytic synthesis we can use water, and a non-hydrolytic technique we ignored water, because ionic liquid, it can be well known that the ionic liquid physicochemical property depends upon the very low amount of water. If we can added very small ppm water to the ionic liquid, then its viscosity changes very rapidly. So we have adopted the non-hydrolytic solvent synthesis route for the preparation of these hybrid electrolytes based on ionic liquid. These are the some steps and different method of the preparation. Solution casting method. In this method, dispersion of the ceramic filler particle in the salt solution, addition of a specific amount of the organic polymer to the mixture, mixing by the stirrer and ultrasonicator, and then casting the mixture homogeneously on the substrate, and finally drying it, we get a polymeric membrane. And this is the spin coating. We have make a solution and then can be spin coated on the desired glass slide substrate to obtain the polymer thing. The thickness of the film depends upon the following factor, that is the viscosity of the solution, what is the solvent, angular speed, and spin time. These are the our some experimental results that can be obtained, that are obtained by my lab. This is the ionic liquid based membrane in solid state ionic devices. There is ion conducting polymer. Some first one is the immobilization of the ionic liquid into pure polymer to give polymer membrane, polymer ionic liquid membrane. And second one is the polymer and dopant ionic lithium sodium salt plus ionic liquid. And third one is the polymers plus salt plus inorganic filler particle. That is, we have to make the hybrid electrolytes by the in situ method. And role of ionic liquid can be role of ionic liquid can be how the role of ionic liquid changes within in the polymer matrices, and effect of the ionic liquid on the kinetics of the crystallization. This is the given phase transition temperature, that is the glass transition temperature, and melting temperature of the pure polymer PO, polyethylene oxide, changes upon the incorporation of the different weight percent of the ionic liquid. Here we use the ionic liquid BMIMPF6, 1-butyl-3-methyl immortolium hexaphosphate. Here we can see that the crystallinity of the degree of crystallinity of these membranes can be obtained by using the melting enthalpy of the membrane with respect to the 100% crystalline PO phase. Here we can say that the degree of crystallinity of the membrane changes from 75% to the 42% on the incorporation of the 20 weight percent of the ionic liquid in the polymer PO. And this is the degree this is the formula used for the degree of crystallinity. Here delta Hm is the melting enthalpy of the polymer plus IL membrane, and delta Hm0 is the melting enthalpy. This is which is 213.7 per joule gram for the 100% crystalline PO. Here we can see that the two samples with the PO plus lithium salt and X weight percent ionic liquid, and this second one is the PO plus LiPF6 lithium salt plus different weight percent of ionic liquid. Here we can see that degree of crystallinity decreases with the amount of the ionic liquid. And the ionic transport property of these polymer ionic liquid membrane can be obtained by the complex impedance spectroscopy technique. In complex impedance spectroscopy technique, a low AC signal is applied to a cell consisting of our sample, and we have to measure the impedance of the sample at the various frequency regime, and we also calculate the real and imaginary part of the impedance. This is the z dash is equal to mod z cos theta, and z double dash is the imaginary part of the mod z sin theta at different frequency, and we have plotted the complex plane, and from this plane we can obtain the bulk resistance RB of the sample. And from here, we are using the following formula. We have to use the ionic conductivity of the polymer electrolytes. And we here, this is the thermogravimetric analysis of the PO plus IL membrane. Here we can see that the pure polymer is thermally stable more than 400 degrees centigrade. When IL is incorporated into the polymer membrane, then their thermal stability slightly decreases, and it has a more thermally stable, approximately 380 degrees centigrade. Here we can also see that the TGA thermogram show that the different step of the decomposition. These steps of decomposition related to the decomposition of the different polymeric backbone, side grouped decomposition. And one of the most important property of the polymer electrolyte, the kinetic crystallization study, how the crystallinity of the polymer changes with time. The crystallization is the process of the phase transformation of the material into single or multi phases from their melted state. And here we can use the DSC thermogram with respect to the time, and then using the following equation we can obtain the relative crystallinity of the sample with respect to the time. And these are this is the DSC thermogram with respect DSC isotherm for the pure PO, and this is the pure PO plus IL 28% sample. Here we can see that with increasing the crystallization temperature, the crystallinity exothermic peak become flatter, and it shows that the samples takes more time to crystallize, and hence it can be enhances the flexibility of the backbone. And this is the relative crystallinity of the sample. Here at fixed crystallization temperature, sample takes more time to crystallize with added ionic liquid, which indicates the ionic liquid lowers the rate of the crystallization of the PO. We have also studied the rate of the crystallization kinetics by the polarizing optical microscopy. We can see that the polymers are generally amorphous or semi-crystalline in nature. In semi-crystalline polymer, it consists of the crystalline and amorphous phases, and the presence of the crystallites. Yeah, the crystallized or crystalline phases can be measured, can be viewed inter from the sporolites, and presence crystalline zone gives the sporolites. Rate of the crystallization can be determined by studying the sporolite size with time. Here we can see that the sporolite growth rate of PO at different crystallization temperature 50 degrees centigrade are given here. Here we have taken the sporolite size is 10 second, 30, 60, and 120 second, and these are the how the sporolite size increases with time for the polymer IL membrane. And using this membrane, we can plot the crystallization growth rate using the diameter with time. Here we can see that the sporolite growth rate is for the pure polymer is highest, and it decreases with the content of the ionic liquid, and is the lowest for the higher loading of the ionic liquid. And in this part, we have to discuss the results based on the organic inorganic hybrid electrolytes. Here we can see that the X-ray diffraction pattern of the our synthesized hybrid electrolyte, which is consisting of the pure polymer and added lithium salt. Here we can see that the pure PO consists to intense peak at 2 theta 19 and 23 degrees centigrade, which are the signature of the crystalline phase present in our polymer membrane. On incorporation of the salt or ionic liquid, we can see that these crystalline peaks are 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 riding over a broad halo. Here we can see that the broad halo, these halo can be used, is the signature of the amorphous phase present in the polymeric membrane. So we have to, by knowing the area of the crystalline peak and broad halo, we can calculate the degree of the crystallinity of the these membrane, and also we can see that degree of crystallinity of the pure PO is decreased with the IL content. And here we can also see that the crystalline peaks of the pure PO are slightly shifted to the their in comparison to the pure PO because of the slight change in the its crystalline structure or microphase separation between the polymeric membrane due to the incorporation of the iron salt. And
Dr.
this,
Sujit, you have another 3 minutes.
okay, just I
Okay.
conclude.
All
This
right.
is the DSC thermogram, and this is the ATR FTR spectroscopy study of the hybrid electrolyte, which shows the S which shows the 1023p wave number peak corresponding to the SIOSI skeleton formation in the hybrid membrane. And this is the same micro scanning electron microscope of the our synthesized hybrid electrolyte. Here we can see that each shows the layered structure along with the some crystalline zone consisting of the silicon nanoparticle embedded in the polymer matrices, and layers have been formed due to the slow solvent evaporation from the surface leading to such a structure. This is the 10 micrograph of the our synthesized hybrid electrolytes of the this pure and this is the 5% of the lithium salt incorporated membrane. It shows the formation of the SiO2 particle in the this size is approximately 10 to 15 nanometer. This is the ionic conductivity of the hybrid electrolytes, which shows that increases in temperature and follows Arrhenius type of the activated process. And this is the we have also we study the ionic material, so it is important to evaluate the ionic transference number and cationic and anionic cationic and electronic and ionic contribution to the electrical conductivity. So here we measure the ionic transference number using the transient ionic current. Our sample is placed between two blocking stainless steel electrode, and we have to measure the current versus time. And from this, using the following equation, we have to evaluate the T ionic. This is the 0.989. Suppose this shows that we have very less approximately 1% of the electronic contribution. We have to also measure the TLI, means ki we have cationic transference number due to the lithium ion. So here we have using this equation, we have make a impedance plot before and after polarization, and using this we have to obtain the lithium transference number, which is approximately cationic transference number 0.39. And this is the electrochemical stability window of our synthesized electrolyte with respect to the silver taken as a reference electrode. It is 4.4 volt, and we have taken the lithium metal as a reference electrode. It gives 5.2 volt. So it shows the higher electrochemical stability window. This
Dr.
is
Sujit, your time is over actually.
This is the possible application of these electrolytes in fuel cell, batteries, dye-synthesized solar cell, actuators, and these are conclusion. The interaction of the lithium ion with polymer matrix as well formation of the SiOS skeleton framework have been obtained. The formation of the silica nanosphere 15 to nanometer size have been obtained. The ionic conductivity of the polymer hybrid electrolyte mm, depends upon the number of the mobile ions, and the lithium transference number found to be 0.39, and this is the electrochemical stability window, and mixing at nanoscale without any mechanical belting leads to the low chance for the aggregation of the particle, which increases the interfacial comparability between electrode and electrolytes. Thank you.
Okay, thank you very much, Dr. Sujit. All right. So very nice presentation. There's several questions, but due to the time constraint, so I hope that you can answer all the questions in the chat box. Is it okay, Dr. Sujit?
Okay.
Right. Okay, so can we proceed to the next presenter, Professor Mat Abu bin Hassan Suzan from Bangladesh. His topic is about tuning morphology and magnetic properties of El Nico electrodeposited from above of reverse micellar. So I pass this session to Prof.
I think you can see the slide, right?
Yes, Prof. Yeah.
Okay. Please just a moment. Okay, thank you very much. So, first of all, I would like to thank Professor P.K. Singh actually. So I had the opportunity to attend a national conference also organized by Sharda University in 2020 in November. So this is my second opportunity to present my work in a larger forum. So I again thank the organizers for giving me the opportunity. So as you can see, I am from Bangladesh. So I work in the Department of Chemistry, Dhaka University, Bangladesh. And we have established a material chemistry research laboratory in the Department of Chemistry, Dhaka University, where we can actually now synthesize new materials, can study their properties, and also we are trying to apply them in some task-specific applications. Today, so my lecture will actually focus on tuning morphology and magnetic properties of El Nico, electrode deposited from a bath of reverse mycelium. So for the audience, for some at least, few terms may sound new, especially reverse mycelium. Those who work on surface chemistry, they are very familiar with mycelium, surfactant, reverse mycelium. But here, in addition to that, there is a process named electrodeposition, which is related to electrochemistry, and El Nico. So you know, aluminum, nickel, and cobalt. This is a ternary alloy. So actually we plan to prepare El Nico, so which can be electrode deposited from a bath consisting of inverted mycelium or reverse mycelium, and we want to control the morphology and magnetic properties of such ternary alloys. So here is the outline of my talk. So like as usual, I will start with a background, and then I will show the electrodeposition of aluminum, nickel, and cobalt independently. That means separately, and how we can control the tune, control the morphology using reverse Michaelis. And then I will move to binary metal alloys, combining aluminum with nickel or aluminum with cobalt or nickel with cobalt like this. And then finally, I will switch to electrodeposition of ternary metal alloys by exploiting all these tunable parameters. And then I will show preliminary results on magnetic properties of L-Nico electrodeposited from reverse Michaelis and then controlled. So let me start with background. So L-Nico, aluminum, nickel, and cobalt, I already explained. So L-Nico magnets are in fact the most commercially important permanent magnetic materials with useful magnetism, even when heated red hot. So actually, why L-Nico? So some rare metals also make permanent magnets which produce magnetic fields. So, but advantages of L-Nico are that the magnets of this kind can produce 3,000 times stronger magnetic materials magnetic field compared to rare earth magnet. So then in the beginning, or as you can see in the title, we have used reverse Michaelis. So reverse Michaelis, actually, this is a system consisting of micro emulsion, which is dominated largely by reverse Michaelis or inverted Michaelis. So these are thermodynamically stable, optically clear fluids and mixture of water, oil, surfactant. So these are macroscopically homogeneous. You can see these are clear, transparent, but microscopically these are non-homogeneous. So this can be water-rich or oil-rich domains separated by an amphiphilic film. And this naturally comprises surfactants, which may be cationic, anionic, or non-ionic. So in the core of the work, as I mentioned, we will use reverse Michaelis. So using surfactant oil-water system for electrodeposition, and this will serve as the electrochemical bath. And the concept is to electrodeposit metal coating on a substrate. So advantages are, we know, cost effectiveness, environment friendliness, lower consumption of energy, etc. So these have excellent coatings with higher purity, low porosity, good corrosion protection, and good control of the morphology. So here I have shown actually the schematic to prepare reverse Michaelis. We can take oil, water mixture and add surfactant. So there is apolar tail, hydrophobic tail of the surfactant and hydrophilic part, polar head group of the surfactant. And when these are dissolved in such oil-water system, as you can see, they combine, they aggregate to form reverse Michaelis. The difference from Michaelis is that, so here hydrophilic part is inside and the hydrophobic part is outside. The small core, the core of the Michaelis comprises hydrophilic portion, so metal salts can be dissolved inside such a core. So this reverse Michaelis therefore can serve as nano reactors, because if we say dissolve metal salts like cobalt chloride or nickel chloride, so this can be easily incorporated inside the core, and if some reduction reaction can be carried out inside these, or electrochemical potential is applied, so these will be converted to say metal, and say the size will not say increase to say after a particular size, which is the size of the or the dimension of the reverse Michaelis core. So these are confined. So diffusion to the electrode surface will be limited, and that will give us the opportunity to control the size and shape or morphology of the electrodeposited metal on the electrode surface. So in our previous work, actually, we have shown that reverse mycelium, here you see, I have shown 4 different types. The major variation is the hydrodynamic radii of the water pool. That means we changed the water and oil ratio. And if we increase the amount of water, you can see if you increase the distribution as well as the size, pore size of the reverse mycelium is increasing. That means that the metal salts that will be confined and maybe reduced to metals that will have wider size distribution depending on the water to surfactant ratio in the microemulsions. So actually we want to apply this concept for electrodeposition. So we have prepared, you can see here, I have shown cetyl trimethyl ammonium bromide, a cationic surfactant, 1 butanol and water. This serve as oil phase, so water. This ratio we have changed, so to control the water to surfactant ratio, and then we used as this as media, and say we prepare different stock solutions of individual salts, or say aluminum or binary mixture or ternary mixture, and then by electrodeposition using conventional setup, we have electrochemically deposited on a copper working electrode. So copper has been the substrate. So from reverse mycelium, so this has been used as a electrochemical bath, and we could electrodeposit so metal or their binary alloys or ternary alloys. So let me now show individually in detail about the deposition of say metals first, aluminum, nickel, and cobalt. So let me start with electrodeposition of aluminum from reverse mycelium. And aluminum, this is a common metal, but so we know that, and I have also explained the characteristics of reverse mycelium. So advantages of using reverse mycelium are that these have slower diffusion of ions. This eliminate hydrogen evolution. This is a common while depositing from aqueous medium, and we can control our morphology. But for aluminum, using aqueous system, which might be the best option, is that electrodeposition of aluminum from aqueous medium is impossible due to the very high reduction potential of aluminum. This is about minus 1.66 volt, and hydrogen evolution is common. So we think that in place of aqueous medium, if we use reverse mycelium as the electrochemical bath, we might overcome this problem. And so it has been a challenging task to deposit aluminum from reverse mycelium. So let me show how we faced this challenge. So we first prepared reverse mycelium, and you see in the reverse mycelium no characteristic peak for aluminum. So when we added aluminum, we can see reduction peak for aluminum, and then at say minus 1.23 volt, the reduction peak is observed. So that means applied potential, if we apply a potential something like minus 0.7.5 volt, 0.7.5 volt versus silver potential, we could electrodeposit because it is reduced. The process starts from here and say here complete reduction. So XRD pattern actually shows that the electrochemically deposited material has aluminum in the thin film deposited, and we can also analyze the crystallite size from this. And actually what happened from electrodeposition of aluminum, so we can see that if the concentration of changes, so here we can have electrochemically deposited aluminum. This is at a potential below reduction potential, and we could deposit, as you can see from the same images, from 50 to 100 nanometer deposits. And then when we have, say, this is, you can see at above reduction potential, so we made it faster. So aluminum is deposited quickly. So here, so you can see the structure is spherical, and here porous behavior we could observe. So that means that even the morphology or the nature of the electrode deposition can be controlled by controlling the reduction potential here. This is usual actually for reverse myceli. And the interesting thing is that for use of reverse myceli as the electrochemical bath, the reduction potential has been shifted. So similarly, we tried electrodeposition of nickel from reverse myceli, and you can see from XRD pattern that so we can have here for aqueous solution reverse myceli, and this is another case ionic liquid. So even for these, we can see that crystallinity XRD pattern of nickel electrodeposition from different media show a definite control in the morphology by using reverse myceli. In fact, this crystalline behavior may be changed or may be controlled, and say amorphous behavior may be introduced by controlling the concentration or the reduction potential. And say you can see scanning electron microscopy study of nickel nanoparticles here. And if we increase the say water to surfactant ratio, you can see here gradually changed, and you can see finally spherical particles here at high water to surfactant ratio. So the cracks are so common for the formation of nickel oxide. So if you keep it for longer time, so such cracks develop. But at such composition, even the crack formation has been minimized, and you can see spherical particle. So nickel also shows tunability of morphology by using reverse myceli. And if we check the energy dispersive X-ray, we have seen that the peaks for copper, you can see this is a refined figure, copper, and this is the substrate, and you can see on the peak for nickel here. And finally, the other material, so aluminum, nickel, and then now let us move to cobalt from reverse myceli. And you see that scanning electron microscopic images here at different electrodeposited cobalt using 20 molar cobalt on copper electrolyte at say here a potential below reduction potential for the deposition of 10 minutes from reverse micellar solution of CTAP. So here you can see that say here, so again, we have a control of hydrodynamic radii of the water pool here by controlling the water to surfactant ratio, and you can see that the morphology here changes. Here, something like vermicelli, this becomes a needle-like ultimately. So mechanism of formation of cobalt is similar as I have shown there. From aqueous medium, the diffusion is faster, but from reverse micellar solution, so it diffuses slowly to the electrode surface, and upon reduction, the deposition process becomes slower and gives definite shape. And if we say effect of decreasing amount of water in reverse micellar solution, that means the last one, diffusion is very slow at the electrode surface, so the deposition is also slow. That means the deposition morphology can be controlled by controlling the water to surfactant ratio. So we have seen that we could deposit aluminum, nickel, and cobalt independently, individually by using reverse micellar bath. So now, can we prepare binary metal alloys? So to resolve the issue, we have taken different mixture. Here you can see aluminum 3+ and nickel 2+. This is a mixture, nickel, cobalt, aluminum, and cobalt. So we have seen that observe different peak potentials for binary alloys of aluminum, nickel, and cobalt on copper electrode at a scan rate of 0.1 volt. So peaks become broad, and some satellite peaks can also be observed. So if co-deposition is possible, that is the deposits, we should have say the deposition of both materials. And say here we have seen that since such satellite peaks are observed, we understand that copper, which may also undergo oxidation, and say with nickel. So this actually happens in multiple steps, and ultimately, as we shall move to the same image, we have seen that the deposition has been possible for both metals together. And deposition for the formation of monolayer is very fast, as we can see from chrono potentiometry or chronoamperometric curve, and then the formation of multi-layer takes place on the monolayer. So here the same images are shown for deposits for aluminum, nickel, nickel cobalt, and aluminum cobalt. You can see that morphologies are quite different here. And here spherical particles with 50 to 200 nanometer, and here nanorod matrix, here large spherical and nanorod shapes with 40 to 350 nanometer. So cobalt shows nanorod type matrix, and aluminum and nickel shows spherical particles. So we can see the mixed morphology here. And you see for these cobalt shows nanorod type matrix, as I have described, and minus 0.6 volt is more favorable for cobalt deposition. So a lower potential. So this process is faster. So it depends in larger quantity than aluminum and nickel. So we have seen that aluminum, nickel, nickel, cobalt, aluminum, cobalt can also be successfully deposited on copper from reverse myceli. So a bath of reverse myceli is also good enough to co-deposit aluminum, nickel, or nickel, cobalt, and aluminum, cobalt. So next step is therefore to deposit our desired and targeted material Al-Nico, aluminum, nickel, and cobalt together. So ternary alloy, and see how did we achieve. We tried different mixture. So took aluminum, nickel, and cobalt in 1:1:1 ratio, for example, and also definitely other concentration ratio for this 1:1:2, 1:1.5, and these several mixtures. And we have also, so we have seen that for minus 0.65 volt, cobalt deposition is sufficient enough. Then we successively changed the redox potential because we want to co-deposit all the three. And we have shown the CBs of three metal salts together. And due to the formation of complex compound by disproportionation in reaction, peak shifts with high concentration. We can see a shifting of peak. And when we check the SAM and the EDX of Al-Nico deposits, you can see a complex morphology at different, let's say here minus 0.65, and you see this is minus 1.27, and you can see clearly the difference in the morphology. So nanorod matrix here with 50 to 80 nanometer size. So as potential increases, nanorod matrix diminishes, and large spherical particles with 200 nanometer size can be observed. And you see for these minus 0.65, this is cobalt deposition is 47%. Here cobalt deposition is 24%, and nickel here is, for example, 43%. And for this event, this is lower, 21 and 44%. That means this composition is also dependent on the applied electrochemical potential for electrode deposition. So it is because of anomalous co-deposition of nickel and cobalt. Nickel and cobalt have very close atomic numbers, so they can take part each space. When minus 0.65 volt is applied, maximum cobalt will come faster than nickel. So different concentration ratio of aluminum, nickel, and cobalt salt. And now we have, say, fixed for minus 0.65 volt as the reduction potential. And say here you can see in the previous slides we have shown the effect of reduction potential. Now we have shown the composition variation, and again we can see that the morphology is quite different. And nanorod type structure, so spherical particles for all compositions were obtained with different sizes, and for 1:1 and 0.25 here we have this one shows better morphology with the deposits. So it means that, and again, if we check that the EDX spectrum of deposits of Al-Nico with different concentrations, so we see that deposition of nickel was suppressed by the deposition of cobalt through nickel, was more than cobalt, as the applied potential is more favorable for cobalt deposition. So anomalous deposition of nickel and cobalt again observed, and we have actually two parameters that may interestingly affect the morphology. One is the reduction potential. That means we can control the kinetics of the deposition, and another is the composition of the feed solution for aluminum, nickel, and cobalt. And the XRD patterns of deposits of aluminum with different concentration. So here you can see the characteristic peaks of some reflection planes of electrodeposit. All composition matches the 2 theta value of aluminum, cobalt, and nickel. So aluminum and nickel show crystallinity, but cobalt shows amorphous behavior. And so last part is the magnetic properties of Al-Nico.
Sorry, Prof. You have 1 minute left.
So maybe I can finish by that. And magnetic properties of Al-Nico. So you can see that vibrating sample magnetometer analysis shows that as nickel content in the film increases compared to cobalt, it behaves like a hard magnet with high coercivity value. And so by varying the composition, the magnetic properties, these are also tunable. So reverse micellar solutions provide scope to control morphology of electrodeposited binary and ternary metals nanoparticles on a substrate. And here are the conclusions. So Al-Nico thin film can be prepared electrochemically on copper from reverse micellar depending on compositions. The morphology of deposits can be tuned by regulating the composition of 3 metals and also the reduction potentials of the 3 metal ions. And aluminum Al-Nico thin film shows a ferromagnetic behavior like a hard magnet. So actually these are 3 former students who contributed for this work. So thank you very much from Material Chemistry Research Laboratory.
Thank you very much, Professor Dr. Mat Abu. That is very nice talk and sharing. So there's one question from Professor Pramod. How to synthesize anisotropic nanoparticle using RM method?
Anisotropic nanoparticles, which are, what was the?
How to synthesize anisotropic nanoparticles using RM method?
Oh, RM method. So actually, it depends. So we have seen that by reverse micellar, crystallinity can be controlled by changing the composition. So composition, in particular, the composition of the reverse micellar, water to surfactant ratio. So from amorphous to crystalline behavior. So that can be changed, and even the crystallographic planes also change. I have not shown all the results in detail, but if you have a control over the proper parameters of reverse micellar, you will have the scope to have a control over the crystallographic plane dependence of the morphology, and of course by potential and this. So to make it anisotropic, definitely. So if you require a desired plane, that means properties will be dependent on that particular crystallographic direction. So you have to tune first the composition of the reverse micellar, which will serve as the bath, and then you carefully choose that which reduction potential will be suitable, because anisotropic that may be made by controlling any of the change in morphology of any of aluminum, nickel, and cobalt. So which composition you desire, and say which you want to get in larger proportion, then by optimizing those parameters and controlling the parameter for reverse micellar, you can synthesize suitable reverse micellar and then apply all these parameters collectively to have a anisotropic deposition of ternary thin film.
Okay, thank you very much, Prof. And so there's another one question, and due to our time constraint, so I would like you to answer the question in the chat box. So is it okay, Prof?
Okay,
So,
okay. So I will
thank you
reply
very much.
here. Okay.
Okay, thank you very much, Prof. So now I would like to invite the fourth presenter, Associate Professor Shinichi Yusa from Japan. His title is Preparation of pH Responsive Polymer and their Application. So, Prof, you can share your slide and start
Okay.
present. Thank you.
Okay. Can you hear me?
Yes, Prof, we can hear
No.
you.
Okay. Okay. Thank you very much. Okay. Okay. Thank you very much. Very nice introduction. First of all, I would like to appreciate to the organizing committee to invite me to this the very wonderful the conference. It's very nice. My name is Shinichi Yusa. I belong to the University of Hyogo. Okay, today's my title is Preparation of pH responsive polymers and their application. Okay. Okay, I'd like to introduce my university firstly. This is India, and this one is Japan. Maybe many people know that I think that from tomorrow, the Olympic Games start in Japan. However, I think the pandemic situation in Japan is not stable, not good. Therefore, I don't believe. I think it's not a good situation. Okay, I magnify the map of Japan, and our university is around here. We call this area is Kansai area. Maybe the many people know the Kyoto, Osaka. Of course, maybe you know Tokyo. However, Tokyo is very far from the Kansai area. And my university is in the Hyogo Prefecture. Hyogo Prefecture is next to Kyoto and Osaka Prefecture. And around here, our university. This city is Himeji City. Okay, this is Himeji Castle. It's a World Heritage. It's a very beautiful castle. And this castle is very near to our campus. It takes about 30 minutes by public bus. Therefore, after pandemic, when you come to Japan, please visit the Himeji Castle and our campus. Please coming. I welcome. And this is our campus, the School of Engineering, University of Hyogo. And this is our building. It's not so new, so old building. This is the inside of the building, and this is my laboratory. This is inside of my laboratory. Now 40 students belong to my laboratory. Unfortunately, my laboratory is not wide, very small laboratory. The Japanese country is very small. Also, my laboratory is very small. And my laboratory is not so clean. And this is our equipment, the 2 NMR and X-ray diffraction and TEM. We can use these equipments freely. Every day we use this equipment to study the polymer synthesis and polymer aggregation. Okay, I move to the scientific topic. However, this is the contents of my talk today. Firstly, I would like to introduce myself. And then I will talk about pH responsive unimolecular micelle. And then I will talk about pH responsive block copolymers. and development of sunscreen, and finally conclusion. Okay, first, I want to introduce myself briefly. Okay, in 1993, I studied, this is an undergraduate student. I studied under Professor Kamachi and Professor Morishima in Osaka University. I studied the synthesis of amphiphilic copolymer, containing cholesterol group. And in 1997, I was hired by Himeji Institute of Technology as a research assistant. And in 2000, I have received a PhD, Doctor of Science from Osaka University. And 2001, I started to study of the controlled radical polymerization, the reversible addition fragmentation chain transfer. We call it a raft polymerization. And 2004, the name of university changes from Himeji Institute of Technology to University of Hyogo. I don't move. Only the name of the university was changed. I don't know the reason. Okay. Okay, this is my research topic in the when I was a PhD candidate. I was prepared this type of the amphiphilic random copolymers, the composed of the hydrophilic sulfonate unit and hydrophobic the cholesterol unit. This one is only the fluorescence probe. It's not important. I prepared the amphiphilic random copolymer containing the hydrophobic cholesterol group. Maybe you know the cholesterol group is very, very hydrophobic. Therefore, I have prepared the many this type of polymers. However, always the polymer cannot dissolve in water because this unit is too hydrophobic. However, some polymer can dissolve in aqueous solution, and the polymer forms this type of the aggregate, interpolymer aggregate. And finally, I prepared some papers, and I can get the PhD. I think the preparation of the cholesterol monomer is not so easy. And this one is not my topic. In 1995, this topic is Professor Morishima topic. My professor, Professor Morishima, his topic, the main topic is this one. His topic was preparation of random copolymer composed of sulfonate unit and dodecyl group, the unit. He prepared this type of amphiphilic random copolymer. And this polymer is easy to dissolve in water. And also spontaneously this polymer forms a unimolecular micelle within a single polymer chain due to the hydrophobic interaction between the dodecyl group. Within only one polymer chain forms like a micelle structure. He called this one is unimolecular micelle. This study is very nice study. However, unfortunately, this study is not my topic. And this one is how to prepare the cholesterol group monomer, the hydrophobic cholesterol group monomer, the two-step preparation. Firstly, I prepared this type of the monomer, the fatty acid group containing the monomer. And next, the cholesterol group was introduced to prepare this type of the cholesterol group containing monomer. And sometimes this type of monomer shows liquid crystalline nature. Of course, this monomer does not have the color. However, the monomer form a line to show the something color, like this one, this picture. This one is a property of the cholesterol groups. And also, I have prepared this type of the monomer, intermediate structure of the monomer. I think this monomer is very interesting. However, I have not used this monomer at that time, in 1993. And I finished my PhD course, and I was hired in the Himeji Institute of Technology, and I started my original study in the new university, the Himeji Institute of Technology. That is a pH responsive unimolecular micelle. Okay. This structure is Professor Morishima's study, the unimolecular micelle structure. That means random copolymer composed of the hydrophobic sulfonate unit and hydrophobic the dodecyl unit. This polymer forms a unimolecular micelle in aqueous solution. And I think that I prepared this type of the random copolymer, the very similar structure. However, I introduced this one, the carboxylic acid group in the hydrophobic unit. I have prepared random copolymer composed of sulfonate unit and the fatty acid group, the pendant fatty acid group. Of course, the carboxyl group shows a pH responsive property. That means in the acidic condition, this unit is protonated. That is hydrophobic. It cannot dissolve in water like this dodecyl group. However, in basic condition, of course, it's the deprotonation to generate the anion. It's a hydrophilic, easy to dissolve in aqueous solution. Okay. Okay, this one is the conventional unimolecular micelle composed of the hydrophilic sulfonate unit and the hydrophobic dodecyl group, the random copolymer. This one dissolve in aqueous solution, the spontaneously form the unimolecular micelle within a single polymer chain. This micelle is composed of hydrophobic, the dodecyl group, the core, and the surface is covered with the sulfonate anion, hydrophobic sulfonate anion. The unimolecular micelle is very stable compared to the conventional micelle structure formed from the low molecular weight compound. This micelle is very stable. And also, of course, the hydrophobic guest molecules can be encapsulated inside of this micelle. However, it's very difficult to release of the guest molecule from this unimolecular micelle. If you want to release the hydrophobic guest molecule from the unimolecular micelle, this micelle should be dissolved in something organic solvent like methanol, ethanol, to reduce the hydrophobic interaction between this dodecyl group. It's possible to release the encapsulated guest molecule. However, this procedure is very complicated. However, in my system means a pH responsive unimolecular micelle. Only this carboxylate unit is introduced the hydrophobic pendant chain. This polymer composed of the hydrophilic sulfonate unit and fatty acid group. At acidic condition, this polymer can dissolve in aqueous solution as a unimer micelle, because this unit, if this one is protonated, this unit is hydrophobic. Therefore, they form a unimolecular micelle. However, at basic condition, this unit is deprotonate to generate the anion. Therefore, this polymer chain is expand due to the electrostatic repulsion between this sulfonate anion and this carboxylate anion. Therefore, this polymer chain expand. Of course, at acidic condition, the hydrophobic guest molecule can encapsulate inside of this micelle structure and very easy to release at the basic condition because the unimolecular micelle is dissociate, easy to release the hydrophobic guest molecule. Okay, I think that this concept is very nice, and I have prepared this polymer, and I checked firstly I checked the molecular weight versus pH value. I have measured the molecular weight of this polymer at different pH value using the static light scattering measurement. Always the molecular weight is the same, independent of the pH value. That means always the polymer chain dissolve in aqueous solution as a unimer state, single polymer chain state, not form interpolymer aggregate. And next, I have checked the size information depend on the pH value. We have used the dynamic light scattering to estimate the size information, the hydrodynamic radius, the size information. At acidic condition, the polymer forms a unimolecular micelle, the compact size unimolecular micelle. Therefore, the RH value was about 5 nanometer, very small value I can observe. On the other hand, at basic condition, at pH 9, the RH value increased to be about 12 nanometer. This suggests the unimolecular micelle dissociate to the expand state. Therefore, the size is increased. And next, I have checked the encapsulation of the guest molecule like this, the hydrophobic fluorescence guest molecule. The pyrene fluorescence, the 3:1 ratio suggests the hydrophobic environment around the pyrene molecule. If the pyrene molecules are in the hydrophobic environment, the 3:1 ratio is large value we can observe. And if the pyrene molecule in the hydrophilic environment, like water, the 3:1 ratio should be the small. I have measured the 3:1 ratio of the pyrene fluorescence in the presence of the pH responsive unimolecular micelle plotted as a function of the pH value. At acidic condition, we can observe the large 3:1 ratio. That means the pyrene molecules are in the presence of the hydrophobic environment. That means the pyrene molecules are encapsulated inside of the unimolecular micelle, pH responsive unimolecular micelle. Therefore, the 3:1 ratio is a large value. On the other hand, at acidic condition, that we can observe the low, small 3:1 ratio. That means the pyrene molecules are released to the aqueous phase because the unimolecular micelle is dissociate. Therefore, we can achieve the pH responsive encapsulate and release. Okay, I would like to summarize this section that I have prepared the pH responsive unimolecular micelle. At acidic condition, the micelle structure is very small and the motion of the fatty acid group is restricted. And in the acidic condition, the guest molecule can encapsulate inside of the unimolecular micelle. And basic condition, the size of the unimolecular micelle is large, and the motion of the fatty acid group is very high, and the encapsulated guest molecule can release easily. Okay. Okay. Then I move to the next topic: pH responsive block copolymers. Okay, around 2000, I became a friend with Mr. Mitsukami-san. He is a company person, and he was a PhD candidate student in Morishima Laboratory, and he come to Osaka University only weekend. The weekday he go to the company. The only weekend he come to the Morishima Laboratory, and also the all weekend I go to Morishima laboratory. In 2000, I belong to the Himeji Institute of Technology. However, unfortunately, at that time, I have no equipment, and completely no equipment. Therefore, every weekend I go to the Osaka University. From here, from Himeji to Osaka is about 1 hour by car. Therefore, every weekend I go to the Osaka University to measure GPC and DLS or something. And I met with Mitsukami-san. And before coming to Morishima Lab, Mr. Mitsukami studied raft polymerization in McCormick Laboratory in Southern Mississippi University. And Mitsukami-san studied about the raft polymerization in 2000. Therefore, I meet with Mitsukami-san and I asked to him, please let me know how to perform the raft polymerization. And I have started to study on the raft polymerization around 2001. Okay, this is the chain transfer agent, the raft agent. This agent is very important for the controlled polymerization, controlled radical polymerization of the raft. However, at that time, around 2000, we cannot buy this agent. Of course, now we can buy easily from the supplier. However, at that time, we cannot buy. Therefore, I prepare the chain transfer agent. And the public rumors that the preparation is very dangerous and very bad smell. I think it's not dangerous. However, of course, the smell is very bad. Therefore, around my laboratory, the next laboratory, the professor coming to me, and he complained that your laboratory is always bad smell. However, I prepare the chain transfer agent, of course, inside in the draft chamber.
Prof, sorry, you have 3 minutes left.
Wow, really?
three, yeah, okay.
Okay. Okay, this one is the final products of the block copolymer composed of the pH responsive polymer. The sulfonate group containing block and fatty acid group containing block. This one is prepared by raft polymerization. This one is not random copolymer. This one is a block copolymer. Okay. And okay, I skip. This one is property of this diblock copolymer. At acidic condition, we can observe the very large size because this polymer forms a micelle structure, interpolymer micelle structure. At basic condition, this polymer is dissociated to unimass state. Therefore, we can prepare this type of the pH responsive diblock copolymer. Okay. This is the conclusion of this section. I move to the application, development of sunscreen. Okay, I have introduced to you that this type of the polymer shows a pH responsive property. At acidic condition to neutral condition, this polymer cannot dissolve in water because the carboxylic acid group is hydrophobic. However, at pH 9, this polymer can dissolve in water because this polymer ionizes. It's very easy to dissolve. Please keep in mind this phenomena. And do you know sunscreen? Maybe you know sunscreen. The main component of the sunscreen is the TiO2 nanoparticles like this one. The TiO2 nanoparticle on the skin, the particles absorb the UV light and scattered the UV light. Therefore, the TiO2 nanoparticle shows a good property for the sunscreen. And in 2005, I have requested from the company that please develop the waterproof polymer, which can be removed by water. It's very strange request. Because the company person wants that at that time, that this one is sunscreen. The TiO2, the black part is TiO2. TiO2 particle is covered by the hydrophobic organic compound because the sunscreen should be keep on the skin against the sweat, the pool water, sea water. It should be remain on the skin. However, the customers go back to house and when they will sleep, before that, they want to completely remove these sunscreen. However, the too hydrophobic, these sunscreen. Therefore, it's impossible to remove from the skin. Therefore, they need to use the special agent, the special cleansing agent should be need to remove the old sunscreen. However, if we use the pH responsive polymer on the surface of TiO2, maybe we don't need the special sunscreen. Therefore, this polymer is coated the surface of the TiO2 nanoparticle. This polymer at the neutral condition, the very hydrophobic property. That means waterproof property. The polymer coated the TiO2 nanoparticle can remain on the skin against the sweat and the pool water and sea water. However, at the basic condition, like a soap water, very weak basic condition, the polymer can change the hydrophilic nature. Therefore, it's easy to remove by water. Okay, this is a result of the experiment. This one is a polymer coated TiO2 nanoparticle at pH 6 to 7. The powders completely cannot disperse in water. All powders on the surface of the water because these particles are waterproof because this polymer cannot dissolve in water. However, at pH 9 to 10, this is a weak basic condition, like a soap water. The completely disperse in the aqueous solution because this polymer is changes to the hydrophilic. The polymer coated TiO2 can be wetted by water by acidic condition. Okay, we get the patent these experiments. We prepare the pH responsive sunscreen. This one is very old story, 2006 to 2007. However, it is still used today. The company still use this technique. Okay, this one is a typical example. This one is old sunscreen. This one is washed by water. Of course, the remain on the skin. This one, this picture shows washed by soap water. They also remain the skin. It's not a good situation. However, our new sunscreen, the pH responsive sunscreen, the washed by water, they remain on the skin. However, washed by the soap water, it's very easy to remove. This one is very nice, the sunscreen for the customers. Okay, I move to conclusion. The pH responsive unimolecular micelle, the unimolecular polymer, unimolecular random copolymer, and block copolymers were prepared. And after that, waterproof sunscreen which can be washed off with the soap. Okay, practically useful polymers were designed and prepared using pH responsive units and raft technique. And I want to I want to advertise little bit, the very small time. I'm now a section editor-in-chief of polymer chemistry of polymers. Now the impact factor increase to be 4.329. Please submit your paper to the polymers. And also I'm editorial advisory board of Langmuir. Langmuir is ACS journal. The impact factor is 3.882. If you have the paper related to the surface phenomena, please submit to Langmuir your article. And also now this is very important information. I'm looking for the PhD candidate student who want to work with me in Japan. If you know good candidates who have an interest in polymer chemistry and Japanese culture, please contact to me. This is email address of my email address. Everything I will support, the travel fee and everything I will support. Please contact to me. Okay, I want to appreciate to the many professors and my laboratory members, and this study is financially supported by the Japanese Kakenhi and Shiseido company and Ricoh company. Okay, thank you very much, kind attention. Thank you very much.
Okay, thank you very much, Associate Professor Dr. Shinichi Yusa. So very nice talk and very
Thank you
nice
very
sharing.
much.
So for those who are willing to join Professor, you can contact Professor and to publish in a polymer and also to join research collaboration. So due to our, since we are run out of time, so there's a one question from Ravindra. So can we use this polymer for sodium ion conductor?
Oh, I have not checked.
Okay.
Now I cannot answer the high, but I will try in the future. It's very nice question.
Yeah,
Okay.
maybe you can do some application in the future, Prof.
Yeah.
Okay. So thank you very much, Prof. So
okay, thank you very much.
Okay. So now we go to the next presenter. I would like to invite Dr. Ainur Izzati Kamisan. Okay, he from Malaysia. He is going to present about high output voltage of flexible zinc oxide reduced graphene oxide nano generator. So you can share the slide and start present, Doctor.
All right, thank you. I can share my screen.
I don't know how to stop.
Prof, can you
stop the sharing?
You just click. Just wait, try.
Oh, thank you very much.
Okay, now Dr. Izzati, you can share your slide.
Okay. Oh, sorry, I still can't share my screen.
All right. Okay, can you try to share your screen now?
Yeah. Okay. Okay, can you see my screen?
Yes.
Okay. Okay, thank you very much, Dr. No. And I also like to thank the organizing committee for giving us the opportunity to share our research work today. So my name is Ainur Izzati Kamisan, and I will be presenting today on behalf of Professor Abi Malik Marwan Ali. Due to the unforeseen event, he is not able to give his talk today. So first, I would like to introduce our research group. Here we have Professor Abi Malik Marwan Ali, Professor Oscar Hazrul Hassan, Professor MZ Yahya, my respected supervisor during my PhD study. And also we have Dr. Muhammad Faris Muhammad Taib, and Cik Atikudin, FF Hatta, AF Cik Omar, AS Kamisan, and me, Ainur Izzati. So our group focus on the developing materials with piezoelectric effect we also work on hybrid and nanostructured materials. So we include the effect of additive, plasticizer, and polymer in our research work. So we have the interest on the barium titanate, xenon oxide, graphene, and PVDF polymer for nano-generated application. Okay, let me introduce about the energy harvesting. The energy harvesting is a process that captures small amount of energy from one or more energy sources. And once the energy is captured, it can be accumulated and stored for later use, such as for powering a variety of sensor or even controlling a circuit for a range of application. So why energy harvesting? Because it uses the renewable source and also will allow us for remote charging in various applications. There is abundant energy sources in our environment. So some examples are light, motion, body heat, and also electromagnetic radio frequency. And also from the natural resource like wind, solar, water, human motion, and many others. So perhaps the solar powered energy is the most established method of energy harvesting. So the challenge here is to convert that ambient energy into usable electrical energy to power an application. For example, like when we utilize light from a 100 bulb of light bulb. So it is also interesting to note that a resting human body also dissipates about 100 watts of energy in the form of heat. So all we need to do is harvest that energy to render practical application like body temperature sensor or pulse sensor or some other biosensor that use low power. The first law of thermodynamics stated that energy can be created or destroyed, but it can be converted from one form to another form of energy. So for nanogenerator, it was first introduced by Professor Dr. Zhong Lin Wang in 2006. And they used the zinc oxide nanowire nanogenerator to produce the electric supply. The energy produced from the nanogenerator will be very small, about few nanowatts to several milliwatts, but it is sufficient enough to power a coin cell battery within 1 hour. So there is a case study that has been conducted at KLIA in 2017 by Boon Chong Chu. So the study found that the average energy consumption at KLIA was about 10,000 megawatt hour per month, where it is mostly used for lighting and cooling of the area. So it may not be possible during this pandemic situation, but on a normal basis, there are about 60,000 crowd sites daily for potential energy harvesting from human footsteps. So it is a good idea to implement a smart piezoelectric tile to contribute to the renewable energy, which can be generated and powered by the 22 million passengers per year. So basically there are three types of nanogenerator: piezoelectric nanogenerator PENG, triboelectric nanogenerator tank, and also pyroelectric nanogenerator. The PENG convert the kinetic energy into an electrical energy, while the triboelectric nanogenerator convert the mechanical energy, including friction, separation, the contact, and convert it into electrical energy. While for the pyroelectric nanogenerator, it utilizes the temperature difference between two ends of the device. So there is a large type of piezoelectric material that can be utilized for nanogenerator. The piezoelectric materials have the ability to generate electrical charges when subjected to mechanical pressure. So some of the piezoelectric semiconductor materials with the word Z structure will exhibit both the semiconductor properties and also piezoelectric properties like zinc oxide, gallium nitride, and cadmium sulfide. Polymers, mostly PVDF, is used in the application with that requires lightweight generator design. So for the application of nanogenerator, there is a wide range of application for nanogenerator like self-powered system, wireless sensor network, smart building, electronic skin, hybrid cell, and also many other flexible electronics. Like this hybrid solar panel here, we can harvest the solar energy during a sunny day, and also we can harvest the kinetic energy from the raindrops when there is shower or heavy rain. So of course, there is challenge in every research work. For nanogenerator, the challenge is to increase its output power density and also how to integrate the packaging of energy storage unit with the nanogenerator itself, and also to optimize its harvesting efficiency from various working conditions, and also to optimize the electromechanical efficiency through structural design, and also for long-term stability, temperature drifting, and also the integration of active or self-powered system with the data processing. So back to our research work, the problem statement here is that the voltage output and power output are highly dependent on the surface area of the active materials. And also due to the nature of the ceramic materials, it makes the nanomaterial brittle and vulnerable, so it tends to crack when handling. So the solution is the preparation is crucial to produce a very thin film with high crystallinity. Also here we try to enhance its mechanical and electrical properties with dispersion of graphene. So what motivates us for this research? So our motivation is to optimize the design of architecture to enhance its practical usage. Okay, so this is our motivation in the future work. So it is also what we also like to reduce the dependency on carbon energy source, and also to increase their lifestyle for maybe up to 10,000 cycle. So zinc oxide is a very promising material due to its biocompatibility, high piezoelectric effect, large material abundance, chemical stability, and also it is of fabrication. Most previous work have employed zinc oxide and polymer to form nanogenerator, but also in order to obtain a higher output voltage, the addition of filler materials like carbon nanotube, carbon fibers, reduced graphene oxide RGO, and graphene has been adopted, and they serve as an electrical bridge between the composite material. So in this work, we present a simple processing method to produce flexible zinc oxide reduced graphene oxide RGO nanogenerator with PVDF as binder. So for the preparation of the zinc oxide graphene composite, the production was divided in 2 steps, where the first step we first prepared the graphene oxide using the modified Hammers method, and then followed by the reduction of graphene oxide in glucose solution through ultrasonication to obtain RGO. The composite solution was then prepared by dissolving PVDF in DMF solution until we get a clear homogeneous solution. And later on, we add the zinc oxide and RGO to obtain a heterogeneous solution followed by ultrasonication. So the composite was then will be spin coated on ITO coated PET substrate to obtain a flexible thin film, and the thin film was allowed to dry on the hot plate to confirm the nanocomposite addition onto the PET substrate. And for the nanogenerator testing, the sample was coated with gold as electrode through the sputtering process. Okay, first, the obtained graphene was characterized with Raman spectroscopy, as it is a common instrument to indicate the structural change of graphene before and after reduction. So we can see the appearance of 2D band at 2700, and that indicates the formation of few layer graphene. And the intensity ratio of the D band and G band also found to increase from 0.9 to 1.10 after reduction. And for the TEM image, the presence of few layer graphene can be detected here with its typical ripple silky wave structure. And this wrinkle morphology is due to the high surface energy of freestanding graphene. And for in the SEM image of the xenon oxide and PVDF, it shows the relatively hexagonal shape of the xenon oxide due to its word-side structure that adheres to its piezo property of xenon oxide. In the FISEM of xenon oxide and RGO, the presence of graphene, however, is not clearly visible, and this could be due to the fact that the amount of RGO is very limited in the composite. But however, the presence of RGO can be confirmed through the SRD pattern here. So for the SRD pattern of xenon oxide, it shows the hexagonal structure. For the xenon oxide PVDF, no obvious peak corresponding to PVDF can be seen, but all the xenon oxide peak shifted and reduced in intensity, that gives shows the interaction with the PVDF. And for the xenon oxide graphene, the strong peak at 100 plane corresponding to the hexagonal carbon of RGO can be observed, and thus confirm the presence of RGO in the composite. So here the graph shows the current voltage characteristic of nano composite with different PVDF concentration. We have 3%, 5%, and 10%. As can be seen, the graph shows a symmetrical and linear nature of IV curves that suggests that all the materials have an ohmic contact, where it can allow charge to flow easily. And it can be seen that the current increase as the concentration of PVDF increase. However, due to the fact that PVDF is also a piezoelectric material, we limit its concentration to about 10% to avoid it from interfering with the nanogenerator performance. As in this study, we only use PVDF to serve as a binder to avoid the sample for cracking. And for the energy harvesting capability of the sample, we measured it without applying the electrical polling. And this is the schematic of our nanogenerator device. The composite was sandwiched between ITO and gold, and the two end contact of the nanogenerator were connected to a source meter to measure the output voltage. A hammer with float was used to knock the surface of the flexible nanogenerator equally. So we use a frequency of 1 Hertz as it imitates a person tapping their heels on the floor. So this applied pressure is expected to distribute over the whole surface of a nanogenerator and be transferred to electrical output. Okay, the figure here shows the output voltage produced by the nanogenerator before and after the addition of RGO. As can be seen, the positive and negative peaks of the generated voltage vary due to the pressing and releasing of the nanogenerator. When a heavy object is in contact with the nanogenerator, An impact force is applied on the surface, and that causes the material in the composite to generate piezoelectric potential due to the compressive strain. And this potential will drive the free electron within the composite to flow through and accumulate at the interface to balance the piezo potential. So when the load is moved and the pressure is released, the accumulated electrons will flow back. And so in each period, we observe the positive and negative voltage signal. So for the zinc oxide with 5% PVDF, the nanogenerator generates maximum output voltage ranging from 2 volt to 8.5 volt, while the zinc oxide with 10% PVDF generate maximum voltage from 3.3 around 3.5 volt to 9 volt. So by applying the same load force, we found that the maximum output voltage increased by twofold after the addition of 1% RGO in the composite. As for zinc oxide and RGO with 10% PVDF, it generates about 30 volt of peak-to-peak voltage output. And this behavior shows that RGO had a positive effect in forming the conduction network and effectively reduce the internal resistance of the nanocomposite. So as a conclusion, the piezoelectric nanogenerator can be enhanced with other material, and that can lead to better high energy output. Also from our study, it was concluded that the presence of graphene, even in a very small quantity, had greatly enhanced the nanogenerator performance. And the self-power nanogenerator could be a new changer to alternative way of harvesting energy. So this is our test at our lab where we use finger tapping mode or flexible nanogenerator. Even with finger tapping mode, the nanogenerator exhibit about up to 120 millivolt. And we also try to embed the nanocomposite to show insole, and it can be used as a sensor. So with that, I would like to acknowledge the Ministry of Science, Technology and Innovation Malaysia for the International Collaboration Fund granted for this research work, and also for Ministry of Higher Education and University Technology Mara. With that, thank you.
All right, thank you very much, Dr. Ainur. Do we have any question from the audience? All right, so we have one from Dr. Jun. What is the role of graphene in nanogenerator?
So actually it acts as a filler. So it serves as the electrical bridge. So to conduct, to connect the electron within the nanogenerator. So we can see from that the output voltage improve after the addition of RGO.
Okay, all right. Thank you very much for the excellent presentation, Dr. Ainur. So now we move to the next presenter, Dr. Sergey Sevilov from Russia. So he will present. He will share about the future of carbon-based 2D nanostructure. So, Dr. Sergey, can share your slide?
One moment, I'm here. Okay, I will try to show. Okay. Okay, do you see my slide?
Yes, very clear.
Okay, dear colleagues, thank you very much. Thank you very much, Professor Singh, for your kind invitation to participate in this conference in this so difficult time for all over the world deals with the pandemic of coronavirus. And I hope that we will overcome this problem and rather soon we can meet normally and perform the conference, how to say, in the normal format. So my presentation deals with carbon-based 2D nanostructures, and I'm from Moscow State University. Moscow State University, you can see the picture on the top. It's one of the oldest and the biggest university in Russia and in former Soviet Union. It's located in Moscow, in the heart of Moscow. We have two campuses, one just behind the Moscow Kremlin and another one here on the Leninsky Hills. Where am I? It's just 10 kilometers from the city center. So carbon nanomaterials are widely used in different spheres of industry. And year by year, the annual production demonstrates a continuous growth. Most of them are used as a fillers in the plastic and composites. It's about 70% of the total amount. Another one used about 10% in electronic devices. About 8% are used for energy storage and harvesting, and about 13% for some other applications. If we view to the past, it's important to mention that in spite of the first carbon nanotubes was described precisely by Suomi Ujima in 1991. Nevertheless, for the first time, it was mentioned about 40 years in advance in the work of the Soviet scientists Radushkevich and Lukyanovich, which was published in Russian Journal of Physical Chemistry in 1952. And this work was devoted to the geometrically anisotropic carbon forms, which have a hollow channel inside. But unfortunately, since in that time, the transmission electron microscopy was not so powerful as now and as 30 years ago. So that's why the scientists were not able to characterize in details these carbon nanotubes. And this work was performed by Suomi Ujima 40 years later. So if we speak about carbon nanostructure, it's important to mention that it can be found in nature as well. So in the composition of ingenious rocks, in oil crude, in Greenland ice cores. So everywhere where the high pressure and high temperature meet together. In this case, especially under the presence of the transition metals like iron, cobalt, nickel, which are widely used in nature. So all these cases lead to formation of carbon nanotubes and even graphene materials. They were also found in planetary nebula and everywhere in industry, especially in the product of pyrolysis. And just to mention that graphite whiskers are well known and were characterized in 1957. So the other carbon forms can be also found in nature. So this is example of the diamond places where the diamond can be found in Soviet Union and in South African Republic. And for diamond synthesis, the high pressure and high temperature without any catalyst also are needed. When speaking about carbon nanomaterials, we can split it on structured and amorphous ones. So to amorphous ones, we can refer to coals and carbon black, and we will not pay big attention during this talk. And structured carbon nanomaterials can demonstrate all the types of hybridization of the carbon. So it can be sp3, sp2, and even sp1, but it's also a material. And sp2 carbon nanostructure can demonstrate different dimensions of the carbon forms. So it can be 0D, like carbon quantum dots or polymers. It could be 1D, like carbon nanotubes, graphite whiskers, and So it can be 2D like a graphene and few layers graphenes, and graphite, which is a 3D. So 1D, so the sp one carbon hybridization can be referred to carbon chains. So we will focus on 2D carbon nanostructure, and it's in the middle of the picture. It's graphenes of few-layer graphene. Since one-layer graphene is very exotic and it cannot be synthesized in big amounts, so normally the material we obtain consists of few layers, of few graphene layers. And to this type of the compounds, we can refer the so-called Maxen phases. Maxen phases are the can be derived from the metal carbides, like titanium, vanadium carbides. It can be synthesized by removing aluminum from so-called Max phases. So it's mixed carbides of intermetallites. And when the easily removed metal like aluminum is washed from there, so we can get the layered structure of the metal carbides, and the interlayer distances are so high that some inorganic and even organic ions can go inside. That is why they are very promising for energy storage devices. So going back to the pure carbon 2D nanostructures, so we proposed the method of the synthesis. So it's a universal technique which allow us to get, almost all the types of carbon nanomaterials. So it's a simple pyrolytic technique. So we use a tube furnace, the internal heater inside. Then we put the gases, and we make the aerosol or direct injection of the hydrocarbon inside the furnace. And then we collect the exhaust gases. And due to this, in the presence of the catalysts, we can get the 1D structures like carbon nanotubes or carbon nanofibers or conic nanotubes. So if we do not use the catalyst and use just a metal oxide, in this case, we got the graphene derivatives like 3, 4, 5 layers, few layer graphenes. When we use some adducts to hydrocarbons, we can get the heterostructures where some carbon atom inside the graphene layers are substituted by the nitrogen, silicon, or boron. And if we use the metal forms, so we can get the carbon forms. And all the substances can be get within one experimental device. So when washed, we can get the carbon dots. So here you can see the high resolution TM images of them. And after further treatment, for example, with spark plasma sintering, under the presence of the metal or without them, so we can get the compacted structure, and we can switch from 1D or 2D to 3D materials for so-called carbon nanotubes frameworks, decorated or non-decorated by metal oxides or metals. And it's very promising material for catalysis, electromagnetic shielding, and magnetic separations. The carbon nanotubes, and as I told in advance, can be used in different types of the composites with metals and alloys, polymers. It also can be used in electrode materials for lithium-ion batteries, ion ethers, or supercapacitance, and as well as for catalysts and absorbents and lubricants. But when used in these spheres, it's demonstrate a few problems. First of all, it's a high porosity and different types of pores. It's not very bad for energy storage devices because they consume a lot of electrolytes. And when we calculate the energy and capacitance characteristics of them, we should refer to the mass of the whole device. And if they absorb a lot of electrolyte, in this case, these characteristics will not be rather high. So another is the low density. So that's why it's very difficult to work with them. The type and amount of functional groups sometimes is a problem, sometimes it's a good. So if you would like to provide the fast and effective interaction within the polymer matrix, it's good. But if you want to use carbon nanomaterials in energy storage, especially with non-aqueous media, and especially in with high voltage electrolytes, more than 2 volts, in this case is bad, because when we use a potential, so this functional groups eliminates from the carbon material. They provide the gases inside the cell, and they provoke the decomposition of the electrolyte that reduce the characteristics. Another weak point is low electrical resistance, weak contact with matrix and composites. It's not consolidated power. And if we use if we speak about the distribution different type of matrices, the distribution is normally inhomogeneous. In order to make it more regular, we need to introduce the functional groups. It's important to mention that normally functional groups appears on the surface of the carbon nanomaterial, as well as they are affected by atmosphere just after the synthesis. And it's very difficult to eliminate about them. So all the carbon nanomaterials are normally after synthesis are functionalized. If we speak about the functionalization, we need to mention two main types. One type is a covalent functionalization, where the carboxyl, hydroxyl, or other organic groups are connected with a tube or graphene fragment by covalent bonding. And another one is a non-covalent modification due to van der Waals and other types of the contacts. Depending on the structure of nanotubes or graphene fragments, mostly carboxyl groups are normally formed on the surface. In the case of the cylindrical nanotubes, they normally form on the tops of the tubes and in the places of defects. When we speak about the conic carbon nanotubes, they normally cover all the surface, of the tubes. And in case of graphene fragments, they are normally at the edges, and a rather big amount of these groups, they provide the geometrical exchange of the planar structure of the graphene fragments, so that I described of the previous pictures. In order to determine the type and amount of the groups, we can use NMR, elemental analysis, and thermal analysis in order to determine the total amount of the all functional fragments, while the thermometry, TM, and the XPS show us only the surface groups. We can introduce more groups on the surface of graphene fragments and nanotubes due to their ozonation, but we need to be very careful, because the ozonides can form on the surface, and this material can be rather dangerous. But when we have a big amount of the functional fragments, that allow us to introduce the graphene fragments and carbon nanotubes for the reactions typical for the organic compounds. So that's why the functional groups on the surface of nanomaterials, they provide their quasi-molecular nature. So at the same time, the carbon nanostructure is a material. And from the another viewpoint, all of them are like molecules, which can be introduced in the reaction typical for organic compounds. So this is a table which demonstrates how different characterization technique can be applied to carbon nanotubes, and this is just a technique which can show us where exactly the functional fragments can be placed in the nanotubes. So if we modificate the carboxylated or even decarboxylated nanotubes by thulium salts in non-aqueous medium dry acetonitrile. In this case, the rather stable complex compound with thulium can be formed inside with carbon nanostructure. And normally thulium coordinate up to 12 atoms of the oxygen, and due to this, the complex is rather stable. And we can then see the location of the thulium atom, which is rather heavy, by transmission electron microscopy. So here you see the pictures of cylindrical nanotubes, and you see the thulium atoms on the tops and in the place of the defect. It's in that contrast inside the TM column. In case of, yes, it's also the cylindrical decarboxylated nanotubes on the few atoms left after decarboxylation, which can be performed by thermal treatment in the vacuum atmosphere. So the rest of the oxygen is about less than half percent. In case of the conical nanotubes, we see the thulium atoms almost everywhere on the surface. And after decarboxylation, so some oxygen groups left. When we speak about thermodynamics of the carbon nanostructure, two important questions can be taken in mind. First of all, we can understand that we speak with small systems. To this problem, Professor Terence Hill from US devoted his first monograph at 1963, Thermodynamics of the Small Systems. And then he returned to this problem almost 40 years later. So he wrote that we need to introduce some additional components inside the energy formulas describing this carbon nanostructure in order to reflect the impact of the surface. And experimentally, we can measure these characteristics by differential scanning calorimetry and bomb calorimetry. But there are some differences in this technique. First of all, is the sample mass. So the DSK is a sample mass of few milligrams. And the results we obtained by this technique can be influenced by many reasons, by many circumstances. And we can also influence by some impurities. So when we speak about the bomb calorimetry, in this case, the mass of the sample could be 1, 2, 3 grams. And of course, the average characteristics will be more precise. And we cannot put much attention to the subspecies and to the impurities. And another important problem, to which value the energy characteristics need to be referred to. So is it could be referred to the gram or to the mole? So if we speak about the mole, we must to speak about the substance. But carbon nanomaterials, they are materials, not a substance. One particle differs from another particle. But if we refer to the gram of the material, in this case, it would be very difficult to calculate, to compare the values for different type of materials. But there is a simple solution. We can use the elemental analysis, so CHNO analysis, to fix all the organic components. And in this case, we can calculate the average molecular mass of our substance by introducing not only the carbon, but hydrogen, oxygen, nitrogen, and even the sulfur if exists. In this case, we will get the value rather close to 12 gram per mole. But nevertheless, it should be a little bit less or a little bit more. And in this case, we can switch from the gram to the mole. And we can compare the data for the different type of nanotubes. But if we look over this table, even in the work performed in our laboratory, we see that the values we got for different type of nanomaterials are differ. And let's see why this difference take place. So on the left side of the slide, the standard Born-Haber cycle is demonstrated. It's typical for ionic crystals. But if we speak about carbon nanomaterials, we have the simple atomic lattice. So we have only three positions of the energy cycle. This is a graphite, so-called zero. This is a carbon as atomic gas. So all the allotropic modification of the carbon should be higher than zero, higher than graphite. But if we introduce the functional groups on the surface, and as I told in advance, they normally exist after the synthesis. So the nitrogen, oxygen, and hydrogen, in this case, the position we measure by calorimetry or by differential scanning calorimetry is below zero. So this is the influence of the functional fragments. This is a technique of the thermodynamic calculations we use. It's rather standard, and I will not focus on them. Here we see that the standard enthalpy of formation normally depend on the diameter of the nanotubes. So for the multi-walled carbon nanotubes, for the small nanotubes, the standard enthalpy of formation is rather small. But if we increase the diameter and switch to the chiral nanofibers, we see that almost 1 order of the magnitude, we see the difference in energy on the formation. Another important point is the defectiveness. So here you see the Raman spectra of the carbon nanotubes from which we can estimate the amount of the defects. And here you see that the defects which are reflected by the ratio of the Raman band D to G and G dot to G, we see that they influence on the enthalpy of formation as well. So if we summarize all the data for carbon nanostructure, we see that normally nanotubes, nanofibers have the positive enthalpies of formation, as well as the fullerenes. For graphite, it's zero. If you speak about the carbon form, so it's very close to graphite and a little bit below zero. But the 2D compounds, like carbon nanoflakes, due to the high amount of the functional fragments, all of them are rather below zero. So they assumed to be, their formation assumed to be energetically preferable. But it's only the impact on the functional fragments. If we will see and trace the functional groups elimination during the heating, we see this picture, so they will be more and more ordered, and this carbon nanoflakes energy enthalpy of formation will switch to the graphite when heating, according to this picture. We can also speak about the heterosubstitution. For this is example for the nitrogen introduction inside the graphene layers, and it's also will influence on the energy characteristics. The few types of nitrogen can be found in the XPS spectra of carbon nanostructure, but it's only the main. Some others can be found. The introduction of nitrogen, since influence on the enthalpies of formation, can also influence on the thermal degradation of nanotubes and nanoflakes, as it's shown on the picture. So in order to get the consolidated structure and switch from 1D and 2D to 3D nanostructure, the spark plasma sintering can be used. Spark plasma sintering is rather universal technique well known for metals and metal oxides, but nevertheless it's possible to apply them to carbon nanostructure. And due to this technique, we can vary the porosity of the carbon nanostructure. Here you see that during the spark plasma sintering, the micropores going out, while the meso and micropores appears, and we can get the density up to 1.7 grams per cubic centimeters, which is
sorry to interrupt, Doctor. You have 2 minutes left.
Yes. Okay. And also 3D frameworks can form during spark plasma sintering. Here you see that it's transformation of the cross CNTs and they're linking together. So this is the application, and I would say let's be healthy during this difficult situation. Thank you very much for attention, and I believe some time for the question left.
Thank you very much, Dr. Sergey. Very nice talk today. So they have one question. Can we remove the unwanted functional group from the CNM? Can you suggest some methods?
Actually, we can do it. So it's very difficult to remove all the functional groups from the carbon nanomaterials, but nevertheless it can be done. So the first and rather simple technique is annealing at the temperatures over 350 degrees in the vacuum. But nevertheless, and as I shown in my presentation, we cannot remove all the functional fragments, but we can remove majority of them. Another possibility is use the spark plasma sintering. Since the spark plasma sintering allow us to reach the temperature higher than graphitization, so it's about 2000 degrees, but it's not a simple heating, it's heating by electrical pulses. So it's for very, very short time. So, and also the impact wave goes together with the heating. So this spark plasma sintering in inert atmosphere allow us to eliminate almost all the functional fragments. And if we transfer the carbon materials to the glove box, we can use it in energy storage devices without any problems. And the third point is electrochemical elimination of the functional fragments. So we can use a compacted electrode from the carbon nanomaterials. We can put it in non-aqueous electrolyte like acetonitrile with some organic salt or to ionic liquid and apply the potential over than 3 volts. In this case, all the functional fragments will eliminate and you will get the pure carbon material inside the non-aqueous electrolyte directly.
All right, thank you very much, Dr. Sergey. Okay, so thank you. I would like to invite the next presenter to share with us. So the next is Professor O.P. Shinha from India. So her topic is about reduce graphene oxide, zinc oxide based nanocomposite as electrode materials for high performance supercapacitor. So
thank you. Thank you.
You can share the slide.
And I'm audible to all of you?
Yes, we can hear you, Prof. Yeah. You can share your slide. Okay, Prof.
Yeah, now it's fine.
Yes, we can see it.
Thank you very much. I am really thankful to the organizing committee who has given this opportunity, especially Dr. P.K. Singh and R.C. Singh ji, to providing this opportunity to share our work over here. This is the work of one of my PhD student who has submitted the thesis and going to defend her final viva on Friday, Swati Chaudhary. And this nanocomposite based high performance electrode material for the supercapacitor applications. So the moment we are talking about the supercapacitor, basically we are looking forward for the energy storage system. So the moment we look for the need of energy storage system, it required for speedy advancement in industrialization and urbanization, deterioration global effects such as the greenhouse effect and the global warming, increasing human population, exaggerated demand for the energy, and how it can be take care. It can be come from your mechanical energy, can be the chemical energy, can be the electrochemical energy, it can be the electrical energy. So until now, fossil fuels such as the coal and the petroleum are the primary used for meeting the energy requirement of the society. However, with the restricted fossil fuels reserve, there is a necessity of developing alternate energy storage system, which has been given over here in terms of the 4 different ways. So the type of energy storage system which is available nowadays is the battery, capacitor, and the supercapacitors, and their value in terms of the energy density, power density, charging time, discharging time, cyclic life, and energy storage determinations has been quoted over here. And you can see in terms of the power density, although the capacitors are there, but in terms of the energy density, you can see the supercapacitor is better compared to that. So value has been given for the different one. And that's what the people are nowadays working with, the super capacitor, or you can call it as the ultra capacitor. So before I start, from where this capacitor came, I would like to, especially for the young researcher, the London jar was basically the first which is given the concept of the super capacitor. In totality, the phenomena of the rubbing amber with the cloth was found to attack a small particle. Many of us has played this game during our childhood, when we were putting the comb in our hair and then putting the pieces of the on the pieces of the paper, and then the electrostatic charge are there. So this storage came in that manner. So in 1745, this unexplained phenomena was used to develop the first known capacitor by Edward Goldwyn Kelest. And in the same year, in 1945, Peter von Moechinger invented the Linder jar, which is known first first capacitor of the world. And then Ben Franklin soon found out a flat piece of the glass can be used in place of the jar model. Then the development take place, energy stored in the field between the two, so energy stored in the electrical field between the two conducting plate, charges and the discharges quickly, long life, very low cycling losses, capacitance limited by the flat surface potential area and the dielectric property that is given by the equation C is equal to nothing, epsilon R epsilon naught A by D, and what the notations have its usual value. C is for the capacitance, A is for the area, and ER is for the relative static permittivity, that is the dielectric constant, and E naught is the permittivity of the free space, which we all know from the science background. So history of supercapacitor start from the electric double layer capacitor. Effect was noticed in 1957 by General Electric in 1957. 1966, Standard Oil of the Ohio rediscovered this effect in 1966, and Standard Oil of the Ohio gave the license to NEC, which in 1978 marketed the product supercapacitor. So from 1978, we have the supercapacitor in the market. So supercapacitors are basically different, whether you call them supercapacitor, ultra capacitor, or you can the electrically double charge, double layer capacitor cap. These devices have maximum capacity well in the 1000 of Faraday. No dielectric supercapacitor are based upon the carbon technology, which create a very large double layer surface area as thin as molecules with an extremely small separation between the layers. And that's what basically we have taken this work. When an electric charge is applied to the carbon material, a double electric field is generated, which acts like a giant dielectric. And while individual supercapacitor can have very high capacitance, maximum voltage rating are low. So advantage supercapacitor, it has the specific energy and the specific power, the total amount of the energy and the energy stored devices. A battery has the higher specific energy and can run for the much longer. But the moment we talk about the ultra capacitor, the speed at which the power can be discharged have the far higher specific capacity, meaning they can be provided a higher current. So depending upon you are looking for the time duration, you are looking for the power, you need to choose, you have to go for battery or you have to go for the capacitor. So bridge the gap between the battery and the capacitor, as it offer higher power density than battery and higher energy density than capacitor, offer high capacitance and long discharging discharging stability in the wide thermal operating range. So you can have the temperature range very wide, easy to handle, lightweight, flexible, and environmental friendly. Emerge as a power solution to application where higher power bursts are needed for shorter duration, like a hybrid electric vehicle, elevators, aeroplanes, frog trucks, and overhead cranes. And further, it is high power density and the fast charging discharging cycle make it liable for application requiring high power output, such as in computer chips, sensitive mechanizations, and the conveyable electrical devices. So just to give another example, supercapacitor, more than a capacitor, different than the battery, you can see over here. So use with or as an alternative to the battery, not as a volumetric efficient and more expensive than the battery, but have the advantage in a specific application, costs are coming down. Can be very quickly charge discharge as many thousands of the times, used in the application where short bursts of the energy are required. Just like if you see the anybody which is going for the 100-meter race, or you're going for the marathon, so those who are going for 100 meter, they require the burst, while those who are going for marathon, they require the more energy. And that's what the two example I have taken, the supercapacitor and the battery. So capacitance from 1 Farad to 100 of Farad, or even the 1000, and the volume range can vary 2.3 to 2.7 for a single cell. The voltage range can vary from 2.3 to 2.7 volt for a single cell package. So again, these are the something which basically come in the market. So I'm not going in detail because I don't want to extend between your lunch and my presentation. So I will try to finish quickly. So different style design ultra capacitor, flat style used for mobile component, typical button capacitor for PCB mounting, memory backup, and the radial style capacitor for PCB mounting in the industrial application. So they are, you must have seen such kind of the capacitor in the market, such kind of those things. So depending upon the use, we have the market has come with the different kind of these capacitors, and these are the basically the market value US dollar in billion. In 2002 it was 0.6 billion, but in 2025 it is expected to touch 3.5 billion US dollar in terms of the super capacitor markets. And the product type, models, and industry has been given over here. Double layer, it has the less than 25 volts. It can be used in the transportation, pseudo capacitors, hybrid capacitor. The volume, the module will be 25 to 100 volts. Industry, above 100 volts, consumer electronics, energy, and other applications. And the major player in the super capacitors are the Maxwell, Cap, XX, Panasonic, Nescap, and AVX. So supercapacitor can be divided depending upon their performance or their category. It can be the double layer capacitor, it can be the pseudo capacitors, and in that we have the different charge storage electrostatically, and that will be basically Holmes layer. If you go for the pseudo capacitor, they are electrochemically Faradic charge transfer. Here you can use the activated carbon, carbon aerogels, carbon nanotubes, CNT, graphene, carbide divide carbon, CDC. Here you can use the conducting polymers or the metal oxide. And when we mix together both double layer capacitor and pseudo capacitor, it basically gives you the hybrid capacitor. That's a asymmetric electrode, charge stored electrostatically and electrochemically both. And here you can take in terms of the asymmetric pseudo or the electrically double layer charge capacitance, then it can be the composite. And the moment you go for that, it may be coming in terms of the rechargeable battery type. So that's what basically in the more detail, both mechanism, both have the different mechanism. ELDC, which are primarily composed of the carbon aqueous material, statically deposit charge within the porous structure of the electrode, while you go for the pseudocapacitors, which consist of the transitional metal oxide, nitride, and conducting polymer, such as the electrode accumulate energy through fast reversible electrochemical redox reaction on the active surface of the electron. And that's what the Regon plot itself say, that which kind of the material you are looking for, or what is the basically best suited for you. So both mechanism have the common qualification for selecting appropriate material for electrodes, which include the flowing. It must have the large surface area and the porosity, good surface evitability, high electrical conductivity, long cycle stability, greater than 10 to the power 5 cycles, facile manufacturing of the morphology, that is the pore size, pore distribution, particle dimension, or the distribution, and the thermodynamically stable for the wide operational potential range. So based upon that, you can take the electrochemical supercapacitor, capacitance, and the first starting cyclic stability, and then we look for such kind of property of electrode material. It should be the low cost, low scale production, and the hazard synthesis process. And then we have taken the work on synthesis of carbon-based nanocomposite as electrode materials. So which are basically low cost, scalable, and environmental friendly, and they have the high capacitance, high cyclic stability. So for electrode material for supercapacitor, it can be the stage 1, stage 2, stage 3, and different material utilizing double layer capacitance, material utilizing pseudo capacitance, composite that combine double layer, and the pseudo capacitance is here: carbon fiber, carbon aerogel, activated carbon, carbon nanotubes. And the moment we're talking about the pseudo capacitance, it will be metal oxide, conducting polymers. And if you mix together, it can be the various carbon material and metal oxide, various carbon and metal oxide conducting polymers can be the choice of the selection. So why we have taken this zinc oxide or the carbon material? I am not discussing this polymer PANI and PYY. So the zinc oxide, because it's easy for synthesis, economical, high redox potential, high electronic conductivity, high chemical and electrochemical stability. And why carbon materials? Because large surface area, porous structures, easy for electrolyte stability, thermal and electrochemical stability, environmental friendly. So here we are going to discuss about the RGO and metal oxide based nanocomposite for super application. And then again we have added another metal, that is the copper nanoparticle based of nanocomposite for your supercapacitor application. And both they are the one-step thermal reaction, or you can say the one-pot synthesis process. And then we use the stainless steel file, and then we put a certain electrolyte, and then we have synthesized these nanomaterials, or the material for the supercapacitor applications. So this is the first result, which you can see over here, RGO and zinc oxide. So these are the synthesis process, and we have taken the 4 different nanocomposite of the RGO and the zinc oxide, where the molar concentration vary from 1:2, 1:1, 1:0.75, 1:0.5. So basically we started from 0.5 to 2 by varying the different molar concentration during the synthesis process itself. So we characterize this nanomaterial with the XRD, and this 00, just a minute. This peak at the 002 belongs to the RGO, and rest all peaks belong to the zinc oxide. So this indicate that the nanocomposite formation take place where the zinc contents are there, and the RGO peaks are also available. Then we go for the this STM and the SEM and the TM analysis. So A to C belong to the SEM images of the RZ2 nanocomposite at different magnifications, and they say that the figure A is the analogy for the interaction, while B and C is the basically intercalation of the zinc oxide and the RGO take place. So you can see difference between the image 1 A and the image B and C. Again, we go for the high resolution transmission electron microscopy, and you can see this again indicate that in this nanocomposite we have the RGO, which we can see over here. The D is given 0.23 nanometers, and the zinc oxide existing in this system, along with the zinc oxide nanorods, which you can see over in this picture, and their RGO existing are there. We also perform the SAT pattern, and this indicate that mobile fringes pattern indicate that the both RGO and the zinc oxide available in the this nanocomposites, and which is again confirmed with the EDAX, which clearly say that the zinc and the this RGO or the carbon contents, carbon and the oxygen contents are there. So this indicate that the nanocomposite formation has take place by the one step synthesis process. And then we go for the CV curve, CV and the DCT analysis and the ES analysis of the your this for the supercapacitor applications. And again, the 1:2 give the high, more this rectangular behavior, and that indicate that ELDC and the pseudo capacitance are there. But the moment we go for RZN1, this is high current due to the high zinc content. If you take the ZN2, and basically in the RZN1, it also has a high redox tendency due to presence of the zinc oxide. If you take the B, if you take the this combined, again the discharge rate for the RZN1 is the higher, and that is due to the high discharge response of the RGO, so high value of the pseudo capacitance present in this one. If you take the EIS, again this EIS state that the highest performance with the lowest value of the resistance for the your system, and this system has been studied for their stability, and you can see in they are more or less very stable even up to the 700 long charging discharging cycle. So calculated capacitance, energy density, and the power density of nanocomposite has been tabulated over here. So you can see, and with the increasing zinc oxide molar ratio content from 0.5 m to 2 m, the corresponding capacitance increases from RZN04 to RZN1 composite respectively. And this can be ascribed to the high rate of potential of zinc oxide to undergoes Faradic reactions, and both the this pseudo rectangular shape CV curve and asymmetric shape GCD curve also indicate the dominance of the pseudo capacitance mechanism along with the electrical double EDLC mechanism. So further incorporation of the pseudo capacitance zinc oxide along with the conductive support of the RGO result in achievement of the high capacitance for the prepared RZNO hybrid nanocomposite. The second work which we have taken, that is based upon the RGO metal oxide, and the metal we have added the copper, a certain percent of the copper in that one. So initially GO was prepared by the modified Huber method, then sodium hydroxide solution was added dropwise in the GO solution, and then 100 ml solution of copper acetate and zinc acetate solution respectively were also added dropwise, following by the addition for 5 ml hydrogen hydrate and reflux for overnight at the 90 degree. This is the synthesis process which we have taken place. So again, this clearly indicate that if you take the green color indicate the presence of the copper, that 111, 200, and 220 indicate the copper presence. The black color, the black one is basically represented presence of the your zinc oxide, and the RGO basically lead to the your red one. So again, the XRD confirmed that the incorporation of the copper is existing in the nanocomposites, and based upon that we have go for the further study. And also we have performed the FTIR spectra for this RZNO copper nanocomposite, and the respective functional group stretching has been observed for OS, CS, C plus C double bond C, and the COH, which you can say we have given over here. So this again indicate that the composite mixing or the functionalization of the nanomaterial, functionalization of the nanocomposite take place. So we perform the SEM images of this images, and you can see some flower-like structure has been observed over here. So, and when we go for the TM images of this GO and the zinc oxide, copper, RGO, zinc oxide, copper structure, you can clearly say a spherical copper nanoparticle are present in this composites, having the particle size of around 200 nanometers. And those who are non-spherical, they are basically the zinc oxide nanorods, and which can vary from 100 to 250 nanometers. So we have confirmed again with the TM and the ICSEM that nanocomposite formation take place in the proper manner. So we observed the CB in the similar pattern as earlier studies for the different concentrations, and again the GCD also showing. So this indicate that the zinc oxide is a higher, more stable system will be. And here we got the more stability. The stability go up to the 3000 long charging discharging cycle. And that indicate that if you add the little bit of the metallic part in your nanocomposites, they give the more stability. Earlier was on the 700, here we got the stability with the around 3000 charging and discharging cycle. So these are the again tabulated whatever we have taken with the increasing zinc oxide molar ratio content from 1 molar to 3 molar, the corresponding capacitance increases from RZNOC1 to RZNOC3, which you can clearly see over here, charging discharging time and the power density which we have achieved. This can be ascribed to dominance of the pseudo-capacitant again mechanism offered by the zinc oxide nanorods, due to its high redox activity, and further the incorporation of the conducting copper nanoparticle also added to this effect. So homogeneous distribution of the both zinc oxide nanorods and copper nanoparticle as visible in the TM spectra over the RGO sheets resulted in preparation of the OH electrolyte ion, that is from KOH, which provide the short ion diffusion and the electron transportation path. And this give rise to the high performance of the RZNO-CO2 nanocomposite as electrode material for supercapacitors. So both the pseudo rectangular shape CB curve and the symmetric shape GCD curve also indicate the dominance of pseudo-capacitant mechanism in this system also with the ELDC. The last one which we have taken with the carbon quantum dots, so that again it has been synthesized with those materials, and you can clearly see the 3 nanocomposite with the RZQ quantum dot, QD basically for quantum dot 300, 400. This is our sample name here given. We have the reduced graphene oxide, we have the zinc oxide, we have taken the carbon quantum dots, and then we go in the one part synthesis process, and then we are getting the RZQD nanocomposites. So these are the basically none other than the images which you can clearly see. TM, the whatever the dark color you are getting, they belong to the zinc oxide, and whatever the gray color you are getting, they belong to the carbon quantum dots. So with the different magnification, you can see from here. I will show you in the TM much better way. So this black one is basically for the zinc oxide, and the gray one is basically for your carbon quantum dots. You can see over here, and we have taken the SAT pattern, which indicate different fringes or different pattern indicating the crystalline nature of these materials with the different lattice parameters. So based upon that, what we observed that the zinc oxide are basically single crystallite in the nature, and they are giving a very good polycrystalline differences between this structure. And then if you go for the E, F, and G, we also perform the EDS images of this one nanocomposite, which give the elemental mapping of zinc carbon in the this sample. Again, the XRD is showing the similar thing. XRD and the FEI are presence of the different component which is we have given over here. And you can clearly observe the different peaks related to your RGO or related to your zinc oxide and the also and this carbon. So we also go for the Raman spectroscopy, and the Raman spectroscopy show the 2 defect peak D and G band, and the high stability, this correspond to the high stability of nanocomposites, and the RGO had the high defect value, that is we calculated from these things, which is ID by IG value is 1.15, while if you take the earlier one, it was only 0.94. So one is with your quantum dots, you can see the defect state has been reduced from 1.15 to 0.94. So it indicate that your system becoming better in terms of the defect passivation. The moment we go for the EV visible spectroscopy, again we are getting the two peak at the 208 and 283 nanometers, and this indicate that this is a pi-pi transition between C double bond transition. While if you take the 283 peak, they are the transition containing hydrogen atoms, and that is there. Similarly, if you take the PL spectra, we are getting the peak at the 400 meter related to the blue source is the blue laser, and peak has been observed at the 59. So again, it is giving the information about how your nanocomposite is there and how the system works. Similar way, we also perform the XPS study to find out what basically we have the zinc, or we have the carbon or the nitrogen. So this again, given this, we also perform the sex spectra. I cannot go in the that much depth, but this confirms the presence of our system, this for the oxygen or the carbon or the zinc in the system or the nitrogen one system. We have already published this paper. Those who have interested, they can go through that and get all the explanation.
Sorry, Prof, you have 2 minutes left.
I'm just, I think 1 or 2 slides more. Okay. So same thing, we have with the combined CV curves, we are getting all these studies. And here, when we go for the stability studies, this stability studies give somewhere around 500 times number of the cycles. Sorry, 800 times. And again, it's showing they are quite stable of the charging and the discharging process. So we have made this, 900 times. We make one prototype also, and you can see over here, the LED is burning, is already glowing using this supercapacitor, which we have made. And based upon that, we have done. And when we increase it, we also go for the improvement. We give some annealing also, and after annealing, we are getting the better performance of your devices. So this is the basically summary. With the increasing annealing temperature of the zinc oxide with the 300 to 400 degrees C, the corresponding capacitance increases from the sample number 300 to 500. This can be ascribed to the following relation given by the capacitance part. Capacitance is directly proportional to the dielectric constant, and therefore dielectric constant varies in accordance with the defect size and synthesis temperature of nanoparticles. So this is the basically composite synthesis method, electrolyte, composite acid, and the long cycle. So what we found that if we add a certain percent of the copper in terms of the lifetime, it is giving the long cycle. While if you look for the capacitance value, so probably the carbon quantum dots is giving the highest value, that is 796 Faraday per gram, and having the stability around 800 long cycle. So these are the publication of the Swati, which she had to her credit. And we'd like to thank VGC DICSR Indore for financial support, Professor Fase, Dr. Mukul Gupta, and Dr. Kiran Kumar for their support, and all authors who data is during this presentation during the introduction. So thank you very much.
Okay, thank you very much, Prof. There's very nice presentation and sharing. There's one question from Dr. Manoj. Can you suggest any simulation software to study the supercapacitor behavior or performance?
Pardon?
Can you suggest any simulation software to study the supercapacitor behavior or performance?
Actually, I had one collaborator, Dr. Anurag Srivastava, who is working with this COMSOL, and there is another one for name I am forgetting. And they are using this software for simulation part, but we don't do the simulation part for that. We are the experimental group. So, but we have the collaboration with the IIITM Gwalior and Anurag Srivastava, who work with the simulation. So those who are interested, they can directly write to him, Atal Bihari Vajpayee, Indian Institute of Information Technology, Gwalior, and he certainly respond that. So we have the collaboration for different aspect, but not for the supercapacitor. But he is working that.
All right. Okay. Thank you very much, Prof. So now we have finished all invited presentation for today. So thank you very much to all the presenter, and that is very great sharing for today. Now I would like to pass this session to Professor Pramod.
Hello, yes, Professor Noor. This is
Yeah.
all for today's session.
Okay.
Before closing the session, I would like to thank all the presenters, all the speakers of this session. And finally, I would like to thank Professor Noor for session sharing. So now time is for lunch. We'll meet after 1 hour after lunch.
Thank you. Thank you.
Thank you so
Professor.
much.
Thank you all.
Thank you.
Thank you very much. We will see at 2 o'clock, right?
Yes. Okay. Good afternoon to all of you. Welcome back to all the participants, all the speakers. So let me introduce. Sorry. So let me introduce Professor Dr. M.Z. Yahya, the session chair of for the last session of today. Professor M.Z. Yahya is the Deputy Vice Chancellor, Student Affairs and Alumni, National Defense University of Malaysia, and a professor in the Faculty of Defense, Science and Technology. He received his PhD degree in Advanced Materials from University of Malaya in 2002. His current research focuses on energy storage materials for applications in batteries, supercapacitors, fuel cells, and solar cells. He also actively works on computational material science studies. 23 PhD and 31 MSc by research students has graduated under his supervision. He has published more than 190 articles and more than 1800 citations with H-index of 21. So welcome, Professor Dr. M.Z. Yahya.
Okay, thank you, Dr. Sonia, for introducing me. And this afternoon, we'll proceed with the next presentation. Okay, this presentation will begin with I will invite Professor Alexandra Carbon. She will presenting the presentation entitled of anion exchange membrane for alkaline membrane fusel devices. Okay, please welcome, Prof. Your screen is yours. You mute your unmute your speaker. We cannot hear your voice. Unmute.
Okay,
right.
You can hear me now?
Yeah.
Okay, good morning. I share my presentation. Okay, you can see my presentation?
All right, clear, Prof.
Okay, thank you. My name is Alessandra Carbone. I work for the National Council of Research in Italy. And today I'm talking about an ion exchange membrane for anionic membrane fuel cell device. First of all, just a brief synthesis on what is a fuel cell. Fuel cell is an electrochemical device that converts the chemical energy of reaction directly into electrical energy. Among the different types, typology of membrane of fuel cells that are divided by the electrolyte that is used and as a consequence the operative temperature of the fuel cell. The focus of this talk is on polymer electrolyte membrane fuel cell. Polymer electrolyte membrane fuel cells are composed of two porous electrodes separated by ionic exchange polymer membrane that acts as an electrolyte. There are two types of ionic groups. The acidic generally is based on sulfonic group, that is the functional group of the polymer, and the protons are the ions that migrates through the membrane, or anionic groups. Generally, quaternary ammonium is the functional group attached to the backbone of the polymer, and hydroxide are the anions that migrates through the membrane. In the first case, we speak of proton exchange membranes fuel cell. In the second one, anion exchange membrane fuel cell, and the topic is focused on this. Just to give an overview on which can be the possible application of this device that produce electrical energy, they depends on the operative temperature and are divided on portable, stationary or automotive systems. In this table is reported, is listed several portable devices like desktop, laptop, printers, TV, hair dryer, and so on. In particular, what is an anion exchange membrane fuel cell? This is a scheme. The core of the fuel cell is the membrane electrode assembly, a membrane on which are attached two electrodes containing catalyst for the reaction. The half reaction are at the cathode. Oxygen is fed to the cell, humidified oxygen that produce with the electrons produce hydroxide. The hydroxide migrates through the membrane to reach the anode side. In the anode side there is hydrogen that is fed. So hydrogen plus oxygen produce water. So the total reaction of the fuel cell is the hydrogen with oxygen that produce water, electricity, and sometimes heat. The advantage of these devices, the alkaline exchange membrane, instead of proton exchange membrane that are the most used, for example, in this moment, the fuel cell car Mirai, produced by Toyota, has a polymer electrolyte fuel cell inside to produce power. So the advantages is that the temperature operation ranges from room temperature up to 70 degrees at relatively ambient pressure. There are the use on non-noble metal, because for polymer electrolyte membrane fuel cell, the used catalyst, the best catalyst is platinum. With these devices, it's possible to use non-platinum group metals, so more cheap catalyst, and a wider choice of fuels beside the pure hydrogen, for example, hydrogen coming from a reformate process, and the use of cheaper polymers. In general, polyaromatic polymers are used for this purpose. The electrolyte. The membrane acts as an electrolyte, is composed generally by a backbone with attached the functional group. The functional group generally is quaternary ammonium. The properties that the electrolyte should be is, first of all, to separate gases, so to avoid the mixing of the gases, hydrogen and oxygen. chemical and electrochemical stability during operation. In fact, in particular, chemical stability, here is reported some process of degradation, because in alkaline environment, the functional group can degrade. So the properties of the membrane can be reduced, in particular the anion exchange capacity, the conductivity, and as a consequence, the performance. Here is reported the membrane that in this moment is used as a benchmark. Even if for this kind of membrane there is not an official benchmark, this membrane is considered as a benchmark. But the research is moving to produce a benchmark that can be universal for everybody. This is produced by Fumatec. Fumatec is based on a polysulfone backbone with the quaternary ammonium functional groups. So my talk is based on two different points. The first is the functionalization of polysulfone-based membranes, and we investigated the influence of the reaction parameter process and the quaternary ammonium agents. The second one is the preparation of membranes starting from commercial polymers. So we investigated the influence of casting solvent and temperature. Regarding the first part, we used a polysulfone bisphenol A. A chloromethylation reaction was the first step of reaction to introduce a functional group, a methyl chloride, chloromethylene groups. We used a different molar ratio of the reagents or different time. So we can see that the degree of functionalization changes with the molar ratio in time. In addition, we discovered that the degree of functionalization follows a linear trend. So it is possible to control the dF as a function of the time. The second step of this reaction is the quaternarization of the chloride chloromethylene group to quaternary ammonium group. So we investigated two different quaternary ammonium agents, the 3-methylamine, the 3-ethylamine. Maintaining the same the parameters of reaction. From NMR, we can characterize the polymers that we obtained, and we can see that different quaternarization were obtained starting from the same polymer when different amines were used. And the difference is more marked when the DF is higher than 100%. Here is reported the membrane preparation. The membrane preparation starts with the solubilization of the polymer in powder form in a proper solvent. Generally, organic solvents are used. In this case, we used the dimethyl sulfoxide, that it was the best for this kind of polymer that we discovered. Desolubilization of the polymer until to obtain a solution. The solution was reconcentrated until to obtain a suitable viscosity to be cast on a glass by Dr. Blade method. With this micrometric screw, we can set exactly the thickness of the wet film, and there is a correspondence with the final thickness that we want to obtain. Generally, membrane with a thickness of about 50 microns were used. After the casting and the drying of the casting solvent, several chemical treatments were carried out in sodium chloride to eliminate some residual solvents, and in potassium hydroxide to exchange the chloride anion in hydroxide. That is the final anion to be used in the final device. Not all the polymer produces a good membrane, but in particular 100% of functional degrees produces the good membrane to be characterized flat, homogeneous, and robust. The thermal analysis for the three different functionalization degrees highlights that the chloromethylation reduces the thermal stability for all. Then the quaternarization reduces so much the thermal stability, but the polymer is stable up to 200 degrees. So it is a good candidate for the operative temperature in the fuel cell that is from 30 to 80 degrees. So there are no problems. The polymer is thermally stable. This is the water that is entrapped in the polymer, and obviously the water uptake of the membrane is higher when higher is the degree of functionalization, because more functional groups, more wettability, more hydrophilicity in the polymer. This is also confirmed by contact angle measurements. In fact, this is reported at 60 degrees, but the other two functionalization degrees have the same trend. So the chloromethylation slightly reduces the wettability that is increased by inserting the functional group, the quaternary ammonium groups, and the trimethylamine agent produces a more hydrophilic sample than 3-ethylamine. In this graph are reported the increase of contact angle by increasing the functionalization degree for 3-ethylamine basal membranes, while there is a maximum at 1-amine basal membrane. And this trend is still under investigation, why it doesn't increase at 150 degrees. Electrochemical measurement. Anion conductivity is important to understand how many groups are able to transport anions. In this case, a section of membrane, the longitudinal section of membrane was characterized. This is the membrane assembled in a commercial cell. By impedance spectroscopy, we calculate the resistance of the ohmic resistance of the membrane, and from the geometrical factor it's possible to calculate the conductivity. So we can see that the conductivity of trimethylamine samples is higher than the corresponding with the 3-ethylamine. The black one is the commercial, the benchmark. This increase is up to 70 degrees. Then there is a drop of conductivity due to the excessive swelling, so the excessive absorption of water, because this measurement is carried out in fully humidified gas. In accordance with the previous results, this membrane is more hydrophilic than the other one. So an excessive swelling produces a drop of mechanical properties, so a drop of conductivity. Regarding the 3-ethylamine basal membrane, the conductivity increases by increasing the temperature up to 80 degrees. Here is reported the electrodes and membrane electrode assemblies preparation. The catalyst used in this case is platinum, a platinum vulcan catalyst. The catalytic ink produced by mixing the catalyst with the alcoholic solution of the ionomer was sprayed on a gas diffusion layer, commercial gas diffusion layer, and by spray dried, and then the final electrode were assembled to the membrane directly in the cell. The fuel cell conditions, the fuel cell test were carried out in 25 square centimeter by feeding the cell with hydrogen and oxygen at 60 degrees at room pressure and 100% of relative humidity of gases. Here are reported the polarization curves. We can see that the membrane produced with both amines have higher performance than the commercial, even if the trend is opposite to the conductivity, because different sections of membranes are investigated. In the case of conductivity, longitudinal section. In the case of fuel cell, through plane section. And this means that probably there is an anisotropic disposition of the groups inside the membranes. But in any case, higher performance were reached from 3-ethyl-based membranes instead of the other two membranes, with 300 milliwatt for square centimeter of maximum power density. So in conclusion, for this part, the functionalization reaction tool was set to predict the functional degrees. Two different quaternary ammonium groups were evaluated and different results were obtained, in particular quaternarization yield, thermal stability, hydrophilicity, and conductivity, and higher performance for 3-ethyl-based membrane were obtained in fuel cell configuration at 60 degrees. Now we pass to the second part of the talk, that are recast membrane produced by commercial solution. In this case, we use a commercial solution in NNP or commercial polymer that were dissolved in lab using dimethylacetamide. The preparative procedure of the membrane is the same that I explained before. In this case, we investigated different solvents and different drying temperature, 80 and 50. Why this temperature? 80 is our standard lab preparative for membrane. 50 is generally suggested from the producer, that suggested to not overcome 60 degrees. So we wanted to investigate a temperature lower and higher than 60 degrees. These are the characterization that we carried out of this membrane, TGA, conductivity, I showed before, anion exchange capacity, that means how many anions are present per gram of polymer. Are measured with two different anions, chloride and hydroxide, by two different back titration methods. Water uptake is the immersion of the membrane in water or KOH solution, and the uptake is measured by simply weighting the wet sample and the dry sample, and scanning electron microscopy. So, the NMP-based membrane here reported the ion exchange capacity of chloride and hydroxide. And we can see that there is a decrease from chloride to hydroxide due to the mechanism of degradation that I show in the second slide, or poor ion exchange, but probably is a degradation of the groups in alkaline solution. But in any case, the conversion is higher than 90%. The chloride membranes has a higher value of ion exchange capacity when the drying temperature of 50 degrees is used, and lower when it is used at 80 degrees for both samples. So the hypothesis, because this value is higher than the nominal amount reported by the producer, the hypothesis is that at 50 degrees there is a residual solvent that can be exchanged from with the sodium chloride or potassa solution, substituting and increasing the ion exchange capacity due to the high boiling point of the solvent. Regarding the dimethylacetamide-based membrane, the trend is similar because there is a degradation passing from chloride to hydroxide, but the values of ion exchange capacity are similar for both samples. A conversion lower than that reported from the previous membrane was found, and similar to the commercial one. And the hypothesis is that no residual solvent can be found in the membrane due to the lower boiling point of the solvent. So casting solvents affect the final properties of the membranes. Regarding the thermal stability, we can see that the water loss, that is the first part of the curve up to 150 degrees centigrade, the water loss is higher for sample prepared at low temperature. In fact, the mass loss is higher than for these samples. but the thermal stability is the same. Regarding water uptake or KOH uptake, these parameters decrease when the post-casting drying temperature increase for both samples, and the parameter lambda that indicates how many molecules of water are coordinated per functional groups follow the trend of water uptake and ion exchange capacity. The same images for membrane produced NMP with different temperature shows that there is no evident porosity due to the residual solvent. The same is for membrane prepared with dimethylacetamide as a casting solvent. So similar morphology was found independently from the casting solvent. Regarding the anion conductivity, in this case, the conductivity for both for all samples, the conductivity increased by increasing the temperatures. But for membrane that has a higher water uptake, the swelling phenomenon causes a drop of conductivity after a maximum values, that is 60 degrees for membranes dried at 50 degrees and higher at 70 degrees for membranes dried at 80 degrees. In any case, only the membrane produced with NMP at 80 degrees has a good stability up to 120 degrees. Here is the same preparation of electrodes and membrane electrode assemblies. This time, the temperature of a fuel cell was investigated from 60 to 80 degrees centigrade. Depolarization curves of membranes based on NMP are higher than the benchmark in both temperatures, and we can see that membranes dried at 80 degrees shows the highest performance at both temperature. The OCV values, that is the open circuit voltage values of 1, is a very good value because this parameter indicates that there is no mixing of gas, no high crossover of gas from one side to the other one. If it should be a crossover, the OCV value can be lower due to the formation of the mixed potential, so a parasitic reaction occurs due to the mixing of the gas. So the performance increase passing from 60 to 80 degrees. Regarding the dimethylacetamide based membrane, we can see that the performance are lower than membranes prepared by NMP. In that case, OCV values are good for all membranes, in accordance also with the same images. And at 80 degrees, the membrane prepared at 80 degrees of drying temperature produces the highest performance. We can see that the power density also in this case is in the order of 300, 368. And here the power density is about half of the previous membrane. So lower performance were obtained. So in conclusion, NMP-based membranes presents a counter-ion conversion higher than 90% independently from the drying temperature, good thermal stability for all membranes, highest conductivity for membranes dried at 50 degrees, but better performance for membrane dried at 80 degrees, and in particular better performance for NMP-based membrane at each investigated temperature. So thank you for your attention. And do you have a question?
Okay, thank you very much, Prof. Alexandra, for your very nice presentation and for very interesting work that you have shared. Okay, we have a question from chat board. Okay, I will read. From Prof. Yogi Nagao. Okay, in the first topic, he want to know why the reason why you choose backbone and cation.
Okay, the reason of the backbones of the polysulfone polymer is found because this is one of the most used polymer for this kind of application. It is a thermostable, so it is important the thermal stability. It is flexible because there is the bisphenol A that gives to the backbone flexibility. And it's possible to produce easily handling membrane, so it improves the good mechanical stability. In addition, the glass transition of this polymer is high because it's 190 degrees centigrade, and it prevents from the possibility to have a transition during the operation condition. So this is the main reason for the choice of polysulfone. Regarding the cations, quaternary ammoniums are generally the most used functional groups. Someone used the functional group based on phosphorus or something similar, but in general, quaternary ammoniums are easy to prepare, are scalable, are not so dangerous material respect phosphine or other things, and is easy to have, to buy. And generally, there are a wide variety of quaternary ammonium groups. This is a starting point from trimethylamine and triethylamine, just to see the length of the amine, which difference can produce in the membranes. So these are the mainly motivation.
Okay, again, thank you very much, Prof, for very good explanations given. Okay, thank you. So we proceed to the next speaker, the afternoon. I would like to invite Professor Sabrina Bilbek-Caché from France. She will be presenting the work entitled Layer by Layer Assemble Capsule as Promising Drug Delivery System. Okay, please, Professor Sabrina.
Yes. So, hello everyone. Do you hear me?
Yeah.
Great. So let me just share my screen. Okay. Is it okay for you?
Yeah.
Did you see my presentation? Okay. So let's start. So I'm very pleased to present my my work. So yes, as you say, I'm Sabrina Belbecouche. I am an associate professor in the East Paris Institute of Chemistry and Material Science. And today I will talk about the interest of developing polyelectrolyte capsule as a promising drug delivery system. Let me first explain you the context of why we are interested in developing such a system in my group. So, in fact, as you may know, there is a lot of problem when we use drug. For instance, due to the poor stability of the drug, or there are some problem of the solubility of the drug in the aqueous media, or sometimes there is some problem just after the oral administration of the drug. So it's important to develop strategy to allow the achievement of the drug to the infection site, for instance, for allowing the required amount of drug to reach this infection site without altering the initial administrated drug. And it has been proven that nanocarrier could be one of the valuable alternatives to overcome such issues. The issue also that we have to take account is the problem which can occur in the bloodstream, for instance, phagocytosis phenomena by macrophage or endocytic uptake of Kupffer cells. So it's very important to develop tailor-made carrier, which we are able to control the size and the surface characteristic, because it has been proven to allow to modulate all this biodistribution parameter. And among all the nanocarrier that we can use, for instance, you may know micelle vesicle, I'm very interested in developing a low particle, also called capsule. The strategy which I use is based on the use of sacrificial template, which could be a liquid, if we think, for instance, of the use of nanoemulsion, or solid, for instance, if we use colloidal particle. And this characteristic of the sacrificial template will control the resulting characteristic of the capsule. And also, we use the well-known layer by layer technique. I mean, we use polychloride, which will be stepwise absorbed on the template, and then we will remove this template without impacting the colloidal stability of the particle to obtain this capsule. The interest is that we can easily control the size of the resulting particle from the nanometer to the micrometer. We can control the amount of the polymer which could be coated, the film thickness, and we have shown that it's very important to control the thickness of the film, because it has a huge impact on the resulting rigidity of the multilayer shell, I mean on the mechanical property of the capsule, which could impact the incorporation of the resulting particle inside the cell. Of course, thanks to this technique, we are able to control the drug, which could be loaded inside the particle, in the multilayer shell, and at the surface. And we aim, of course, to control the release of the drug. So I will show you some example during my talk about this. So to control the release and also to obtain biocompatible system, I am very interested in using biopolymer. Among them, I specifically use polysaccharide. So there is some example, as you can see here. The very interest of using polysaccharide is that most of them are biocompatible, biodegradable, and also, as you can see, there is a lot of functionality. For instance, see hydroxide, amine, carboxylic acid, which can be chemically modified to bring to the resulting system stimuli response and also to allow targeting. And developing stimuli responsive system is very important to allow the gradual release of the drug into the body at a control rate over a specific period of time. And this then allows the patients to take medications less frequently. Among all the stimulus today, you may know pH responsive system, thermosensitive system. Today, I will focus on glucose responsive system, hydrogen peroxide system, and redox responsive system. So let me first begin with glucose responsive system, which could be useful for treating diabetes or cancer. So the glucose is a very interesting class of chemical stimulus, which has a great impact on medical application because this molecule has a very important role in living system. For instance, if you remember I talked about cancer, glucose is overproduced in tumors. There is a high concentration in glucose in comparison to normal cells. And also, as you know, when there are problems of diabetics, there is a high amount of glucose compared to healthy person. So to develop glucose responsive system, I am very interested in using the boronic acid chemistry, as you can see here. In specific physico-chemical condition, the boronic here, as you can see, is able to complex with the diol and to form a stable complex. And by controlling this physico-chemical condition, I mean, for instance, by increasing the amount of glucose. So I think that you have understand that this diol will be further the glucose. We can play on this thermodynamical complex and are able to release a drug. As polyelectrolyte, as I say, we use polysaccharides. So here, as polycation, we use ketosane. You can see here the chemical structure. The interest of using ketosane is that it's biodegradable and biocompatible. It's a FDA-approved system, and this polysaccharide presents an ammonium group. As polyion, we have selected the alginate, also very used for biomedical application. And alginate possesses a lot of carboxylic acid, or here it's represented carboxylate. And this carboxylate has been modified to introduce boronic here acid. So of course, we're able to control the amount of the boronic which will be introduced here. And this will have a huge impact on the resulting glucose response. To study the layer by layer assembly, one of the very useful technique is a quartz crystal microbalance. You can see here. The technique is based on the piezoelectric effect. So in fact, there is a mass which is measured by measuring the change in the frequency of a quartz crystal resonator. So let me show you a quick short videos for those who are not familiar with this technique, which is very interesting. Let me show you. Oh. So here, this is a device. So as you can see here, there is a quartz, so which could be coated with different metals. So here, the quartz is the gold, for instance. And we can follow the multi-layer buildup, so with the polyelectrolyte, as I told you, and we are directly the impact, of the thickness. We can follow also the mechanical property of multi-layer film, and we can study, for instance, different parameters. For as you can see here, the swelling effect according to the solution that we will flush on the surface. So this technique has been used to follow here, the multi-layer assembly, because as you can see here, flushing the different polycation and polyion result in a decrease of the frequency, and this is directly correlated to the increase of the mass on the substrate. And we can then flush this substrate, which has been modified with the multi-layer of interest, with different solution. And if we flush this multi-layer with solvent, there is no variation of the frequency. I mean, the multi-layer remains stable. And if we flush this multi-layer with the solution containing glucose up to a critical concentration of the glucose, you can see there is an increase of the frequency shift, which is in accordance with the multi-layer detachment, I mean, with the glucose responsive system. So this is simply based to the fact that you remember, I told you that in the alginate, we have incorporated boronic, and here, so the assembly will be done with the carboxylate and the ammonium group of the ketosane. As soon as we flush the multi-layer with glucose, so you see here the diol, this diol will be able to interact with the boronic present in the multi-layer shell here, and will form this complex, and this complex contain a boronate, so I mean this contain another anionic charge, which leads to the multi-layer destabilization. Interestingly, if we cross-link the multi-layer film before to flush the multi-layer with the glucose concentration, according to the cross-linking time here, we have not a removal of the multi-layer, but we see a swelling effect. Okay, so If we do not cross-link, all the multilayer is removed up to a critical concentration. If we cross-link the multilayer, we see a swelling effect, I mean a change of the permeability of the multilayer shell due to a specific concentration of glucose. Of course, we are able to control this concentration according to amount of the boronic introduced in the alginate, according to the number of the layer which will be prepared, and this allow to control the release of the drug. Okay, so this is just what I say, total destabilization of a multilayer film, or we see a change of the swelling, a change of the permeability of the film, I mean a swelling effect. As soon as we have determined all the physico-chemical conditions to obtain this on flat substrate, we go to the use of sacrificial template, as I say, to prepare this capsule. So we can use different templates. So for instance, we can use calcium carbonate particle. The interest is that we can easily synthesize it from nanometer to micrometer in a controlled way, as I say. And also, they, as you can see, calcium carbonate present negative charge on the substrate, and we can absorb this different polyelectrolyte. So to follow the different step of adsorption on the surface of the particle, we use the well-known zeta potential measurement, and we see that indeed, when we have calcium carbonate, the surface is initially negatively charged, and up to the exposition to the ketosane, it switched to positive value, and addition of the alginate leads to a negative value, as you can see here, -20. Okay, so then the template will be removed. As I say, we can control the drug which will be loaded. Here, we take advantage of the use of calcium carbonate because the calcium carbonate are porous. So we can load the probe or this probe will be further inside of the probe, then we will add drug to load it inside the porosity, and all the strategy will be applied. And to remove this calcium carbonate, we use a very soft condition, for instance, acidic condition, or we can complex this calcium carbonate to obtain this low particle. So let me show you here the particles that we obtain. So calcium carbonate, which are modified with the multilayer film. And then when we remove this template, as you can see, we obtain microparticles. So still here, the interest is that we keep the characteristic of the template. Then when we load a probe, to mimic, for instance, the incorporation of the drug, we decide first to load the rhodamine, which is a fluorescent probe, inside the porosity of the calcium carbonate, and we modify the multilayer. So you see here by fluorescent microscopy that indeed we have particles loaded with this fluorescent probe, and up to a critical concentration, the rhodamine is released, as you can see here. And if we cross-link the multilayer film, we see that the exposition of the glucose leads to a gradual release of this rhodamine. Okay, so if we want to go to a small size, we can use gold nanoparticle. The interest of using gold particle is for instance, if we want to do transmission electron micrograph, or also to study the incorporation of the particle inside cells. And you can see that indeed we have bare gold particle here, then gold particle modified with multilayer shell. And here, when we remove the gold particle, we see that we have capsule. So you can see here that these capsules are a little bit collapsed. This is simply due to the technique, because there is a vacuum when you use them technique, and all these experiments are done in the dried medium. So it's expected that we obtain this aggregation state. But we have shown with other technique that this capsule remains stable, for instance, with the DLS technique. And we have shown, or we have studied the colloidal stability over 4 months to show that the size and the zeta potential remain stable. The interest of the technique is that we are able to control the amount which is loaded and released. It's also possible to load 2 drugs, for instance, in the porosity and in the multi-layer shell. Of course, instead of loading the rhodamine, we have tried to load the insulin, and we show that we are able to release this compound. Okay, so let me now show you the interest of developing hydrogen peroxide responsive system. So this system could be very useful to study inflamed tissue. Still, we pay attention of the boronic acid chemistry, as you can see here. We have this different formation of complex, and here up to a critical concentration of hydrogen peroxide, this complex is disturbed. And why we studied this, as I say, oxidative stress is mainly due to the accumulation of hydrogen peroxide, and this enabled to distinguish between inflamed tissue from an healthy one. So it's very interesting to develop such kind of system. So here, as a polychloride partner, still we use this phenylboronic modified alginate, and we use dextran, also a polysaccharide. And here, this boric acid will complex with the diol present inside the dextran, according to the complex that I just showed you. So we follow the multi-layer buildup with the QCM technique. And when we flush the resulting multi-layer with hydrogen peroxide, we see that there is a gradual increase of this frequency showing the hydrogen peroxide responsiveness. Of course, if we simply flush the substrate with a solvent without hydrogen peroxide, there is no impact on the multi-layer. Okay, so let me now move to the last example, the interest of developing a redox responsive system. So here we show you the interest of developing such a system for kidney disease treatment. So this is a collaboration that we have. This is a kidney disease. So here you can see healthy kidney and disease 1. Here you can see that there is a degradation of the kidney. And you see that it's very important to be able to control all the parameters of the carrier, because there is a specific size which is targeted to allow the particle to go across the kidney and to be able to release a specific compound. This specific compound here is a protein, because my colleague has evidence that the renal membrane degradation is due to the overexpression of a protein. And they show that using a specific DNA that they have developed allow the inhibition of this protein and then prevent the renal membrane degradation. So it's important to be able to vectorize this DNA. So as you may know, the DNA is a polyion. And it's also important to be able to control the size of the vector. And another parameter that we have to control is the charge surface of the particle, because the kidney membrane is positively charged. So it's important to develop particles which are positively charged too. And I say that we use a redox responsive system because, as you may know, disulfide bonds are extremely stable in the extracellular medium, and they are naturally released or reduced inside the intracellular medium, because inside the intracellular medium there is a presence of a reducing agent, which is a glutathione, which allow the reducing of this bond, and then we can release a compound of interest inside the intracellular medium. So this is very interesting for us. So the strategy here is based on the DNA, which behave as a polyion and which is the drug. And we use a ketosane, and this ketosane, we chemically modify it to be able to introduce thiol, as you can see here. And you see that after this chemical modification, we have this thiol that we're able to control the amounts, and also the interest of this chemical modification that we see that the ketosane is still positively charged, so we can still use it as polychloride for the multilayer assembly. And we have seen that the resulting particle that we inject, this DNA has been tagged with a green fluorescent probe. This is and this particle has been injected into a mice, as you can see here. We see that our particles are able to reach the kidney here, and without DNA, or there is no particle which reach the kidney. Okay, so to conclude, I show you the interest of developing glucose and hydrogen peroxide system based on boronic acid chemistry. Also, the interest of using redox responsive system. All this combined to the use of templates and multi-layer shell. So it's very easy, but the most important thing is to be able to control all the physical-chemical conditions, because if the pH or if the unique strength are not controlled, you can easily collapse all the system. And all this can easily be monitored, as I say in the beginning, by using QCM technique. Okay, so all this system have been, some of them patent or all are published. So if you want to have some information about it further, and if you have question, please do not hesitate to ask, or if you want to contact me to collaborate, for instance, I will be pleased to discuss and collaborate with you. So thank you very much for your attention.
Okay, thank you very much, Prof. Sabrina, for your very amazing work you have done. Okay, if there any question from our audience, please, or you can type the question in the chat box. Okay, okay. One simple question from me. Okay, is there any simulation or computational technique that can be used to study this topic, Prof?
What do you mean? I don't. Could you please repeat? I don't hear.
Is there any simulation or computational technique that can be used to study this topic, Prof?
Unfortunately, not. It's not possible. All the experiments that we have to do, as you can see, is to do physical-chemical experiment, and then to try to do in vivo and in vitro experiments to evidence the efficiency of the system that we have developed.
Okay, okay, all right. Okay, thank you very much again. Thank you very much to Prof. Sabrina for a very nice presentation. And then we go to our plenary speakers, plenary session, last plenary session for this conference, plenary 5. Okay, our presenter this afternoon is Professor Agnieszka Pawlika. So allow me to read her CV. Professor Agnieszka Pawlika obtained her master at Warsaw University of Technology in Poland and her PhD in chemistry, physical chemistry at the University of Sao Paulo, Brazil in 1993. She is currently professor at the University of Sao Paulo. She has published 189 full papers in professional journals and 22 conference proceedings. She is the author of 3 books and 4 patents and has received 17 awards. In 2014, she received the scientific title of Professor of Chemistry from President of Poland, Bronisław Komorowski. She participated in several scientific international events and was a visiting professor at Warsaw University of Technology in Poland in 2008 and at the University of Malaya, Malaysia in 2011, 2012 until 2013, and in 2015, she was a visiting scholar at the lab of Professor Jerzy Kanichi of the EECS University of Michigan, USA. She is a member of the editorial board of 2 international journals and referee of more than 30 magazines and Brazilian and other international science sponsoring agencies. She was advisor of 20 master theses, 12 PhD dissertations, and 6 postdoctoral fellowships. Moreover, she was a head of the Culture and Extension Commission at the Institute of Chemistry of São Carlos, the University of Sao Paulo, and coordinator of post-graduation course at Science Engineering of Material at University Sao Paulo. Her major is chemistry and material science with an emphasis on material for electrochemical devices and development of electrochromic windows. She also started with development of biodegradable hydrogels based on natural polymers for application in agriculture. The keywords related to her works are solid polymeric electrolytes, natural polymers, electrochromic devices, thin films, conducting polymers, electrochromism, and ion conduction. With that, I would like to invite Prof. Agnieszka, to deliver her presentation.
Thank you. Thank you very much, Professor Yaya. I am very happy to be with you again, to meet you. Unfortunately, not in presence, but still we see each other. These are my first words in this morning. It's early for us, so forgive me if my voice is not so clear. First of all, I would like to thank organizer for inviting me. I am very happy, as I said, to be with you. Thank you, Professor Pramod, for inviting me. And as I said, I'm very happy to see my friends. I see here Professor Ikwan, to whom I worked with some years ago. So let me share my screen. Okay.
Okay, clear, Prof. Right.
Do you see it?
Yeah. Okay, clear.
Is it working?
Yeah,
okay.
It's working.
I would today I would like to share with you some of my more recent research about environment-friendly hydrogels for plants and for devices. This work we are developing in our lab and also with collaborations. Superabsorbent, I will start with superabsorbent polymers or hydrogels. They are commonly called as SAPs or super slappers or super soakers, which are hydrophilic, cross-linked, and mainly synthetic polymers that have ability to absorb and retain large quantity of water without dissolving. As we can see here, I took this picture yesterday. We can see this ability where I have some old polyacrylate hydrogel in dry form. And after a few hours in water, it increased its volume by 91 fold times. So these SAPs or hydrogel or superabsorbent hydrogels, they are made mostly from sodium polyacrylate. They can be also made from polyacrylamide copolymer with polyacrylate, and some of them from polysaccharides. And they are usually used for mainly for personal hygiene, like baby and adult diapers, and also for female hygiene products, among some others. In medicine, we find them for wound healing, as wound healing pads, as contact lenses, as medical implants, and also cell growing substrates. And more recently in agriculture, we can see them as soil conditioners and chemical substances controlled release matrices. Before, when I was trying to prepare, when I was preparing this this presentation last days, I wanted to know, I must say, okay, we are working with hydrogels, but what is the market value of these hydrogels? So I was browsing a little bit in the literature, and I discovered that that this market is very interesting. So I would like to share with you some of the data I found. Okay. So this value, the value of this market in 2019 was $9.58 billion. And it was mainly due because of the sodium polyacrylate hydrogels, which had held 44.6% of the market. And the more interesting is that this market is growing, and the projections are to reach almost double in 8 years, to reach 16 billions, more than $16 billion in 2027. Other interesting information I found that this market is fairly fragmented. So there are numerous players. Some of them are big, some of them are small. So it's fairly fragmented market. I got this data from 4 research agencies. So just I wanted to see if they're true or not. So I discovered that basically they have the same values of compound annual growth rate, starting in values of 9.58 or 7.6 in 2019. The growth will build up to 16 or $10.8 billion. And this year, CAGR value about 6-7% in 8 years. But when we look at the more recent data, this value decreased a little bit. It is sure it is because of pandemic. And also this last one was, the projection was done for only 5 years. So, but still we can see the it's a very high value for this kind of materials. And it is due mainly by the growth in Asia Pacific, also in Latin America, as we can see here in green dots, and also in a little bit in Saudi, Middle East and Africa. We have actually we have in the world, we have 3 types of markets. So we have the market which is a saturated market, which is North America. but still we can see a growth of this market for SAPs. We have a stable market, which is Europe, and still we have seen, we are seeing a growth in this stable market. And we have a futuristic market, which is attributed to mainly to the Asia Pacific. And the Asia Pacific in 2019 region had a share was almost 50%, and this share is also projected for the next 8 years. So what kind of materials are expected? Surely they're expected personal hygiene materials for SAPs, industrial materials, medical materials, some others materials, and also for agriculture. So this growth is expected not only for sodium polyacrylate, but also for polyacrylamide copolymers that are widely used in diapers and water treatment. But still, the biggest growth is expected for the personal hygiene materials. And this segment is responsible for CAGR of 7.7%. Okay, so when we are talking about hydrogels and diapers, we always remember about the environment problems. And maybe not in this developed country, we don't see this as much in some other countries. And here I found some pictures from Indonesia, from the people recovering diapers from a river in Java. So as SAPs are mostly made from synthetic polymers such sodium polyacrylate, they are not biodegradable. So they pollute environment, and this pollution is made mostly by this hygiene, personal hygiene products, and mostly by diapers. So not only regular people as us are seeing this, but also the main players observe this problem, and they are trying to adopt new strategies to overcome this problem. So the industries like Nippon Shokubai, Live-Do Corporation, or Total Care System in November 2020 announced that they have been developing various technologies to promote systems that recycle disposable diapers. So this is a good news. The other good news for this kind of materials is from BASF that came recently in March of this year. And they said that they're investing $30 million in new excellence center for its hygiene business. With this investment, BASF will increase innovation capabilities for its SAP business by building a state-of-the-art super absorbent excellence center at its Verbund site in Antwerp, Belgium. So there are good news, because super absorbent hydrogel are very interesting, are used as we see, and we need them. The other information I found was that all the markets report interest in developing new and eco-friendly and cost-effective products with high water retention capabilities. So this is from one side, we have the solution for recycling. And from another side, it is expected a development of new materials that can be more environment friendly. So it is expected more investment in the research and development of bio-based superabsorbent polymers. And also it is expected more investment and more SAPs adopted by healthcare and especially for agriculture sectors, as I showed you a few slides before. Why that? This is because hydrogels, they have some advantages, and for personal hygiene, we know that. And for agriculture, which is of our interest, we can see that these hydrogels, they act as soil conditioners by improving the soil fertility, the soil aeration, the soil compactation, etc. It also reduces irrigation frequency. They also reduce overuse of fertilizers and pesticides. They also can improve availability of water during rain shortage, and in overall, they positively impact soil edaphone. As we say about advantages, we always see the disadvantages. And for not only for eco-friendly materials, but also for synthetic materials. But this one, the first one is mostly for eco-friendly. The presence of ions in the water can decrease the swelling of the hydrogels. And the hydrogels can only help in water management if there is enough rainfall or additional watering. So if there is no watering, they can't help. And some of disadvantages is also that the hydrogels usually are expensive. So when we talk about agriculture, they are mostly used for potted and gardens plants. But I see that the increase of interest in hydrogels for agriculture is happening. So when we talk about agriculture, again, and agriculture and hydrogels, again, the types they are used are the same as we have seen before. So they're cross-linked polyacrylates, which, as we see, are mostly used because of their very good water retention, high efficiency, and no toxicity. There are also cross-linked polyacrylides and acrylamides, acrylates copolymers. And finally, this more eco-friendly materials based on starch grafted copolymers, mostly with synthetic polymers, which are obtained by free radical polymerization of starch with acrylic monomer. Seeing this perspective, some years ago, we decided to develop new eco-friendly and environment-friendly materials based on only natural polymers. We have already tradition to work with natural polymers. So we decided to do some hydrogels for agriculture, looking at fertilizer release and water management. So the first samples we made a few years ago, they were based on gallan gum and chitosan. And as we can see here, we have a polysaccharidic chains of chitosan and of gallan gum. And the advantage was because why we chose the gallan gum? Because it has very specific chemical structure with this double helix chains that can absorb a high amount of water. And also it has it is negatively charged. So it was possible to cross-link it with chitosan. As we can see, here we have chemical structure. Here we have, on the right side, we have some representation of chains, chitosan and gallan gum chains interactions. And on the bottom, we have the pictures of hydrogel, hydrated hydrogel of this gallan gum chitosan. So we did some measurements of these hydrogels. First, we did the measurements of swelling, and we prepared many compositions. The compositions starting with less gallan gum. We used high acetyl gallan gum. We also worked with low acetyl gallan gum and chitosan. So we started with low quantity of gallan gum in these compositions, and we finished with high acetyl gallan gum composition and chitosan. So as we can see here, the quantity of gallan gum in the composition impacts the swelling ratio, where the samples with high quantity of gallan gum have the best and highest swelling, reaching more than 200 times of water swelling, so of its own weight. We also did some measurements of water evaporation. So we compared the water and this hydrogel samples, and we proved that they retain the water. These measurements were done at 70 degrees. So the water retention was pretty good. And finally, we also charged the samples with some fertilizers. In this case, I am showing you MKP, which is monopotassium phosphate release. So we soaked the samples in solutions of 1 gram per liter of this fertilizer, 5 gram and 10 gram per liter. Then we dried the samples, and the release was done in the water by measuring its conductivity. So in all the cases, we can see that depending of how much of fertilizer we have in the samples, the release reach the higher or lower values. But for all the samples, we have like a release in 8 hours after putting the samples in this clean water. So we did these measurements not only for these samples, but also for some other compositions. So we tried during this last years, we tried with some other compositions. So besides galen gum, high acetyl galen gum, we always worked also with low acetyl galen gum, but the results are a little bit worse than high acetyl galen gum. So we worked with hydrogels of networks of galen gum and chitosan, galen gum with jeffamine, which is a polyether diamine called Jeff. We made some hydrogels of galen gum and lysine, and also galen gum with gelatin. Then we made some other composition, which was alginate and chitosan. So, what we observed, it was that still among all the samples we prepared, galen gum and chitosan were the best ones because of higher swelling of 218 times, and depending on the samples, it decreased up to 80 times for the alginate and chitosan. But when we compare these results with some results in the literature, so with these samples, hydrogels that contain natural polymer or its derivative, mostly derivatives, we can see that with our results, we are far below. So we're in between here. So we didn't reach these values. However, the values I was observing in this market reports are expected to be in between 500 and 800. So we are still below these values. But when we compare the values obtained for hydroxypropyl methylcellulose and methylcellulose, we see here that our value, the worst our sample is still much better than the samples reported in this research, in this paper. So we did some tests also with our samples. We just made some tests for seeds growing, germination of seeds. So we prepared 3 kinds of samples: a control sample, sample with hydrogel. So we put seeds in 3 samples, in 3 pots, and with here we in the middle we put hydrogel without fertilizer, and also we made samples with seeds and fertilizer and hydrogel and fertilizer. And what we observed in this lab test, that our hydrogels, after watering only 1 time and with the same amount of water, same volume of water, it was, I think, if I remember well, it was 10 milliliters of water for each pot. So only the samples that had hydrogel and hydrogel with fertilizer allowed the seeds to germinate. So it was very positive test, and we were very happy with that. But not only this was of our interest, as we are seeking to see and to develop the materials that are biodegradable, that are environment friendly. So we tried to do some biological tests, which didn't work, but simple letting the samples in the lab environment, we observed that they were attacked by fungi. So this indicates that this kind of materials is biodegradable. So we were very happy with this, and we are trying to go in this direction, developing other hydrogels and to confirm our results on biodegradability. So this was the part about the hydrogels we are doing in the last few years. The second part, what we are working on are materials, are membranes, are hydrogels for devices. Actually, my colleagues like Professor Yaya, Professor Ikwan, they promote also. They know we are working for years with ionic conducting membranes made of natural polymers, similar as my colleagues. So we are working with geopolymer electrolytes and solid polymer electrolytes. They are made mostly of natural polymers. We are working with polymers and macromolecules. We were working with many of them. We have worked with hydroxypropyl cellulose, hydroxyethyl cellulose, with alginate, with galen gum, with chitosan, with also we've worked with DNA-based membranes with ionic conducting properties. But in recent years, we decided to develop and to see what happens when we add to this natural membrane compositions some clay. So we started working with Montmorillonite clay and three kinds of samples with gelatin, galen gum, and alginate. And first of all, we seek to see how this clay interact with these polymers. So if they form separated phases, intercalated, or exfoliated. And for that, we used X-ray measurements, and we discovered that when we work with gelatin, so depending on the quantity of clay, the structure of these membranes can be or partially intercalated or exfoliated. So the membranes that had the biggest quantity of clay, up to 20%, they had partially intercalated structure, and we are not sure now if it was because of the clay or because of the gelatin triple helix crystal structure. So, but still there is some kind of interaction, different interaction when we compare with the samples with lower quantities of clay. When we look at alginate nanocomposites, we observed independent. We have worked with clay, sodium clay and lithium clay, modified lithium clays. Depending on the clay, we didn't observe any peaks. So in this region, so we confirm that the structures are exfoliated. And for Galen gum, again, we have quite different results. As we can see, for Galen gum, the structure was confirmed as predominantly intercalated, and it was again probably due to the Galen gum double helix structure entanglement.
Prof, you have 5 minutes more, Prof.
Oh, sorry, I will go faster. I have some few results. So here we have some transparency results. So we can see that some samples are more transparent, but when we add more clay, the samples start to be more opaque. But the most opaque samples are again the Galen gum, which is probably because of its structure and the interaction, different interaction with the clay. Okay, here I have, as these membranes are used for the ionic conductivity and for the devices, so we evaluated the ionic conductivity properties, and we discovered that the samples are have very high conductivities ranging from 10-4 to 10-3 Siemens per centimeter in between 25 and 80 Celsius degree. So the same we observed for samples with gelatin and lithium modified clay. When we look at the alginate, the values are one-fold higher, so from 10-3 to 10-2. And for the Galen, again, we have a little bit different behavior. So as for other samples, the behavior is linear, so Arrhenius behavior. For Galen gum, we have two Arrhenius behaviors with some change of the inclination, which probably is due of this interaction of the Galen gum and clay interaction. So here I have some comparison of the samples. Sorry, I didn't put other most of the samples have very appreciable ionic conductivity values ranging from Arabic. So the values, they increase one-fold between and we
Prof, you mute your speaker. Please unmute your speaker. We can,
okay. Okay, I lost my connection. Sorry about that. The internet is not always. Do you see my presentation?
Yeah. No.
Okay. Sorry about that. So I am just finishing. We did also some TGA analysis, thermal analysis to see about the water in our samples, but we are pretty sure that we don't have much water when we do electrical measurements because we do this under a vacuum. So we did also some measurements about the conductivity when we heated the sample at 90 degrees. And then we analyzed, it was done in dry box. So these values are the lower, a little bit lower values are due to the sample which was heated at 90 degrees. And the red values are due to the samples that was only heated in normal condition. So as we can see, the samples without no heat treatment and with heat treatment at 90 degrees, they're still in the same range of values 10-5. So there's not very big differences. We proved this this water content by the FTIR measurements. So to conclude my my talk, I would like to say that natural polymers and their derivatives are very versatile raw materials. They can be successfully used as superabsorbent hydrogels or gel polymer electrolytes. As superabsorbent polymers, they can absorb up about 200 times of water and release it to the soil without or with fertilizer. As GPS, so they can form ionically conducting membranes that reach conductivities up to 10-2 Siemens per centimeter in room temperature. They can be combined with clays, resulting in better properties compared to the electrolytes without clay. And they have many advantages over synthetic polymers, and their main advantages are biodegradability, compatibility, and renewable origin. Finally, I would like to acknowledge my collaborators, my students, and my former students, and also the sponsoring agencies. Thank you very much for attention.
Okay, thank you very much, Prof. Agnieszka, for your very amazing presentation and knowledge sharing. Okay, so the question, we have one question from the audience. Okay, in the chat board, what are the current industrial application of this hydrogel, Prof?
Oh, as I thought, do you mean this hydrogel, natural-based hydrogels, or the synthetic ones? So when we see synthetic ones, we have contact lenses. We have, as I told you, the spotting hydrogels. We have diapers and female hygiene, also for medicine capsules. When we why I was talking about the market value, because recently last year I got some actually for last few years I am receiving emails from some agriculture people, the people who are working with agriculture, so they have small or bigger properties and they want to plant and they want to do this modern technologies, and they want also do some these technologies to be environment friendly. So and recently last year I was contacted by some industry, Brazilian industry, who is looking also for hydrogels for agriculture. The main problem is the price. So they are expecting to pay, to have the material that costs about $3 per kilogram. And this hydrogels we develop, the problem is the price, because we are working with gallon gum, which for instance, the price is $26 per kilogram. It depends from where it comes. So we can have better price at this moment. So, but what I am seeing recently is a very big interest in the hydrogels for agriculture. I don't know if I answered the question.
yeah. Okay. And then, okay, maybe one question from me, just yeah. So actually, when we are dealing with the biodegradable material, Prof, so one of the factor of the challenge is the aging factor of the biodegradable material. So how could we overcome or we reduce this problem?
Oh, I think it is not a problem. I think this is an advantage. So aging,
you see,
yeah.
in opportunity side, it is very good.
Yeah, exactly. I am looking on my, on my cell phone, and I see that we don't use them more than 2 years. So, the industries, they don't want us to have, the appliances and products, that are permanent for years and years. Then they don't want us. They want us to change, to move forward. So I think that this natural-based materials are very interesting because if we use less, we don't pollute as much as synthetic ones, and sure they will integrate in the soil when we talk about agriculture. So I don't think that this is a problem. I think this is an advantage, that we can, if we pay less, maybe, and we can, buy every, 2 seasons, the hydrogel for the soil, it is not a problem, because these materials, they degrade and they provide some nutrients to the soil. So I see this as an advantage when I compare with some other materials that are problems, real problems.
Okay. Thank you very much, Prof. All right, because we are limited of time, so thank you very much for your amazing presentation and sharing knowledge. And then thank you again, Prof. Agnieszka. And then we proceed to proceed to the invited speakers, IP77. Okay, Dr. Zayana Oman. Okay, she will be presenting the title of Influence of Reaction Viscosity on the synthesis of unstructured PMMA in the development of flexible membrane. Okay, please, Dr. Zayana. We cannot hear your voice. Okay, Dr. Zana, we can see your screen, and please start your presentation. We cannot hear your voice.
Sir, I think mic is not working.
I think Yahya.
Yeah.
There are some problem with her own mic, I guess. These
Okay.
are the technical leakage, I think each one is facing. This is due to COVID pandemic situation. We can say. So I think we are going to request the next one, you can say invited talk. If she is ready, then we can just swipe out this lady in next term.
Okay, all right.
Okay.
Okay, okay. Okay, Dr. Ziana, so we let you to present after this. Okay, I would like to invite for the invited speakers 78, Professor Simona Liguri. She will be presenting on the title of Engineering a Paradigm Shift in How We Think About Reactors, Metallic Membranes for Highly Intensified Ammonia Synthesis. Okay, please, the screen is yours. Prof.
Thank you everyone for inviting me. Can you hear me?
Yeah, clear.
Yeah, and can you see the screen, right?
All right, clear.
Perfect. So thank you today. And I'm Simona Liguri. I'm assistant professor from the Department of Chemical and Biomolecular Engineering at Clarkson University. And my research is more related to energy and environmental research. And in particular, today, my talk will be on metallic membranes for intensified ammonia synthesis. I mean, we are facing really big problem today, and the big question will be energy dilemma. Essentially, the question is like, it's better to have less energy, but we were in a better environment, or it's better to choose more energy, but we are going to waste our environment. Of course, I'm not here to choose one or the other one, because I'm the first one that I don't want to give up on the energy, you know, on the air conditioning, on the car, on the energy, I mean, on the Wi-Fi, on the computer. But we have also to think to the future. And so we have to think how we can produce energy, but not wasting the environment. And if we are going to see right now the world energy consumption, and we're going to do the projection, we can see that in 30 years, the world energy consumption will be double right now. And also, if we are going to check the CO2 emission, it is going to accumulate in the atmosphere from 1971 to 2016, we can see that there is a lot of CO2 accumulation in the atmosphere. And it has been shown that there is kind of connection between the CO2 emission and the global warming. And so essentially we are going to focus on making energy, but without without wasting the environment. So we have to remove the CO2 and we have to decarbonize our system. And so essentially it looks like the mission impossible, but I would like to say maybe impossible, because the idea right now is to limit this global warming. So we have to stay below the 2 degrees Celsius increasing. And in order to do that, by mid-century, we have to reach net zero CO2 emission. And we have the possibility, we have the technology to do that. In particular, we have 3 main routes for decarbonization. In particular, the first one is reducing the carbon-intensive product and service. So in particular, we have to reduce the heavy-duty transport, for example, air, shipping, heavy truck. We have to think a way on how to decarbonize this part, or we have to improve energy efficiency. And then we have to think a way on how to produce energy capturing CO2. So for example, we can produce electricity by electrolysis, by producing hydrogen. We can make hydrogen by biomass. We have to capture CO2 and we can use hydrogen. And regarding this last path, we have one technology that usually I call smart reactor technology, but essentially it's just a membrane reactor technology that allows us to produce hydrogen, to capture CO2, to start with the feedstock coming from biomass, and we can produce electricity, of course, by hydrogen. But why we need this smart technology? Can we just take the hydrogen as it is, you know, and use it? The problem is that hydrogen does not exist in nature as it is. So why we need an advancement in this area is because hydrogen right now is produced by natural gas steam reforming process. And it's a kind of process that takes place at high pressure and high temperature. In particular, the temperature is between 800 degrees Celsius and 1000 degrees Celsius. And it has different steps from the reaction, and then we have the purification and separation of hydrogen. Moreover, this kind of process has different limitations as thermodynamic constraints. So for this reason, we have to use really high temperature. We have mass and heat transfer limitation. We have a problem of coke formation. And as I said, we have several steps of hydrogen separation and purification. But as I said, I mean, my talk was related to ammonia. So now why I'm talking about hydrogen? So why there is this link between hydrogen and ammonia? I can say that approximately 55% of global hydrogen production is used in ammonia plant. So it means that most of hydrogen that is produced is used to make ammonia. And also to make ammonia is also an energy intensive process because this comes from Haber-Bosch process. And you can see here the pressure that is around 150 and 200 bars. So it's really high intensive pressure, and the temperature is mostly 400 degrees Celsius. And right now, ammonia is more used for agriculture. We use ammonia in order to, I mean, at the end, we want to eat. So we are going to use 85 of ammonia as a fertilizer. But now ammonia is raising a lot of attention because it is seen as an energy transportation, as an energy storage. Because yes, we would like to use hydrogen at the end of the day. So we would like to make hydrogen in a different way. The problem with hydrogen is that we cannot transport and we cannot easily store hydrogen. And so we are going to spend more energy in order to transport and store hydrogen instead of directly to build a new power plant, right, with carbon capture unit. But if we are going to make ammonia, we can easily transport and store hydrogen. And also where we need, so we can produce hydrogen on demand, we have a carbon-free energy. We have carbon-free hydrogen because when you're going to decompose ammonia, we only have nitrogen and hydrogen. The problem with ammonia is that we are already producing a lot of ammonia due to the fertilizer, and it's causing 1.2% of global CO2 emission because in any case, we are emitting CO2 and also is taking 2% of global energy demand. So making ammonia in a different way would be really a key point here in order to make a different energy in the future. And so my research is devoted to intensify the overall process of ammonia production. I'm going to produce hydrogen in a small device that is called membrane reactor. And that is like, and I'm going to show you right now, that is a kind of device that allows for reaction and separation in the same unit. So I can produce hydrogen right away. I can separate the hydrogen right away that I'm producing, and then hydrogen will be fed in another part where we can produce ammonia at different temperature and pressure in overall. So what I'm going to do right now and what I'm going to show is just the combination of these two big processes. And of course, this is not for replacing the power plant that are right now, but it will be just for small scale. And so why we need this smart reactor? As I said, this membrane reactor is a tool where there is a synergy between reaction and separation. So reaction and separation takes place in the same unit. And so just because there is a separation, it's an open system. So we will not have thermodynamic constraint. We could have higher conversion with respect to conventional working at the same temperature. We can have same conversion at lower temperature. And at the same time, we can have two output from this membrane reactor. One output will be pure hydrogen, and the other one will be a stream mainly composed by CO2. And I'm going to show you what does it mean. And this is a clear example of process intensification. So if you remember that natural gas stream reforming reaction was taking place at this operating condition, now we are going to cut in half the temperature, and we're going to reduce about 1/4 at least the pressure. And so how essentially it works. In order to make hydrogen, we can come from natural gas steam reforming, where we have methane plus steam that is going to produce hydrogen and CO2. So what happens is that we have the feed in the system, and then the feed, methane and steam are going to react with where, and they're going to meet the catalyst, so where they are going to react to form hydrogen. Hydrogen can permeate through the membrane, and only hydrogen can permeate through the membrane. And then with a kind of sweep gas, we can collect hydrogen and we can remove out of the system. And then from the other side, we will have a stream that is mainly composed by CO2. And so at the same time, we can, separate CO2 from hydrogen, we can capture CO2, and we can use hydrogen for other purposes, such as, for example, making ammonia. But as I said, this membrane reactor can give us better performance in terms of conversion, and also we can separate and pure hydrogen, but what it essentially means, right, from a mathematical point of view. So if we're going to make a plot of endothermic reaction, here we have the thermodynamic equilibrium. So if we're working at this temperature, the maximum conversion that we can get will be almost 0.6. But if we are working in an open system, such as the membrane reactor, we can get at the same temperature higher conversion. So it will be 0.9. Or, for example, we can fix our convection to 0.4. But instead of to work at high temperature, we can just work at lower temperature. So this technology gives us a lot of benefits. And one of these, as I said, better performance, and the other one will be like making pure hydrogen. But how is it possible that we can make pure hydrogen? We can make pure hydrogen because we're going to use a membrane, most of the time is palladium-based membrane, that allows only for hydrogen permeation. And this permeation takes place through a solution diffusion mechanism, where hydrogen is going to absorb on the metal, is going to dissociate, and then it's going to diffuse through the bulk. And then we have the recombination and we have the desorption of hydrogen. And the math that is behind this mechanism is just written here, where we have the hydrogen permeating flux that is equal to the permeability divided the thickness. And the permeability is a kind of parameter that is intrinsic to the material. And then we have our driving force. And the driving force is dictated by the partial pressure of hydrogen in the right-handed side, that is this one, minus the partial pressure of hydrogen in the permeate side, that is this other one, elevated to N. N is called dependence factor, that is going to correlate the hydrogen permeating flux with the driving force. And usually this N is going to vary between 0.5 and 1. And when it's 0.5, then it means that the limiting step about all this step is just the diffusion through the bulk. And when it's 0.5, this equation is called Seaver law equation, temperature constant. I'm reporting this equation because it's really important to catch what are the operating conditions that are going to affect the permeation of hydrogen. So if we would like to increase the hydrogen permeating flux through the membrane, we can work with really thin thickness of membrane, or we can work with really high pressure on this side, but consider that the driving force is the partial pressure. Or we can just use the lowest pressure here in the permeate side, and the lowest pressure can be reached by using a sweep gas. So by decreasing this term or by increasing this one, we can increase the hydrogen permeating flux. As I said, we can also work with the thickness, but sometimes we don't want to work with a really thin membrane. Otherwise, when we're going to have a really different pressure or high different pressure, the membrane just collapses. Also, the temperature has a role in all this system, and the pressure is inside the permeability, because the permeability is a kind of function of Arrhenius law. So if you would like to understand how the temperature is going to affect, we have to watch the permeability. And we can see that by increasing the temperature, the permeating flux also increase in order exponential. So the main parameter are thickness, temperature, and partial pressure of hydrogen in the permeate and right-hand side. And please keep in mind, because I'm going to show later how these parameters are going to affect. So the outline of my talk will be really a big, broad picture with some experimental results. And so the motivation why and how to power sustainable future, I think that I already talked a lot about this one in the first part of my talk. But now I would like to show, is this membrane reactor is a feasible technology? And is it possible to really produce ammonia synthesis by using hydrogen selective membrane, and how? So I'm going to show some experimental results, and then I'm going to briefly give some opportunities and challenges. And so the first one, as I said, I already talked about, and I would like to talk about the feasibility of this technology. So there is a lot of research in this field about palladium membrane reactor in literature, in particular for palladium membrane reactors in 1976. And so essentially the idea in my work was like, okay, now we know that this membrane reactor technology is working. So we can feed methane, we can produce hydrogen, but how much hydrogen? How can I really go from the small scale to the upscaling? And so what we did, we built this module with 12 tubes and with 12 membranes, and we were able to produce 7 kilograms per day of hydrogen. What does it mean, 7 kilograms? You know, I always like to give some comparison. So if you think that 5 kilograms of hydrogen can feed a car for 350 miles, so it means like around 500 kilometers. And if you run about 6 miles per hour, it means that I need at least 4 or 5 of this module in order to run the 300 miles, 350 miles. And 4 or 5 modules of this one, and there are like this big, are not so bad if you're going to put in a car, and we can have hydrogen on demand. So we're going to feed our car, we are going to the fuel station, we can put methane, and then we can run a car for 300 miles. And the cost of this membrane module is not so bad if you're going to compare with the steam methane reforming plant with conventional separation purification system. It is called pressure swing adsorption, where there is no carbon capture and storage. And so here is the cost of normal power plant. If you would like to add the carbon capture with the solvent base that usually is amine, then the cost is going to increase. And this system, by doing technical economic analysis, was not so far away from the steam methane reforming plant with carbon capture storage. Of course, we can also have water electrolysis. I'm saying that palladium membrane reactor could be in the portfolio on making hydrogen. I'm not saying that it's the best and we can use just that one. I'm just saying that it's in the portfolio. We can also use water electrolysis for making hydrogen, but the cost, of course, is different depending on where the energy is coming from. But as I said, we are working with palladium membrane, and palladium as a material is not so easy to find. It is a rare material, and the palladium production worldwide is around 200,000 kilograms per year. So how much palladium would be required for an industrial size hydrogen plant? So if we could take an example of a power plant in California, the Chevron power plant, and we would like to substitute, to retrofit this power plant with membrane reactor, and we would like to build membrane reactor of 5 micron thickness, we need 8,000 square meters of area. So it means that by doing some calculation, we will need 480 kilograms of palladium. That is almost 4% of US domestic production and 0.2% of the world production. And this is just for one power plant. So the idea of retrofit on the power plant, I believe it's not feasible. So this technology will be really feasible for small application. And so I talk about hydrogen. I said we can really intensify the natural gas steam reforming process, the one that I showed before for producing hydrogen in just one tool. But now let's see, is it possible also to produce in the same device ammonia? And so by using a hydrogen selective membrane. So essentially the idea is to combine membrane catalyst for hydrogen selective and ammonia selective catalyst. And here was the plan in the lab. And we divided the project in 3 phases. In the first phases, we wanted to show that this membrane reactor, if we are going to deposit a palladium metallic layer on a porous support and we were feeding hydrogen, and we were packing ammonia catalyst, commercial ammonia catalyst in the permeate side, we were able to produce ammonia at certain temperature and pressure. And the first phase were really promising because we got it really good results. And so we were able to produce ammonia. And the second one, the second phase, sorry, I just lost you as a connection. Let me start. And the second phase was feeding was packing also in the retentate side the catalyst and to produce hydrogen, and then hydrogen was permeating through the membrane, and then we were feeding ammonia. And so we made ammonia, we produce ammonia. And so what we had that we produce ammonia, great. So we were able to intensify the process. But unfortunately, the ammonia production that we produce in this system was not the same of the first phase. And so we thought about that maybe was the problem of the catalyst and hydrogen that was coming in and then was not seeing completely the catalyst. So what we thought was like, okay, let's deposit the catalyst in the pore of the support. And this is still a work in progress. So let's see the first phase where we just make the membrane with electrolyte splitting, and we made palladium gold membrane supported on a porous stainless steel support. And then we put this membrane in a membrane module. We build our setup. So here we have the feed zone, here we have the preheating, we have the membrane reactor, and then we have the analysis zone. And we work at different temperature and at low pressure. And you can see how we cut the temperature in half, and now we cut the pressure about one order, more than one order of magnitude. And the pressure in the permeate side was just kept at 1 bar. We studied the effect of the temperature and the space velocity. So what we found that by increasing the space velocity, the ammonia production rate was going higher. This was due to the fact that by feeding more reactants in the system, more ammonia is produced. But regarding the temperature, you can see that also by increasing the temperature, the ammonia rate was going higher, which is pretty, at the beginning we thought, okay, this is pretty weird because ammonia reaction is exothermic reaction. So if I'm increasing the temperature, it means that the ammonia rate should go down. But this was not the case, because if you remember that the temperature is going to affect the hydrogen permeation through the system, and if we are going to increase the temperature, it means that more hydrogen can permeate through the system. It means that we have here more hydrogen in the system. So in this case, the hydrogen permeation is prevalent with respect to the thermodynamic effect. So for this reason, we have that by increasing the temperature, we have an increasing of the ammonia rate. So we were really happy that we were producing ammonia, and it was not so high, but still high enough to say, hey, we can produce ammonia at certain temperature, but at 10 bar and not 150 bar. And then we thought about, okay, so now let's go to the second phase. So let's add the commercial catalyst in the retentate side, and we can run the methane stream reforming in the retentate side and see how much hydrogen is going to permeate. And then we can feed nitrogen as a sweep gas. And then with the catalyst available, we can produce ammonia. This phase was divided in 2 parts. In the first part, we just run the reaction because we wanted to understand by changing the operating condition how much hydrogen was permeating through. Because as I said, the hydrogen permeation is going to depend on the pressure, on the partial pressure here, on the partial pressure in the permeate side, and also on the temperature. So we ran some tests in order to understand what was the best results. And then what we did was just substitute the sweep gas that was at the beginning and inert with nitrogen.
Prof, you have 5 minutes left.
Oops. Okay, I'm just going to run. And so we did some tests, and we kept the temperature at 430 bar. And so what we found that by increasing the sweep flow rate, the sweep gas, so it means that we are going to decrease the partial pressure of hydrogen in the permeate side, we are going to increase the driving force of hydrogen. And so we found that this high sweep gas flow rate, we can get 90% of conversion of methane and 75% of recovery of hydrogen. It means that the 75% of hydrogen that is produced in the system permeates as pure in the permeate side. but how much it was like 63.1 milliliter per minute. And so what we did, now that we know all the operating condition and we know exactly how much hydrogen, we did the ratio between 3:1. It is the stoichiometric ratio for making ammonia, and you can see the reaction here. And so we ran the reaction, both reaction at the same time, and we made ammonia. We made hydrogen, and simultaneously we create ammonia. And this was 2.5. You can see that 2.5 with respect before was lower, because before we were able to reach 8 millimole per gram per hour of ammonia, but we were still satisfied. And you can see here in this table some comparison with the literature. So we were happy about producing ammonia, but at the same time, the ammonia rate was really low. So what we thought that maybe the reaction was limited in the permeate side. And so the idea was to substitute the catalyst, the commercial catalyst, by making our own catalyst, by depositing the catalyst inside the pore of the support. But in order to see if it was working, we didn't deposit at the beginning the membrane layer. And so what we did, this was the Princeton tube, and this was the tube with the deposit catalyst, and it was ruthenium. And this was the experimental setup. And at the beginning, we prepared the catalyst and we characterized the catalyst. And from the literature, we saw that if we are going to add some promoters, for example, cesium, potassium, barium, the selectivity of ruthenium towards ammonia is going to really increase. So what we did, we'd also add some promoters. And here in the first part, we just produce ammonia. We made just a pure experimental test with just ruthenium and the support. And we choose two different support. Y and Z, it's a support, and alumina. And we saw the Y and Z has higher performance with respect to alumina. And then we did other tests with the promoters. And we can see that promoters increase rate about 5-10-fold with respect pure ruthenium. You can see here 20 at 450, but if we are going to add cesium, you can see that the rate of ammonia is almost 500. The problem with cesium, that is really active, and then we have barium and potassium, is that although it's really active at the beginning, after some time it's going to decrease. But regarding barium, we saw that it's pretty stable along the time, although it's really slow to be activated. And regarding the ammonia process, we are just making some intensified ammonia process, and the work is still in process. So in synthesis, we were able to combine everything to intensify the process by using hydrogen permeable membrane. And if before the mission seemed impossible, now it really seems possible. And the DOE estimates that using this membrane reactor could save around $1 billion per year. And regarding the benefits, you saw that we have a lot of opportunities in the use of this kind of system. Of course, there are still some challenges like palladium availability, so we are trying other different material, and we need a more stable and active catalyst. And of course, the design is going to play a role in everything. So I hope I didn't go fast in the last few minutes, and I'm glad to take any kind of question. Thank you.
Okay, thank you very much, Prof. Simona. Okay, okay, there is no question from the chat book. So I have one question. Okay, how much the energy efficiency when you're using this production technology?
We didn't start yet, but the idea here is not taking the energy, because in any case we need a compressor. We need, in any case, to reach at least 5 bar. We need to get 400 degrees Celsius. So now the next idea is to take some hydrogen from the membrane reactor. Some part will be used for ammonia production. Another part will be used as to make energy. So the next idea is a kind of project with a mechanical engineer where we're going to burn hydrogen in a gas turbine that is going to, well, in a boiler, and the boiler is going to make steam, and then we're going to feed the steam in a gas turbine in order to make energy. Of course, the efficiency we didn't calculate yet, but it's still work in process. This was more a kind of proof of concept, and we were able to be there. And so now there are a lot of questions that, of course, come in the mind as energy efficiency. Yeah.
Okay, thank you very much, Prof.
Thank you,
Simona,
Hod.
for your amazing work you have presented and
Thank
very
you.
nice
Yeah.
Yeah. One more question from Prof. Pramod.
No, it's not a question. I think for USA, I think Simona is presenting, so I am thankful to her because we guess that time in the USA is very hard right now. Simona, so personally on behalf of, you can say, conference organizers side, I am thankful to you because I saw from morning time till evening, you are presenting in our conference. So we are going to invite you also your comment on validity session if you are available. Thank you.
Thank you so much. I really appreciate it. Thank you. You're always so kind. Thank you. Thanks a lot.
Yeah. Thank you very much.
Thank you. And thanks for inviting me. Thank you. I'm just going to stop sharing.
Okay, so we go back to our last the presenter, Dr. Zayana Oman. I hope this.
Yes, the voice. Do you hear me?
All right. Okay. Very clear. Very good.
Yeah.
Okay,
now we got Zayana. It's okay.
The screen is yours.
Yes. So do you see it?
Yeah.
Okay.
Yeah.
Alhamdulillah. Good evening, everyone. I am glad today to be on one of the participants in the 4th online international conference on science and engineering of materials to present my paper entitled Influence of Ionic Liquid Properties on the Synthesis of Unstructured BMMA in the Development of Flexible Membrane. My name is Zayana Saif. I want to take the opportunity to tell you about Oman. Is a country on the southeast coast of Arabian Peninsula, situated in Southwest Asia, bordering the Arabian Sea. This is the Arabian Sea and Gulf of Oman and the Persian Gulf. It is between Yemen and United Arab Emirates. The coast of Oman was an important part in the Omani Empire and Sultanate. My presentation outline will be introduction, methodology, results and discussion, then conclusion. Our study is based on polymer electrolytes, which are considered to be the most promising electrolytes for potential application in various solid state electrochemical devices. The main advantage of polymer electrolyte against the conventional liquid electrolytes is that there will be no leakage of corrosive liquid that might cause damage to the device and sometimes may cause danger to the user when it explodes. Our polymer host is BMMA, which has been choice of many researchers due to its stability towards lithium electrode. This can be only achieved when it fabricated in film form. Unfortunately, most BMMA films fabricated from commercial BMMA are brittle due to its polar nature that is prone to form hydrogen bonding between its chain. Therefore, several modifications have been made to overcome this brittleness of BMMA, such as blending with another polymer, addition of plasticizer, addition of filler, limitation, and addition of salt radiation. However, unfortunately, they face some limitation like poor mechanical properties, agglomeration, not homogeneous blending, retarding effect, induced cross-linking, and low ionic conductivity. So nowadays, they are trying to use ionic liquids which are sold in liquid form in temperature room, because this exhibit plasticizer-like characteristic and has many properties such as high ionic conductivity, non-volatility, high thermal and chemical stability, and lower melting point. So after from literature review, after incorporating the ILs in BMMA-based electrolytes, the ionic conductivity has been enhanced. However, most of them are in gel form. Our study is based in a solid form because gel electrolytes have some drawbacks like Bohr mechanical stability, Bohr mechanical strength, and Bohr thermal stability. So they tried to make the solid BMMA after by incorporating ionic liquid, and unfortunately the ionic conductivity is still low. Therefore, synthesizing new solid BMMA is needed, which is our main objective. From literature review, they used several types of polymerization to polymerize MMA in ionic liquid. The free radical polymerization is the most widely used because it is the simplest technique and compatible with a wide range of monomers having different types of functional groups. Moreover, it has the possibility to obtain high molecular weight of MMA. However, not all free radical polymerization of BMMA containing IL were successful. Sometimes a solid BMMA can be obtained from the polymerization. Hence, BMMA film cannot be fabricated. Unfortunately, factors of the compatibility between MMA and ionic liquids has not been widely discussed in detail. Most studies reported that the viscosity of IL is the main contribution to the feature of the polymerization. So therefore, in this study, apart of studying their viscosity effect, other properties like their density, type of cation, and the size of the cation and the molecular weight also investigated and discussed in detail. So for this purpose, we use 3 ionic liquids with the same anion and different cation. And the chain of the cation is also different. These ILs exhibit different distinguished physical properties. Also, these ILs has not been used in the synthesis of BMMA via free radical polymerization. Therefore, it is an additional information on the potential of these ionic liquid as hydrogen bonding inhibitor as well as doping material since they are ionic solvent. Note that the results obtained in this study were compared with the similar studies done by Zailani 2019, which used this ionic liquid that has the same anion, but the cation is different. To add more information for this study. So our work is to we fix the amount of ionic liquid and the amount of initiator and the amount of MMA to study the effect of IL in polymerizing MMA. Then we stir the mixture until dissolved. Then we heat the mixture in the water bath at 80 degrees Celsius until solidified. The solid form of BMMA-IL further characterized using this method of characterization, NMR or MGBC, TGA, DSC, and FTIR XRT. So our results, we got only solid and transparent production only when we use IL-1, which the other one are incompatible with MMA and are in gel-like or sticky. Therefore, we studied the effect that can, the factors that affect on the synthesis of MMA-IL. The first factor is the viscosity. Note that in this polymerization, the ILs became the polymerization media. Hence, the viscosity of the reaction system is corrosion because it will affect the mobility or diffusion of the reactants to react with each other. From the table, we see that IL-2 exhibit the highest viscosity among the three ionic liquids, which may generate large viscous reaction medium. Highly viscous medium have been reported to reduce the initiator efficiency by impeding the diffusion of primary radicals. This is because viscous medium becomes hindrance to the mobility of the reactant radicals to polymerize. In addition, in a highly viscous medium, it is more difficult to release the heat from the polymerization, hence raising the temperature of the polymerization system, which may eventually cause the oligomers to disintegrate again. And also when the viscosity is too low, like this IL-3, it was difficult for BMMA to absorb the IL during the polymerization because it is too showy. And previously, as we said, we will compare this with the Zailani study. BMMA has been successfully synthesized in the presence of this one, which has the lower viscosity than IL-3. So we can conclude that the viscosity is not the only determining factor to ensure the success of polymerization reaction. So the density and the size of cation may also affect the polymerization process of MMA, which we'll discuss in these slides, the following slides. The viscosity, we get the difference viscosity between MMA and the ionic liquid. The difference in the density of the two, the difference in the density of the two liquids will determine the degree of miscibility of the two. It was found that the density of MMA, it is the lowest, hence it will be on the top layer of the solution mixture. Since IL-1 has the highest density difference, therefore its polymerization system is the least homogeneous as compared to the other polymerization system containing IL-2 and IL-3. Therefore, it can be suggested that less MMA radicals are able to be trapped into the viscous phase of IL-1, and more free MMA radicals are able to polymerize with less hindrance at the surface. Interestingly, it can be concluded that the polymerization of MMA is not possible in low viscosity and density of IL, like in the case of IL-3. This may also explain why the polymerization of MMA in a less viscous medium of this ionic liquid is successful. It was found this to be more denser than IL-3. Hence, it can be concluded that the density of the IL is more crucial in ensuring the success of the polymerization reaction. The other factor that affect the polymerization of MMA and IL is the cation structure and its length. All the selected ILs contain siloxene groups with different chain length. It was found that IL-2 and IL-3 contain longer siloxene linkage that may cause hindrance in the diffusion of the monomer radicals to polymerize. This factor may also add to the success of polymerization of MMA in Zailani study that consists of shorter siloxene chain length. In addition, these siloxene groups are prone to be attacked by the initiator, hence produce siloxene radicals, and hence the longer siloxene chain in IL-2 and IL-3 may produce more siloxene radicals. These radicals may form larger molecular structure of IL, hence become hindrance in the dispersion of MMA radicals to polymerize. addition, with the limited amount of the initiator, some MMA monomer may not be initiated. Hence, shorter BMMA chain length is formed. The monomer has to compete with siloxane groups in order to be initiated. Therefore, it seems in this study, the initiator more favored to attack the siloxane group than the monomer. Hence, less monomer has been initiated. Also, molecular weight and cation structure is related to each other. So we notice from the table that IL-1 and this Zailani IL has the lowest molecular weight amongst the other ILs, which indicates that the smallest IL structure gives less hindrance to the monomer radicals to diffuse and polymerize successfully. So after we get the result, the projection, so we determine the solid PMMA IL properties. From NMR, we saw that the IL peaks appear in PMMA IL-1. That means that IL-1 has been successfully incorporated in MMA matrix. And also there is some changing in the intensity and shifting of the peaks, which which indicate that there is an interaction between BMMA and ionic liquids. This can be further confirmed from FTIR study. We saw that the intensity of the polar groups in BMMA has been changed, and the peaks of IL has been appeared in BMMA matrix. So this confirmed the successfulness of incorporating IL between BMMA chain and reduce, as we see from here, reduce the hydrogen bonding between BMMA chain. And this also confirmed the successful of producing BMMA IL. And also from OM study, more smoother structure we got after incorporating IL-1 between BMMA chain. That's indicating that the bulky structure of IL-1 managed to reduce the hydrogen bonding between BMMA chain by placing themselves between the chains. As we see, the cracks from BMMA IL-0 without ionic liquid has been reduced. This makes the thermal stability of the BMMA IL increase and the TG also increase due to the interaction between BMMA and IL. Also from XRD study, upon the addition of IL-1, the crystalline peaks of BMMA became broader, suggesting that when IL-1 occupies the space of the polymer matrix, it interrupts the ordered array of the polymer chain, hence reduce its crystallinity. This can be confirmed from the crystallized size. It reduced when after incorporating IL-1 into MMA matrix. With also inducing IL to the polymer matrix, the molecular weight increase, which indicate that the addition of IL-1 has increased the polymerization rate of the system, and this suggesting that when IL-1 occupies the space volume between the reaction media, it limits the distribution or the diffusion of the monomer radicals. Hence, their monomer radicals became closer to each other, and this the growing polymer chain became rapid, which increased its propagation rate. The newly synthesized BMMA IL-1, we fabricate it into a film by using solution casting technique. Although it has the higher TG, than BMMA IL0. It produced a more transparent and flexible film than BMMA IL0. Therefore, it can be concluded that TG is not the main factor that contributes to the flexibility of a film. The higher TG obtained can be compensated if the polymer amorphous. The stiffness of any material is related to its ordered crystalline structure. In addition, it was realized that the strong dative bond between the polymer and IL1 was not as strong as the intermolecular hydrogen bonding. Since most polymer electrolyte hosts are polar in nature, it is the best overcome to its strong intermolecular bonding in order to obtain a more flexible film.
Dr. Ziana, you have 5 minutes left.
Okay. So this study contributes to the OM morphology of BMMA-IL film. We saw that the grains that we observed in the BMMA-IL0 show grains with different orientations, and these grains reduced when after incorporating IL due to its ordered crystalline structure that has been disturbed of MMA chain. So this study contributes to new knowledge on how other properties of IL, such as its density, the type of its cation, and its molecular weight, affect the polymerization of PMMA. We have free radical polymerization and its role on the development of thin film electrolytes. It may also provide new potential electrolyte material for solid-state lithium batteries. So the synthesis of MMA in IL media is not only dependent on its viscosity, but also on other factors like density, cation, type of cation, its size, and its molecular weight. It was found that the density and the size of the IL are the major factors that contributed to the success of the BMMA polymerization. Also, the presence of groups that are prone to be attacked by initiators should be avoided. Therefore, in this study, only IL1 has been successfully incorporated into BMMA matrix. Hence, more flexible and transparent film obtained. And for future work, we are going to increase the concentration of IL1, which may produce more flexible BMMA IL1 film. Thank you.
Okay, thank you very much, Dr. Zayana, for a very nice presentation. Okay, there is one question from chat box. The question is, for the electrochemical devices, which kind of ionic liquid is preferred, whether hydrophobic or hydrophilic?
Hydrophilic, ionic liquid.
Yeah.
Sorry?
Pardon? The question, which one kind is ionic liquid is preferred in electrochemical devices?
Hydrophobic one.
Okay. Okay. Thank you.
Thank you.
Okay. Since we have late from the time. So thank you very much again, Dr. Zayana, for your amazing work. And then thank you very much. And then I give back to the organizer this session, okay, to proceed the next our validity session. Okay.
Yeah, I think thank you, Yahya bro, to finishing this one in on time. And now I am, you can say, pilot of this aeroplane. So no need to worry. And I think I am also thankful to Jana. At least the last moment we can find you. There are some problem with internet connection, but these kind of things already, I think it's now happening whenever we are going to organize any conference. So from our side, we are thankful to all of you to join this conference, and particularly on conference organizer behalf, I think I am thankful to Professor M.J. Yahya, who is my close friend, to at least pass such a long time just to sit and judge. It's a very difficult task, but I am thankful that you are so close to us. So using such kind of personality, we always feel relaxed because we are managing everything from India. And now we can, you see, after collaboration, these kind of things, we are also managing very well by these, you can say, my own colleagues and my friends like you. So I am especially thankful to Professor M.J. Yahya to chair this session. Thank you, bro. And I think we are going to meet in coming time after COVID pandemic situation.
Of course, bro. Most welcome, bro.
Yeah. And I think now from our conference own side, I am going to hand over these mics to my colleagues, maybe Dr. Geeta or Dr. Venus. We are going to just start validatory session within 5 minutes, you can say. So we request all of you to be here with us if you have free time. We want your opinion and your beautiful thoughts so that we can improve yourself in coming time. So thank you everyone, and we are going to start validatory session within 5 minutes. Thank you.
मेरे को बना दो, मैं भी नहीं मैं तो पोस्ट ही निकला मोहित कुछ बोलो।
नहीं ये जो वीडियो चल रहा है इसकी आवाज नहीं है यार हेलो
Tejas, you want to speak something? You can unmute yourself.
A very good evening to all. Welcome to the valedictory function of 4th International Conference on Science and Engineering of Materials, organized by School of Basic Sciences and Research. Just give me a second. Altogether, there were 32 countries who participated from all parts of the globe in this conference, and 5 plenary talks were given. Altogether, there were 81 invited talks and 176 oral presentations were scheduled. Total of 260 presentations were the part of this particular conference, and out of which 251 presentations were made, which is a mega marathon of presentation. The papers that are presented here will be published, will be peer reviewed and published in the 8 international journals. And the organizing committee is requesting you to have some patience. They'll be contacting you back for the manuscript. And Professor P.K. Singh sir will be talking a little bit about the Center of Excellence on Solar Cells and Renewable Energy. He will be coming back on this shortly. We welcome the suggestion and feedback, because without that, there is still there is still hope. There is still a lot of scope of improvement, and we request feedback, and we would like to invite some of you to say something. I think Professor Bhaskar Bhattacharya was here, and he has been our mentor, and we will start from him. Professor Bhaskar Bhattacharya, we would like you to say a few words. Yes. Yes, sir.
Thank you, Dr. Venus. It is really a pleasure to talk to you people anytime, any day. As you said very rightly, it was really a marathon conference. Excellent efforts, because contacting so many people and connecting them, especially scheduling the program in such a way that there is no time gap and everyone could speak in proper time and proper schedule. That is really excellent. I congratulate you all for such nice arrangement. This conference, as many of the participants may recall, we started in 2014. The first one was held in 2014. We had around 300 people gathered at Sharda University campus. The second one was 2018. By that time, I left Sharda University and shifted to Varanasi. But anyway, that conference was also the second ICSEM. And now we are witnessing, we just witnessed the fourth ICSEM. The number growing like anything. Moreover, the academic rigor, which is expected from a conference, that is very much high and very in the hot atmosphere of India. It was really hot academic discussion, and I don't have words to appreciate the efforts of the organizers, my friends, P.K. Singh, Venus, Mohit, Munendra, Sandhya, Anindita, Sunil, Pandeji, and many, Geeta, and must be many people who are always behind the scene and not coming in front. Oh, somebody messaged, Shamsuddin is also joined, the participant in the conference. Great. This time, though it was very difficult because everything virtual, the platform virtual, nobody sitting in front and talking to someone not looking at is a bit odd. But anyway, the arrangements were very nice. I hope the papers which shall be published in different journals, that will also add up a grade to the academic, the scientific community. Venus, to make some comments. I should make some.
Yes, sir.
Some,
We
some,
want that, sir.
yes, some comments also. It is not good to comment on friends, but anyway.
But we would
Comment.
like to have those suggestions, sir.
Yeah, that is regarding the schedule. Though you people have managed very nicely, especially for different countries, the timings are different. So accordingly, you must have planned. But still, there were certain overlaps. So in the future conference, please take care that overlaps, such as a speaker in one session is the session chair in other session. These things should be avoided. If there is any change in the schedule, it happens often that due to some or the other constraint, we need to change the schedule all of a sudden. That should be flashed. That should be flashed so that everyone can know that what type of change is happening and what change has happened. Because careless people like me, we just put tick that, oh, I want to attend this talk and I want to attend that talk. So when you switch from one classroom to the other, then you find that, oh, that lecture is over. That gives something, I don't want to use odd word, but that is not good. So please, in future, whenever you please see that it happens.
Yes, sir.
And what else? That's all. Thank you very much. Thank you very much for inviting me to talk to you people once again, talk to many people. I can see 121 participants joined now. So congratulations to you all. It was a really pleasure to talk to all of you, the scientists, participants. And personally, I feel that this time I had the chance to, sit and listen many people, because when you are the organizer, you don't get time to sit inside the conference hall and listen to people. So this time I got that chance because I am away from you people. The burden was onto your head, so I was enjoying talks. I hope the participants from different countries means that we will have more channels open for international collaborations, students exchange, and further improvement in our research capacity and caliber. Good luck. Thank you.
Thank you so much, sir. Thanks for the words of appreciation as well as suggestions, because suggestions always improve us. We apologize for the inconvenience that was caused to you due to switching off the session and not finding that all. We really, from the heart, we apologize for that. But we'll make sure that the session are scheduled in such a manner that if there is any change, we are flagging that on the website. We apologize once again for the inconvenience.
Oh, you need not to apologize. It is a matter of, you said that I need to comment, so I made that comment, and I am sure that in any future endeavor, you people will take care of these things.
Yes, sir. Yes, sir. Sure, sir. I can see Professor Neelam Shrivastava. Ma'am, will you please take over the platform and say something? This time we could not meet physically, but we would like to have your overview. Professor Neelam Shrivastava? I saw her, yeah.
Thank you, Professor Venus. It's really very nice to be a part of your
Ma'am, just 1 second. Can you keep your microphone close?
Okay, sure. The same problem yesterday also during my presentation. Slow voice, sorry. Okay, thank you very much, Dr. Venus. And it is always what to say, very nice feeling for me to be a part of your conference. You people organize the things in such a nice manner when it was offline at that time also, or even in this pandemic situation when you are making all these things in the online mode. I should say that means marathon effort. You people collect, you tried so hard and collected so many participants, starting from the plenary talks, keynotes, and invited to the participants, oral participants. very large number of people participated in this conference, and you people managed in a very nice manner. The breakout room concept and everything you managed in a very nice manner. Of course, the thing which Professor Bhattacharya mentioned, that that is a point. I think that he has already told about that. And of course, in the when you are present collaborating so many people, then it is really difficult for us also to choose to listen whom and who to leave whom. Yes, so such a means so many nice talks were there. So it was really a, I can say that it was a problem for us to select whom and not to listen whom. So it was really means a credit to you, all of you, and it was always nice to be a part of your conference, and credit to all the organizing teams. Thank you very much.
Thank you so much, Professor Srivastava. It is always nice meeting you through the conference. Thank you so much, ma'am, and thanks for your feedback. We would like to invite Professor Simona Liguri. Ma'am, can you please say a few words? How was your experience attending this conference? Yeah.
I mean, you did really a great job. I mean, organizing a conference online, putting together really people around the world, because I was seeing from India, Malaysia, Brazil, the United States. Of course, choosing the right time is not so easy, but you did really a great job. I mean, nothing from the beginning, since when you invited all these amazing speakers. I saw few of them, unfortunately, due to the time. It was 1 a.m, so I could not wake up most of the time. But I saw a few of them that were amazing. So you did really great. I don't have future suggestion unless did the same for next time. I mean, I think that also the other professor suggests the same. So you did really great. And I'm not here just to, say, hey, yeah, great, what we can improve. But if I don't see any black spot, why I have to make the black spot? But really great job to the organizer. I know that I organized the conference internationally, and it's not easy, above all during the pandemic, above all the schedule of the people. So, and the marathon was really good because it was really 3 intense days that you can focus there. And you can really see all the research, and you can say, oh, wow, I can make a connection. Oh, wow, yes, it's really cool. You were the portal of also other future collaborations. So thank you so much.
Thank you so much, Professor, for your kind words and your appreciation. Thank you so much. Now may I invite Professor Agnieszka Polika to say a few words and your suggestion, ma'am.
Thank you, Dilu. I share the same opinion as Simona. I am very happy to be here. I am very happy to see my friends and to meet other people too, and to see their work. And I had the same problem with the time. So the most of the presentation were during my sleep time. I could attend some of them early in the morning, and I was very happy to see such a high level of the presentation, and that gave us a new perspective for collaborations and for the research. I would like to thank also the organizer to let see some of the presentation to my students and my collaborators. So I think that this kind of conference is very useful and very nice because without moving from our place, we can see each other, we can interact, and we can exchange our point of views and our results. So once more, I would like to congratulate everybody, Professor Pramond, Professor Bhattacharya, and all the organizers and all the people who worked to meet us together. I know that, and you know how much work it needed, and I am very grateful to you for that. Thank you very much.
Thank you so much, Professor Polika, and thanks for making the effort and hearing the talks, even though it was sleep time for you. Thank you so much. Now, I would like to invite Professor Chin Han to say a few words. Professor Chin Han. Okay, if he's not available right now, may I invite Dr. Melissa? Dr. Melissa, she was here.
Venus, probably he has written some text. If you could read it out.
Okay.
It's in the chat box.
Okay, yeah, Professor has written, thanks to the organizing team for bringing their expertise and experience around the table and engaging in such fruitful, but this is not from him. But anyway, someone has written and I would like to read it. Thanks to the organizing team for bringing their expertise and experience around the table and engaging in such fruitful, constructive and open exchanges throughout the 4 days of the conference. It was wonderful and perfectly organized online conference. Thank you so much for your words of appreciation. If Dr. Melissa is there, we would like to hear some feedback and comments from her. I could see Dr. Shankarama. Dr. Shankarama, you were very active throughout the sessions. We would like to invite you to give your feedback. Dr. Shankarama, if you're here. Dr. Shankarama.
ऑर्गेनाइजर्स तुम लोग भी कुछ बोलो अपना एक्सपीरियंस अच्छा लगा बुरा लगा वीनस कितना परेशान हुई गीता कितना नाराज हुई कुछ तो बोलो
I would like
हिंदी में बोल रहा हूँ क्या कुछ बोलो
Geeta ma'am, ma'am, like to hear from you. Yes,
it was a wonderful experience, and I can recall the words you used to say ki, in this type of conference we are agitating our scientific minds, and we are really confronting so intelligent people around us that we actually learn a lot from them. And when we are physically confronting such scientific minds, then it's a different thing. But this kind of experience is also fantabulous. So this whole conference that was designed by Department of Physics, School of Basic Sciences and Research was fantabulous. And it's a great teamwork. PK sir has collected such a wonderful team, and I'm really grateful to him that he has considered me to be the part of this conference and this organizing team. So thank you so much, sir, and thanks to everyone who actually showers so much affection that we can actually hold such type of conferences.
Thank you so much, ma'am. We would like to hear from Professor M.Z. Yahya. Sir, are you here? If you can give some suggestions and feedback. Professor M.Z. Yahya. Okay, would like to invite Ms. Pratima. Ms. Pratima. Ms. Pratima.
Yes.
Yeah, would like to hear from you, ma'am.
Okay, thank you for giving me this opportunity to say my feedback about this great conference. Actually, I'd like to thank the organizer to give me this opportunity to be one of to opportunity to present my work in this conference. Also, I'd like to thank the conference committees for this very interesting and fruitful conference. Actually, I have one problem is the time difference. This is my it was my problem, so I missed many of sessions because the conference starts very early compared to my time zone. Very interesting time that I spent, and thank you, well organization. Good luck.
Yeah,
Okay,
thank you.
you.
So much. Yeah,
Okay.
thank you so much, ma'am.
Okay.
We hope that next time we are meeting physically so that there's no time lag or time difference. Or maybe while we were discussing amongst ourselves, few suggestions were coming that we can have it in 2 shifts. Okay, so we don't know. Okay.
Thank you. Bye.
Yeah, thank you so much,
Okay.
Fatima. And
I think, Venus, most of things related with time difference.
Yes,
but
sir.
I want to say that if there is a wish, we can interconnect, although there are time difference. So now see the thing in front of all us that now Malaysia is plus 2.5. And now if we are going to backside, like France and other is minus 2.5. So we are trying to make balance. So now you see, we are trying to make balance and we are collected such kind of nice people all around the globe. So in coming time, as everybody wish, maybe we guess that this COVID pandemic situation is going up. And we officially in position to say hello or hugging anyone. So take care, be patient, and I think we are going to again invite you when this COVID situation is going up.
Okay, thank you.
Now this Venus, I think mic is on your own hand.
Thank you, sir. We'll take a note of all those things and we'll see what we can do best in the next one. Is there anyone else who would like to say anything on their own part?
I think I'm seeing Noor or anybody.
Professor Noor would like to hear from you.
Dr. Venus?
Yes,
Professor MZ Yaha has sent a very long message in chat box, 5-6 point message.
Okay.
I think you must read that message.
Okay.
He has written very point-wise message.
Okay, I'll read that. I cannot read the last message that I'm getting is from Miss Simona.
No, it is not the last message. He has messaged at 4:53.
Okay.
At 4
I think Neelam did. If you are able to see, kindly help us.
I got it. Let me.
Venus, I have copied it at the end if you wish to read.
Okay. Shall I read it? I mean, if I have permission.
Yes, you can read it.
Yeah, firstly, a million thanks. This is coming from Professor MZA Yahya. Firstly, a million thanks to the organizer, especially Professor Pramod, for inviting me to join this conference. I would also like to congratulate again the organizers of the conference for organizing this such amazing online conference. This conference brings all the material scientists and scholars under the same umbrella, where they can interact and share their ideas. Even though the pandemic COVID-19 has limited the conference to physically be carried out, but the organizers proved that it can successfully be done via online with the involvement of the participants from 32 countries over the world. Nothing is difficult. If you make up your mind, anything can be done successfully. Lastly, to the organizers, keep it up to organize this amazing conference. Looking forward to physically meeting you all in the forthcoming 5th ICSEM in New Delhi. Thank you so much, sir, for your words of appreciation.
Thank you.
There are so many congratulatory messages coming from different people. Shamsuddin Mazu has written congratulations to both the presenters and organizers for the completion of the conference. Thanks to Sharda University and participants. From Hari Shankar Shyam, many congratulations to the organizers.
At the end, Pinakin Bhatt wishes to speak something. I think he has written, may I say something?
Yes, sir. Yes. We would like to hear from you. Sir, we invite you to say something. Professor Bhatt, we would like to hear from you.
Then there is a hand raised from
Yes,
Professor Gyanendra Singh. Yeah.
Gyanendra sir.
Hello, Dr. Venus, madam. Good evening.
Good evening.
Can you hear me?
Yes, sir. We can.
Yes, I am from Chhatarpur. You may not be familiar with this name, but it is known for World Heritage Khajuraho, close to Khajuraho. I motivated our students. I'm a teacher in a college. I motivated our students and myself too to expose them to the international arena, what type of discussions are going on and what is the level of research. So despite my all efforts, I could not devote that much time to attend all the lectures. But intermittently, I did join and found the most of the topics were very interesting, though they were not of our subject because we belong to geology and the topics were that of chemistry and other and physics. But nevertheless, the level of research that is going on there, my intention was to expose our students to international platform so that they can understand and make them familiar what is going on around. So this international conference has been extremely fruitful. I think 10% or 20% students that I motivated might have, changed their level of understanding. So I must thank the organizer for organizing such a wonderful conference. Thank you very much.
Thank you so much, sir. We are so much honored to have you and have your participation as well as from your students. It was very nice that you chose to participate. Thank you so much. There are a few more comments in the chat box from Siti Nural and Mohammad Zameen. Thanks, Professor Pramod, an excellent and friendly scientist. Thanks to committee of ICSEM 2021. Very helpful, and all of you have done a great job from Malaysia, UPM, University of Malaysia. Thank you so much.
Venus, Professor Bhatt is back. I can see him if he wishes to speak.
Yes. Yeah, sure, ma'am. Sure, ma'am. Professor Bhatt, we would like to hear from you, sir. Some suggestions, feedback. Professor Bhatt. Okay, anyone else would like to say?
No, I think he's speaking, sir. Your voice is not coming.
Professor Bhatt.
It is really a good conference. Without traveling, we can attend conference. This is a very comfortable way to attend the conference. Even more than 32 countries can participate in future if you organize like this way. So with sitting at our home or our working place, we can know the latest research work and we can be encouraged through this conference. So really, I appreciate all the organizers, and I will participate every year if you organize every time. So thank you very much.
Thank you so much, Professor Bhatt, for your kind words and appreciation. And indeed, this technology has taken us to this position. It has made us, it has empowered us. The technology empowers us, and technology gets empowered by the research. So definitely researchers have a big job to come up with latest technology, and we get benefited, although pandemic had brought a lot of bad phase in people's life, but we just look forward that things will change. We are looking forward to a changed world where there's no COVID. I just hope and I wish that. There are lots of, yes, sir.
We are seeing, I think, our old colleague, Divya. Now she is in USA. Divya?
Okay, yeah, Dr. Divya Singh, we would like to see you, ma'am. If you're there, we would like to see you and would like to have your suggestions and feedback. Dr. Divya Singh.
I think she did not want to talk with us. Anyway, we are moving on next one, Dr. Danaja. I am seeing also she is present. If she
Doctor,
want
sir?
to,
So, doctor?
Dr. D. Istula.
Dr. D. Stua.
Yeah, D-A-N-A-J-A, if you see.
Dr. D. Stua, if you're here, we would like to hear from you. Okay, sir, I am taking this time. Now I would like to say something. If you allow.
Okay. Yeah.
Bolo.
Yeah.
Kuch to bolo.
I just want to say that it was effort of many people together to put this in front of you all. I would like to really appreciate all our research students who work day in, day night to help us out. And if it is coming up, most of the time we are the ones who are speaking, but there are lots of students who have worked really hard, and it included making phone calls also. And if you can see that they were lined up presentation, there was not a gap of even 1 minute if you talk about the oral presentation. So it was the effort of so many students who were making calls to the people. And yes, time difference was also there. So these people have done the job of waking people up and getting them ready. At times they were not aware of due to the time difference, or maybe it was not added in their Google Calendar, so they were not aware of the time difference that they had. But people had worked really hard, and we really appreciate. Although it was a lockdown also, but despite of that, people we met so many times. We met so many times on Saturdays, Sundays, in different meetings, and whatever is here, it is due to the effort of so many people, and I really appreciate all of them. Dr. Mohit Sahni, Professor P.K. Singh sir, and we cannot miss thanking Professor R.C. Singh sir, who always is there to tell us abhi tak tumhara yehi nahi hua. So that line, it always motivates us to bring things with perfection, to bring out things with perfection, because if he doesn't text us, if he doesn't criticize us, so the perfection lacks in that case. We need criticism, and in that case Professor R.C. Singh sir has always he at times he scolds us also. So we really love that. I don't know, Professor R.C. Singh sir is here in this valedictory. Maybe he's in some meeting. We would like to hear from him, and thanks to all the PhD scholars. Although this part goes to Professor P.K. Singh sir to say thanks, but I thought that I should bring out those things also what we did. There are like post credit in the movie, you will see post credit what all happened. So would like to tell you that yes, we met on Saturdays and Sundays, and despite of pandemic situation, many of our dear ones have lost their dear ones. So that was also there, but still we are here looking forward that may our research build up something which is good for the society. This is like my personal heart's desire. So that's all I wanted to say. I could not control myself. I am done. Let me move forward. So
Yes, I think now I am seeing Bhavna. Dr. Bhavna, if you are online, you want to say something? You want to criticize something? You want to give good suggestion, bad suggestion? Your suggestions are welcome. Dr. Bhavna. I think she is also not able to communicate all of us. Anyway, I think Venus, you have to move forward.
yeah, so coming. Yes, Dr. Bhavna, are you there? You want to speak something?
Yeah, I'm here, and my phone was not charged, so I was putting it on. Thank you so much, sir, Professor P.K. Singh, sir, for your always, you are very helping and supporting always. I'll like to quote that I attend all the conferences organized by Sharda University, be it national or international conferences. It is always very good experience to attend the lectures, and I mean, I like to attend the conference in offline mode most, but online mode also it is a very good experience for all of us. So I really want to congratulate the organizing committee, and I would like to thank PK Singh sir for inviting me to give my talk. Thank you so much, sir.
Thank you
I
so
think,
much.
Venus, we are going to open platform for others also. Anybody want to say something? These are almost welcome. Yeah.
Yeah, good evening, sir. Anjali, Dr. Polu. Yeah, it's really, first of all, I'm very thankful to my guru, like Dr. Pramod sir. Is it audible, sir?
Yeah, I think, Anji, you are audible, and PK Singh nothing without his team members. So you must congratulate my team.
Yeah, that's all I'm going to say, sir. And Dr. Professor PK Singh and his team.
Yes.
Yeah, really organized in very smooth manner. And even we have taken a session chair up to around 5 hours. Even we have not find any difficulty in that. That 5 hours that has gone very smoothly. And once again, I'm very thankful to all organizers and your team members, sir. Yeah, thank you, sir.
Thank you so much, Dr. Reddy.
Hello, can I speak something?
Yes.
Hello.
Yes,
Professor
please.
Pramod, how are you? Now I see you again. Okay, maybe on behalf of Malaysia. Now is 8 p.m. So everyone is going for dinner or take bath something. So I'm representing all my family. So I would like to thank. Yes, I would like to thank Prof. Pramod for this invitation, and you always sending me flower every morning. That's very nice of you. And then you always sending the invitation. Some of them I cannot join, but this year I started to follow you. And then I found that this is very, very good for, especially for my students. Some of them not familiar with talking to audience, especially presenting the scientific content. And this is a very good platform for them. And also for the, we call that the new staff. As our target that some staff they need to publish at least 1 to 3 papers. And then this platform is very good for them. I mean, it easily can be published because the reviewer is among us and so on. So thank you very much, Pramod. Please do it again. I will follow you.
Yeah,
Thanks.
I think now till my team member is here, I promise you that when this COVID pandemic situation is going up,
yes,
I am again in Malaysia with my team member this time. I have already planned.
Good.
Okay,
That's
and
good.
we are going to
All
take
right.
that fruit. And I forget his name. There is a one fruit which we like too much
All
in
right.
Malaysia.
That's good. Thank you very much. Okay.
Yeah, thank you.
Thank you very much, everyone. Bye.
Thank you so much, Professor Ahmed. So shall we move now?
Yeah, I think now you open platform for our student also if they want to say something.
Yeah, Gaurav, would you like to say something, Gaurav?
Any student.
Any student who would
say,
like
I want to say something.
Ibrahim is saying thanks. Abu Bakr is saying thanks. All the students are saying thanks in the chat box.
They do not want to appear physically, not physically, maybe online too. Because once they are going to appear, we are going to say them homework.
Hello.
Professor Bhattacharya.
Hello, am I audible?
Yeah, Nilesh, you are audible.
Sir, very half an hour I have seen, I am looking your smile.
Okay, thank you.
Dr. Pramod
Now I am
Singh,
going.
what
Now I am going to
great
close.
job, great job done by your team. Very smooth and very great platform. This one you provided, and here I have seen a lot of great researcher, which I think never seen before. So definitely it was great platform provided by your team and your effort. So it is a great, and I would like to say something. Can we start a platform for student for presentation their PPT presentation, not PPT presentation, their poster presentation? Can we start? So lot of students can be connected with us. Actually, some students having some fear, and we don't have time to give them they can speak. We have in a limited slot. So I think if we can start, then student can also enjoy, and we can judge and we can motivate to them also. So you can think, and if you think, then you can do. And so thanks to the organizing committee, and particularly Dr. Pramod Singh also, and other madam, Dillu madam, I'm sorry. So you have done a lot of work continuously. Thank you very much. I'm really happy.
Thank you, Nilesh. Thank you. I think now we
Thank
can
you.
see on via video Muhammad. Muhammad, you want to say something? Because
Yeah,
you
this is
are already
Ibrahim. Yes, I want to say something.
Yeah, it's
I'm,
okay.
yeah, I'm so glad to be part of this reputable conference organized by your reputable school. I was in India when this conference was, announced, and I've been in communication with Professor Pramod Kumar Sil. Professor Pramod Kumar Sil is a very nice person and very calm, and he could respond to challenges because I actually face challenges in trying to register. I want to really appreciate the committee putting up this kind of reputable conference that connects the global world. I will say it's a connection of global world in the sense that in this conference, we have the Asians, we have the Americans, we have the Africans, we have the Europe, all connected in this conference. You will not know what you are doing from your Noida University, Shada University, Noida. From Noida there, close to Delhi, you are connecting the group. And I want to really appreciate, and I want to also stir you up to put up some things like this in the future, so that when I get to my faculty, because I'm back to my country, I was in India when I registered, and I just returned to my country, Africa, Nigeria, so that when next you organize this kind of a conference, I should be able to let my faculty members, colleagues, to be aware and also see how to participate in this kind of conference, and perhaps even giving an opportunity to be one of the inaugural, presenter. The conference, because we are working
I think
we are working on
materials. Thank you.
Thank you very much. I really appreciate it. And we hope to see the outcome of the conference as in when we talk about the publication. I think if that can be facilitated, it will be a good encouragement to all the participants. Thank you, Professor Prasmo. Thank you for all the organizing committee, the chair, and others. Thanks. We are grateful. Thank you very much. Speaking from Nigeria.
Yeah, thank you, Ibrahim. And now I think we are going to proceed further. Dr. Venus. Yeah, so I think Venus.
Yes, sir. So I would like to announce, dear participants, we would like to announce it over here that the prize distribution will be announced on the website because still some parts are left, and actually we have to match the results and all. So there were different judges, and we on this point we would like to thank the judges also who patiently judged all the oral presentations, and the results will be announced on the website. For vote of thanks, I would like to invite Professor P.K. Singh sir to propose vote of thanks.
Yeah.
And this is the team that has worked hard day in, day night.
Yeah, I think Venus, thank you. At least after you can say 4 days diary work, I can say. But whenever I saw a smile from other faces, means faces and my colleagues, I always feel enthusiastic, and that one boosts me to organize this kind of conference. So I am nothing without my colleagues, you can say. But I am happy, at least their common effort, we are at least able to gather nearly 260 participants, not participants, 260 presenters in this conference. And as Ibrahim already informed in front of all audience, the uniqueness of this conference is that we got participation from India, Asia, Europe, Africa, maybe some other countries where I could not believe. So just to time manage, although my senior point out right way, of course we are lagging in some points, but definitely we are going to come up with these kind of, these are you can say minor correction in thesis. So certainly very soon we are going to remove it. And I think with these kind of conferences, the responses which we got, it's overwhelmed all of us. We never expect such a kind of gathering, and all efforts, all things you can say goes to my colleagues, my friends, my seniors, because these are the seniors who always encourage me to do something better. I am nothing without my seniors, my colleagues, my friends. And I think as Dr. Venus already informed to all of you, there are 8 international journals. They are agreed to publish papers presented in conference. So we have already followed some rule regulations set by, you can say, journals. We do not want to dilute the quality of papers which is going to present in conference. So within a week, have a patience, and we are going to send you information regarding to publication. Now coming to last but not least, I think now I have just got, you can say, oral based. We have already announced that we are going to give at least 3 based oral presentation. And I think I make delay because one of, you can say, foreign examiner, she could not send me that report, but right now, just 5 minutes back, I got that results, and now results in my own hand. And I am happy to announce the prize and other things. Maybe we are going to announce later because it's a big money, so we cannot officially announce. But of course, there are 3 best oral presenter. First one oral presenter, you can say, let us congratulate to him. He is OP96 and his name is PK Harjan. He is from India. So first one, you can say this oral presentation, topmost oral presentation is OP96. So we are going to send you soon, maybe hidden prize money to your own account. Don't worry about that one. Then second oral presentation, of course, it's gone to the one oral presentation from, I think, either Poland or France, Miss Carolina. So Carolina was Joskawa. She got second best oral presentation, you can say. And her number is OP115. So we are going to send your prize on your PhD supervisor, who is very close to me. It's not officially, I can announce in front of conference, Professor Bauchata, Sirohi from France. So Carolina is the second, you can say, runner-up for oral conference, oral presenter, at least. Now last one is OP120. And I think it is Navneet Kaur. So third one presentation is, you can say, OP120 got prize, and it is Navneet Kaur. So these are 3 oral presentation from, you can say, judge panel side. So I thanks all of judges, my team member who is in front of you, with seniors, my head of department, my colleagues, my juniors, my friends, my seniors, or anybody. There are many people who are always behind curtain, which cannot, you can say, come in front of audience. But of course, without their help, we cannot move. So many, you can say, from not only related to science, maybe you can say being our another officer like Dr. Mridul, Dr. Anbha, Dr. Harishankar Syam, now they are attending this meeting. So there are many people who always play their best to make this conference, you can say, bloom or maybe in such a organized manner. So I am thankful to all of my Sergeant family members, particularly the Sergeant family and particularly from presenter who is coming from abroad. Because sometimes we saw like Professor Melissa, I never believed that she is present whole day in conference. She is from Malaysia, Professor Melissa, she always with me. I think another one presenter, you can say, our the Professor Maria from Italy. She always. So whenever I saw their faces, I always feel boost up with energy. Professor might, you can say, from France, and many other professors. So I cannot move a single step without my colleagues. With the last word, I think I am most thankful to all of you to attend, to join this conference. And in coming time, as Dr. Venus already told in front of you, we are also feeling problem with this COVID pandemic situation as usual all people are facing. We hope maybe God, Allah, is going to remove this situation very soon and we are in front of you with physical mode. If it is not possible, very soon we are going to come in future to all of you. So once again, I am thankful to my colleagues and all of Sergeant family. Thank you.
Thank
Venus,
you so
much. I think we are going to close this one.
Yes, sir. Thank you so much for joining this session. Stay connected. See you soon. Thank you so much. Thanks for joining the valedictory function. Bye, everyone.